You have fallen into Event Horizon with John Michael Godier. John is joined by Dr. Martin Cordner. Dr. Martin Cordner is an astrochemist at NASA's Goddard Space Flight Center and a research professor at the Catholic University of America. His work focuses on the chemistry of comets, interstellar clouds, and planetary atmospheres, with special emphasis on what these environments can reveal about the origins of stars and planetary systems. He is the lead author of the recent study JWST detection of a carbon dioxide-dominated gas coma surrounding interstellar object 3I Atlas.
Dr. Martin Cordner, welcome to the program.
Thank you very much, John. It's a pleasure to be here.
Now, Doctor, we have run into, or it ran into us, one of the most interesting astronomical developments in the last decade, which is saying a lot because we've already seen two interstellar objects so far. One very enigmatic, and the other one not so enigmatic, but interesting in its own right. And now we're on 3I Atlas, the third confirmed interstellar object. And it is definitely interesting in that it is the oldest thing we've seen other than the universe itself. This thing it could be, based on its motion, statistical evidence, could be 7 billion years old from an earlier time period in the universe. And that begs a question you have to ask: what was the chemistry of the Milky Way like back then? And 3I Atlas has a chance of telling us that. What have you found so far in the short time that everybody's been studying 3I Atlas, which has only been since, early July, something like that? What have you found about the chemistry, and what is it doing that deviates from a solar system comet, a run-of-the-mill Oort cloud object?
Yeah, well, as you say, this is a really fascinating object. A fascinating time to be alive, that we can bear witness to the passage of these interstellar objects through our solar system and be alive in the era where we have access to incredibly powerful telescopes on the ground and in space to observe these objects, find out what they are, where they came from, and what they're made of. As you say, it's fascinating to think back to where these objects came from, what environments they formed in, what the conditions were like in those environments. What we're looking at here with this interstellar object is basically one of the oldest fossils that we've ever seen, a fossil that contains a chemical record, if you like, of its formation environment and the conditions it was exposed to during its travels around the galaxy for the last, as you say, several billion years. Now, we have to be a bit careful when we talk about the age of this object, because we don't have access to sort of isotopic samples that we might be able to put through a laboratory and do an accurate age dating, right? And as far as I know, no isotopic ratios have been derived for this object that might give us real robust evidence of its age. So we have to look to sort of indirect evidence to understand how old it is. And the strongest evidence we have comes from comparison of its trajectory with models, with dynamical models for how these objects move throughout our galaxy and how they move through time, and trace their trajectories back to a likely origin site. And so there was an interesting study by the Otautahi Oxford group, who have constructed a very detailed model of how these objects move in our galaxy to trace back the trajectory of this object, 3I Atlas, and determine that it, with a good probability, that it comes from a part of the galaxy that seems very old in terms of the ages of the stars there. And that's this so-called thick disk population. It's a population of stars within what you would call the plane of our galaxy. Our galaxy is essentially like a plate kind of structure, mainly composed of a disk. But there's this thick disk population of stars which are moving around a bit faster, that we call kinematically hot population. They're moving throughout this disk in a more excited way than the stars in the plane. And this population, this thick disk, could be almost as old as the universe itself. These are some of the oldest stars in our Milky Way galaxy, potentially as old as 14 billion years. And so if we trace back the age of 3i Atlas to this population, if we link it to that population, then what this means is that it could be as old as some of those stars, and the estimates that I've seen potentially place it within an age range of 7 to 14 billion years. So that is, it's incredible to think that we have passing through our solar system one of the oldest objects, potentially one of the oldest objects in the universe. And we get a chance to point our telescopes and find out what it's made of, and get a direct window into the conditions of the system where it formed. We believe it formed probably in a similar way to the comets in our own solar system, which means accreting during the process of planet formation as gas and dust clumps together, if you like, to form these icy, rocky, small bodies which progressively grow larger and larger, and some of them eventually become planets. A lot of them don't grow larger and larger. There's a lot of these smaller objects flying around when planets are being formed within the disk of a young star. And we presume that this is what was happening. We observe these disks around young stars throughout our galaxy, and this is how we believe planets form throughout the galaxy, and also comets. So these kinds of objects are forming in these environments around these very old stars in the thick disk, getting ejected out, and some of them end up passing after billions of years through our own solar system where we can observe them. So that gives us this window back in time. And so we measure the chemical compositions through spectroscopy. We have many different wavelengths that we can study throughout the electromagnetic spectrum, all the way from gamma rays and X-rays and ultraviolet through optical and infrared and radio. This is sort of a library of tools we have at our disposal to investigate chemical compositions of these objects as they heat up and start to release the gases that they've been storing inside for however many billion years. So it's just a case of reading the spectrum then to work out what it's made of. And that's what we've been doing. Astronomers around the world have been pointing their telescopes at 3i Atlas. We've been using our best space-based assets. It's an all-hands-on-deck approach. It's you can think of it as a once-in-a-lifetime opportunity to observe an object such as 3i Atlas. We see that these objects come along every now and then. This is the third interstellar object. There are likely many more. We have no guarantees. This is an unusually bright object, actually. It's brighter than Borisov. It's brighter than Oumuamua. There's no guarantee we'll get another interstellar object this bright. So it's all hands on deck and all telescopes on the sky to point at this object and work out what it's made of. So what did we find? That's something that we are addressing with our current studies, and I just submitted an article to Astrophysical Journal Letters on the composition of 3i Atlas as studied by the James Webb Space Telescope, and we have beautiful infrared spectra of this object. It was a short integration on the sky, a short observation, just a preliminary reconnaissance of this object just to get a first inkling of what it is and what it's made of, and some of its properties, so we can follow up a bit later when the object is brighter. This is just our first try, and what we saw was just amazing. The amount of carbon dioxide, CO2, in this object's atmosphere. I refer to the gases coming out of the object as an atmosphere or a coma. The coma is the typical nomenclature that we describe these gases with from a comet. There's no reason to assume this is a comet a priori as it's coming in. We don't know much about it at all. But from our observations, it seems very comet-like. It produces a dust scattering of optical light surrounding the object as a result of interaction of the dust in its atmosphere with the solar radiation. So that was the first evidence that it has a coma. And then we see some of the gases it's producing. And with the James Webb Telescope, we were able to see, as I say, very strongly the carbon dioxide. We also picked up fainter emissions from carbon monoxide. And then fainter still was the water emission, H2O, water vapor. And so we're starting to build up a picture of what it's made of. And these are the typical gases that you see in the comets that we all know from our own solar system, comets like Halley, Hale-Bopp, 67P, Churyumov-Gerasimenko. There's a lot of comets with unusual names, and we see them every year, and we build up an idea of what they're made of, and kind of performing chemical surveys of these objects. And just time and time again, when we observe these comets from our own solar system, we see these gases which seem to be coming from the sublimation of solid ices inside the nucleus. As they heat up, as they get heated by the sun, these gases come out, form a coma or atmosphere, and then we observe them. So 3i Atlas, back to your question, John, very CO2 rich, surprisingly water poor. What this then translates to is a high CO2 to water mixing ratio. And when we compare that to typical comets that we observe from our own solar system, that CO2 to water ratio is one of the highest ever seen in a comet. In fact, it's the highest ever seen within the distance range from the sun, between 3 to 4 astronomical units, where we observed this object. We can talk a little bit about the variation of that ratio with heliocentric distance and how it's supposed to behave. You know, this water abundance, this low water abundance and high CO2 abundance, that's likely to change as the object evolves and gets closer to the sun, because water has a different set of physical properties to carbon dioxide ice. Water ice doesn't like to sublimate or enter the gas phase as easily. It takes a higher temperature to produce water vapor from water ice than it does CO2 vapor from CO2 ice. So we can envisage that as this object's coming in, it's not very active when it's far from the sun. It came in from, of course, parsecs, light years, thousands of light years away, and it's come all the way to approach our sun and start to heat up, and these ices start to sublimate. And the first thing to sublimate is the carbon monoxide. In terms of the things we observe, carbon monoxide, CO, is very volatile gas. It likes to leave the ice phase very quickly. As soon as the ice heats up above about 20 or 30 degrees above absolute zero, that CO ice starts to enter the gas phase. And then as the comet approaches the sun more, the CO2 starts to be released. And then one of the last volatile species to be released from the nucleus is the water. So we think that there's probably an element of that going on. And as the comet, as the object 3i Atlas approaches the sun closer, that water production rate is probably going to start coming up. And the CO2 to water ratio is therefore going to come down a bit. But we think that compared to the other comets we've observed from our own solar system, if it behaves in a similar way to those, even when it gets close to the sun, this object has so much CO2 coming out of it, we think that it's still going to look very CO2 rich. So even accounting for this temperature and distance from the sun variation, this still looks like a chemically unusual object.
Now, in regards to the carbon monoxide and how there's not a lot of it, let's take that one first. Could that indicate that the object passed semi-close to a star system in the past at some point in its history and it got depleted? Or did it get depleted when it was, before we even discovered it, when it was coming in? Is it that volatile to have depleted its carbon monoxide before we ever even saw it?
This is a fascinating question. It gets into issues of the nature of interstellar objects. How much of the different chemicals and ices do they contain? What was their intrinsic inventory? Did they come from an environment that was rich in those gases? Could they have been then lost? If we think about Oumuamua, we didn't spectroscopically detect any gases coming from Oumuamua, the first interstellar object. And some of the theories to explain a lack of outgassing from what should be a cold, icy object is that, well, maybe it passed close to a star on its way. Maybe it got heated when it was being ejected from its host system. Maybe it had a close encounter with another star in its host system that meant that some of that intrinsic chemical inventory, such as the more volatile species, carbon monoxide, methane, maybe they ended up getting sublimated away before it even arrived here. maybe there was chemical processing happening within the body during its passage. That's another really intriguing thing to study from a laboratory astrochemistry perspective. You could irradiate these sorts of ices in the laboratory and see how much of them survives and how much of it gets turned into something else, how much of it gets sublimated, and then that's the sort of experiment you can then do to compare with the chemical inventories that we observe and see if they are changing in the way that we might expect, or if we can predict some of those chemical changes that might be occurring, and then compare those to observations to try to validate our theories. So, but just going back to your question about a relatively low amount of CO. So, we see a CO to water ratio in 3I Atlas of greater than 1. I think it's about 1.4. So a little bit more CO than water. And from a global cometary science context, that's actually fairly CO rich. So we have to bear in mind that at the present time, it seems like there is a pretty decent amount of CO in this object. But again, as it approaches the sun and the water comes more active, the CO2 is unlikely to become more active. And so it may end up, as you say, showing evidence of being CO depleted in that case.
Now, in regards to the object, so, all right, it comes in, and we're looking right now at its profile on its way in. Then it hits perihelion, and maybe we can study it with some Mars probes and things like that when we can't see it. It's behind the sun. And then it goes on its way out. How do comets overall change? At least with solar system, we haven't seen what this one will do yet, but with solar system comets, how do they change, chemically speaking, on their way out versus what they looked like on their way in?
Well, as comets pass through the solar system, most comets that we observe with our telescopes and even with our eyes as they come through the sky and light up, they're passing pretty close to the sun, and the amount of solar radiation that they're receiving on their surfaces increases, with the 1 over distance squared rule. So as it gets closer to the sun, the heating increases with the inverse square of the distance from the sun. So the heating really ramps up the closer the object gets. And as a result of that, a wave of heat from the surfaces of comets are fairly dark, a bit like the moon. They may appear shiny, but in fact, they have a low albedo, which means they absorb a lot of sunlight. And so this thermal heating on the surface proceeds inwards and starts to heat the ices that are stored inside. Those ices sublimate, come out. We see them as plumes and an outgassing. And then as the comet comes past perihelion, it's closest to the sun, the heating, of course, peaks there and the activity peaks. And as the comet starts to move away, there's sort of a thermal inertia effect that we sometimes see, that even though it's moving away from the sun a little bit, it's still receiving heat, and it can still be heating during that stage, even though it's moving away from the sun, because it's still receiving heat, and there can still be a net heating of the nucleus. So as that comet then proceeds to move further away from the sun, the heating decreases, the cooling increases, it radiates its heat to space, and ultimately the sublimation starts to decrease from the inside out. So the inside will start to cool before the outer layers. And so if there's more water in the outer layers, because it's less volatile and kind of sublimated less overall, then you may see an increase in the water and a decrease in the other gases during that period. But it's quite complex and depends on the intrinsic structure of the nucleus. And so as it cools, we expect to see changes again in the chemical compositions. And interesting effects can happen as an object sort of rounds the sun in terms of seasonal effects. You think of a comet, you think of a rock, an icy rock moving through space. You don't sort of immediately think of them as sort of seasonally varying objects. We know planets have seasons depending on their polar tilt. Well, comets can have seasons as well. They spin, they have an axis. If that spin axis is pointing towards the sun in its north as it approaches the sun, then of course we'll have more heating in the north, and that could get depleted of volatiles, depleted of ices, such as the water and the carbon dioxide and the carbon monoxide and other ices that may be present. And then as the object rounds the sun, it might point a different side, a different part of the comet may come into sunlight. And so then we could see fresh sublimation of material that wasn't previously being heated. So things can change significantly during that process. And
it's gonna be fun actually, because I've seen comets before, going all the way back to Hale-Bopp back in the 90s, observing that with, in my amateur capacity. And yeah, they can flare, they can do all kinds of interesting things as their conditions change. And this might do that. I don't know if it'd ever go too crazy, but still, it's really interesting to get that profile along the whole passage of the object. Are you happy with the amount of observations being done? As a scientist, do you think that the data set that we're getting on this object is as robust as we could be doing?
I'm a scientist. I always need more data, John. There, in my opinion, there should be no limit to the amount of data we should be obtaining on this unique and very special object. Having said that, I'm but one scientist among a global network of astronomers studying many galaxy collisions, dark matter, star formation. So there's many different competing topics to use our telescopes for. We live in an amazing time of astronomy with access to so many amazing and large and powerful telescopes to observe all these phenomena, but we are limited in the amount of funding that we can request and be granted by government funding agencies or various kind donors, people who want to build telescopes and provide money for this sort of thing. So I'm going to say, we definitely would benefit from more, but for the time being, I would say I'm suitably impressed with the amount of attention Atlas is getting from the global media and from the global astronomical community. Everybody in planetary science, for sure, is fascinated by this object and watching it with bated breath to see what it's doing next. In telescope time, we don't just go and knock on the door of one of these big telescopes and sort of tell the operator what to point at, or make friends with him, buy him a beer, and pass him the coordinates of what we want to see. It's a very strict and tightly governed process, subject to intensive peer review, and so it's a little, you could say, the wheels sometimes move a little slowly, and so what that means is that we may have to put in applications for telescope time that have to be vetted by the standard procedures and then peer reviewed by other scientists to allow us to actually get these data sets and to do more and more observations. So right now, we're writing our telescope proposals, observations, and we have to be hopeful that the people that review them grant us that precious telescope time so that we can carry on observing 3i Atlas in the best way. Now, I'm also aware of coordinated efforts to use various space assets to observe 3i Atlas. It's such a unique object that NASA, with all of its space hardware, is orchestrating a plan to get as many different instruments from as many different pieces of space hardware and interplanetary missions as possible to observe this object during the short amount of time we have. Part of the issue here is the fact that the object in question, 3i, is traveling fast and travels past the sun when the Earth is on the other side of the solar system to the object. So it's not going directly behind the sun as we observe it from Earth. It's on a sort of a tilted orbit as it comes in. But it's basically in a part of the sky which makes it very challenging to observe from Earth and using any telescopes around the Earth. And so that closest approach to the sun happens October 29th, just a month and a half or so from now. And the fact that it's so close to the sun means that, we're going to struggle to observe it, and we're going to struggle to monitor it using ground-based hardware. So we have to look to space-based hardware, and there is indeed a large number of space missions flying to various planets. We've got Juno at Jupiter, we've got Maven and MRO at Mars. We've got various hardwares at Mars. There's numerous rovers and orbiters around Mars at the moment, which will be able to do a much better job of observing it close to perihelion than we'll be able to do from Earth. So it's incredible to think about this orchestrated effort going on through from around the solar system to get what we can on this object. From that perspective, I'm confident that we'll be able to be monitoring it with sufficient regularity and sufficient wavelength coverage that if this object does do something unusual or surprising, even if it doesn't do something unusual or surprising, it's still important to measure that. And measure is certainly going to change and evolve as it passes. And so, yeah, it's crucial that we have these plans in place to keep on monitoring it as it carries on and continues to provide a source of intrigue for astronomers.
Now, formation temperature. So could it be that where this object formed within its star system of origin could be defining the chemical profile that we see? In other words, can they differentiate? I mean, with a very, very small object like that, where maybe the water is simply deep inside of it, as opposed to near the surface where it can be warmed and sublimate, whereas the carbon dioxide and monoxide are shallower. Can that actually happen, or am I completely all wet and that it wouldn't do that?
Well, we don't know how big this object is, right? There are some estimates, some initial estimates, which didn't take into account the fact that it had a coma that was making it seem brighter. Initial estimates said it could be a few tens of kilometers in size. More accurate measurements that try to subtract off this bright, dusty coma and therefore leave the signal from the nucleus are showing us that the nucleus size is less than a few kilometers in radius, less than about 3 kilometers in radius. Nevertheless, that is, that's small on an astronomical scale or on a planetary scale. But with an object of that size, you get into a realm where things are starting to differentiate. And the reason is that the heat doesn't penetrate very quickly into the nucleus. It's quite a porous sort of physical structure, kind of almost maybe sponge-like. And we know this from the visit of the Rosetta mission to Comet 67P, and also the gathering of cometary dust samples from other sample return missions to space. We know the density of comets is very low, and because of that low density, heat doesn't easily penetrate inside them. And what that means is that even if the comet experiences significant heating from the outside, the heat doesn't penetrate that far. However, if the heat penetrates a little way, say a meter or a few tens of centimeters, then you would expect the preferential loss of the more volatile ices from those surface layers. So the closer to the surface you are, the more likely you are to lose those volatile species. And so you may end up with more water-rich layers closer to the surface because water is the less volatile. And this is greatly simplifying the complex thermodynamic theory and thermochemical calculations that you would have to do to really determine how the interior chemical abundance structure changes with time and with heating rates. So it's broad brush, but yes, I believe that it would be possible to end up with a differentiated body. You talked about differentiated bodies in general. We're talking about maybe part of the object being CO2 rich, part of it being water rich, maybe part of it's rich in organics, or other ices like maybe ammonia, methane, something like that. And we see this kind of chemical differentiation happening on other small bodies in our solar system. When I talk about these kinds of small bodies, I'm thinking icy moons of Jupiter, Saturn, Uranus, Neptune, thinking about distant objects in our solar system, the dwarf planets like Pluto, Sedna, and these other trans-Neptunian objects. Well, when we look at those objects, we see clear chemical differentiation of the surface ices. Now, this can happen for various reasons. Geological processes, for example. If we look to the very small moons of Uranus, which may be hundreds of kilometers across, they're big enough that when they formed, in the protoplanetary disk or in their subnebular part of the formation zone where they formed, then it's quite likely that they have a differentiated chemical structure, which means that some ices may sort of float to the surface. The heavy elements, the metals, sink to the core. They're warm enough that these kinds of bulk transport processes can happen, and you end up with a differentiated object. Typically, comets aren't considered to be large enough to be able to do much of that. They don't get hot enough when they form. When they form, they don't preserve enough of the formation energy, the heat. It gets radiated away. So they're pretty cold. But we can envisage comets forming in different parts of the protoplanetary disk that they came from. There could be a water-rich part of the disk where there's a lot of icy pebbles, maybe closer to the sun, and more carbon dioxide, carbon monoxide, methane-rich as you go further out. So we can form different bodies in these different parts of the protoplanetary disk through mixing processes, through gravitational and dynamical mixing of these bodies throughout the disk. They can be transported in or out, and maybe two chemically different objects can meet each other, come together in a slow collision, and ultimately coalesce into a single object that may have a differentiated composition. So we may be able to probe these kinds of dynamical and chemical processes if we observe dramatic changes in the chemical composition that can't be explained in other ways.
A lot of options there, and I think one of the things that speaks to that is, you look at these outer solar system objects, and we looked at the one with New Horizons, that it's two objects coalescing very slowly. They come into contact, they're orbiting each other, and then they come into contact. Well, what does that do to composition? Now, one of the interesting aspects of 3I Atlas is that we see nickel chemistry, and we see evidence of that. Not really seeing iron, and those two like to go together. What do you think about that mysterious aspect of this object?
So yeah, you're talking about some observations which were done with the VLT telescope, spectroscopic observations of 3I Atlas in the sort of optical UV range. I'm aware of those, and I saw the spectrum there, and I saw so many peaks in the spectrum due to nickel, just atomic nickel. Now, the detection of these kinds of atomic metals in our own comets from our own solar system was only first realized a few years ago, maybe in the last 5 or 10 years, that comets contain these atomic metal vapors. And to my knowledge, since their discovery, it hasn't been possible to explain why comets contain those metallic vapors. So this is a really interesting puzzle, and I was very intrigued to see detections of iron and nickel in the second interstellar object, 2I Borisov. It implied that it was subject to a similar sort of maybe surprising metal-based chemical composition for some of the material inside that object. Now we're seeing 3I Atlas, very nickel-rich. No apparent signatures from iron vapor. Iron and nickel are both produced inside massive stars late on in their lives. And, we're thinking about whether this object, 3I Atlas, may have originated from a metal poor system, an old star, which maybe there was lower enrichments of metals in its surrounding protoplanetary disk when it formed. It seems plausible that 3I Atlas could have formed in a relatively low metal environment, and yet we're seeing a strong nickel signature. So chemically, that's very interesting. And from an elemental synthesis perspective, from understanding how atomic elements become created and these sorts of heavy metal atoms get produced in the galaxy, I think that this is probably going to be telling us something pretty interesting about the nature of the material this object formed from. I would say it's too early yet to really be definitive, because we're observing this object quite far from the sun. We've talked about the issues pertaining to how different ices and substances enter the gas phase and sublimate as the comet comes closer. Potentially the iron could start to appear. I would say it's early days to say for sure this object is iron poor. So once we have more observations in hand, we'll be able to make a more robust statement about that, and then try to understand more about whether that is indeed a signature of a peculiar initial elemental composition, and what that could therefore mean in the context of how these elements are synthesized and enriched within our galaxy, and what their initial compositions may have been. So yeah, I think it's a fascinating question. I think it's really fascinating to try to understand why we're seeing these metal vapors in the comet Coma as well. It's not obvious, mainly because these kinds of metals, they typically, when we think of how interstellar chemistry works and how dust chemistry works, everybody knows that metals like to stay in a solid form. If you were going to make something to survive a fire, would you make it out of ice or wood or or metal? It's pretty obvious, right? And so these kinds of metals, these metallic atoms, they like to stick together. They like to form metals. They like to be solid. Why are they sublimating into the gas in a comet Coma, coming out of essentially an icy phase, a very cold phase associated with a lot of ice? This is something very peculiar, and it's a great question for chemists to try to answer. It seems as though these metal atoms are probably bonded in some kind of chemical structure that is liberated during sublimation, along with the ices that are sublimating. Yeah, as I say, something for the chemists to go after in the lab and try to explain this.
That's a huge chemistry question. It's really interesting because you're looking at, ostensibly, again, early chemistry for the universe. So things might have been a little bit different back then, especially if it's really, really old. And that might hint at certain things. Now, with meteorites, we see obviously tons of nickel and iron in our meteorite collections. And this is sort of saying, well, it's a little bit different when you're forming way out far from your star. And, we see that too with the carbonaceous chondrites, and that those metals drop off. Those are associated with comets or cometary material, and those metals start dropping off, but they're still there. But they're still at that same ratio of typically 7% nickel and most of the rest iron. But without an iron emission here, it's a little bit weird. Is it possible, though, that we know that asteroids differentiate? We have pallasites, which are a kind of borderline between chondrites and iron meteorites, and then, iron meteorites, but comets really don't. And so does that speak to where this object formed in its star system of origin? Did this form someplace likely to be very, very cold, like our Oort cloud? Or could it have formed a little bit closer, and that's the weirdness? That might explain some of the weirdness.
Yeah, so there's a lot of questions there about asteroid chemical abundances and how those come about. As you rightly said, asteroids can be differentiated. They may have come from larger bodies, which were able to thermally differentiate. For the comets that formed in our solar system, the presence of very volatile, hypervolatile ices, methane and carbon monoxide, they show us that our own comets must have formed, or must be comprised of material that formed at these extremely low temperatures. And even N2 was molecular nitrogen was detected in Comet 67P by the Rosetta mission. It's incredibly volatile. That won't stay around through any sort of thermal processing. So I don't envisage that our own comets have been subject to much in the way of thermal processing. They do incorporate grains from the Stardust mission, where cometary dust grains were collected and brought back to Earth in a special kind of gel that captured those grains and brought them back intact.
Yeah, the aerogel, where everybody was citizen scientists and looking for tiny grains embedded in the aerogel from that mission. It's absolutely amazing.
Yeah, it was incredible that so many of those grains were detected, and a lot of the organics got burnt off, but I think a decent amount of the metals were remaining. Those grains that were picked up within the aerogel were found to contain minerals, olivines, iron-rich silicates that were formed. They can only be formed at very high temperatures. And so what this tells us is that comets can contain materials that were formed at high temperatures, but those grains where, they're small, and we're not talking about macroscopic particles here. We're talking about microscopic particles, sort of microns in size. And those kinds of grains, which are present in comets, clearly contain these metallic substances that we're talking about. So they can certainly be incorporated in comets. But the actual chemistry of those and how they can lead to the production of just atomic vapor upon sublimation, to me, that's still a significant puzzle.
Now, regarding the brightness of 3I Atlas that we briefly touched on, it's unusually bright for what it is. That's not really saying much. You're not going to walk outside and see this thing unless you've got a 8-inch telescope or something like that. But it is bright, and that's leading to the ambiguity of the size, which Hubble constrained that down. I think you said 2.5 kilometers, something like that, which is actually really small compared to something like Comet Halley or something like that, which I think was orders of magnitude larger. So
Halley was about 10 kilometers.
Yeah, it was bigger than, it was like 4 times that size. So this is a small object, but that's not all that well constrained. And some people have said that if the object actually turns out to be really large, which, the upper limit on that was like 24 kilometers in early July, but I think that's not on good, solid ground at this point. But that would make it very, very strange. Is there anything about this object that gives you pause? And other than the chemistry, which is interesting in its own right, but it's not unexplainable. Is there anything that gives you pause, given the controversy that surrounds this object, that makes you go, that's a little too weird? Or is it well within the limits of what you would expect from an interstellar comet, accounting for what we don't yet know about these things?
Yeah, so great question. And there's a lot that's weird about this object. Is there anything that's too weird to be explainable as a result of natural phenomena? I don't think so. But from what we know about the orbit, the trajectory of this object, it's a little unexpected, to the point where we would say it's on a statistically unlikely trajectory through the solar system. And I want to give the dynamical modelers a lot of credit for what they've done in working out the potential paths of these objects through the galaxy. There is a stronger likelihood of encountering these objects from certain directions of the sky as a result of the direction that our sun is moving through the galaxy, and also higher probabilities that these objects appear from certain constellations based on streams of these objects through the galaxy. They interact with gravitational fields and galactic tides, which push them about and form them into streams. And the Otautahi Oxford model was saying that this object seems to be a little surprising in terms of where it's coming from. It's coming from a direction away from the solar apex. So if you were just to pick an interstellar object at random, you would expect it to be coming from somewhere in the northern hemisphere of the celestial sphere. This one's coming from the south, coming from the direction of Sagittarius. And so just that origin, that point of origin is a little peculiar, but not to the point where I would say, that's statistically extremely unlikely. These objects can come from any direction in the sky. So the fact that one comes in from this direction and it's at an angle very close to the orientation of our ecliptic plane, the plane that the planets are orbiting. All our planets are orbiting in this plane of the solar system, and 3I Atlas is coming in at 5 degrees to that plane. So that in itself is also fairly unlikely for it to be on this trajectory that brings it so close to Mars and Earth's orbit, and then onwards out. It does a very close flyby of Jupiter later on as it's on its way out. So the actual trajectory of this object is a little bit unexpected. But as I say, not to the point where I suspect anything really strange going on, but that's just something notable, I think. Other peculiar things about this object that are noteworthy, in addition to the CO2-rich coma, the nickel-rich coma that we've already talked about. When it was discovered, and within a few weeks after the discovery, it was showing this ejection, or basically a sunward enhancement in the coma, which means that the coma dust seemed to be having a tendency to to show an asymmetry in the direction towards the sun. And because this object is coming in on a trajectory through our solar system that goes pretty close to the sun, then that means that the direction, if you're standing on the comet nucleus, standing looking up at the sun, the direction you'd be looking up in would be similar to the direction of travel of the comet. And that's the direction that it seems to be preferentially producing its coma in, or at least it was. The latest images from the Gemini telescope were showing that, contrary to those initial images from early on in its detection, it's now showing a tail or trail of debris that is more typical for a normal comet and pointing in the direction away from the sun. So it's behaving a bit more like a normal comet now. And, we may sort of think to ourselves that that was a very peculiar thing to observe a comet with a tail pointing towards the sun. But as I say, we think of it more like a plume. And when you think of it like a plume, it's not altogether surprising to envisage a situation where the nucleus of the object is heating up on this direction towards the sun. That's where the sun rays are striking and warming the surface. And that's where the production of gas is likely to be the strongest, driving out the dust in the direction towards the sun. And imagine this object hasn't been exposed to any heating for perhaps billions of years. The first thing that happens when it starts to heat up is you might start to get some outbursting kind of events as pressure builds up beneath the surface. You may get some sort of violent ejections of dust during those initial warm-up stages of this object that could force out the gas and dust in the direction towards the sun. So from that perspective, yeah, it's an interesting object. It comes from a slightly weird place, and it was doing some slightly weird, unexpected and unusual things when we saw it. But I don't think it's surprising that an object from such a different part of the galaxy potentially would behave in a slightly unusual way when it first starts to get heated up.
It's interesting about the sun spike or anti-tail, whatever you want to call it, but I'm careful with that because comets actually have two ways to produce an apparent anti-tail. One is, the preferential heating you're talking about, where it's shooting it off in one direction. But also, you can get an optical effect or a perspective effect of anti-tails with comets. And I actually saw that with Hale-Bopp. So you've got two mechanisms, and it's like, well, interesting, but I don't know if too much should be made of it. However, what I want to hammer home here is on the point of it coming in from a slightly weird angle, that could get way weirder. And if we'd have had all these spacecraft during, for example, the Grand Tour alignment that we took advantage of with Voyager 1 and 2, and you see it, some kind of an object coming in and doing very close passes like a Voyager spacecraft to as many planets as it can based on where it's coming from, this could get much, much stranger, is my point, that you could see something that would really raise eyebrows, based on alignments of the solar system. If somebody were to, some alien civilization wanted to take a look at everything here, you could do much better than this and pass much closer to planets based on alignments. And I think that it's not hard to point a telescope to the solar system and work out what the orbits of these planets do. We do that ourselves. So it isn't that far out of normal. But I have one final question for you. Should we even be calling this a comet, or should we be calling it an exocomet? Burning nomenclature question for you, and I worry about such things. Should we be calling this the exocomet? And should we have an entirely different, well, I know we have the I, 3I, 2I, whatever, but should we change our terminology regarding this subject?
Yeah, I like that idea, actually. It's awkward for me to always talk about comparing this comet to the comets from our own solar system. And that is to say that, there needs to be a way to talk about this thing in the context of comets, maybe without actually calling it a comet. It's nice to reserve the word comet for our own comets, right? Which we've been studying for, well, thousands of years. If you look into the historical records, comets have fascinated astronomers over the eons, and we've learned a lot about them and their chemistry in the last few hundred years. So yeah, to be able to to really discuss these new objects and give them the credit they deserve compared to our own comets. I would probably say that calling them exocomets is reasonable. There's a field of study already in place which studies exocomets in protoplanetary disks or debris disks around young stars, where we believe dust and gas is coming together to form new planetary systems, and we see signatures of outgassing bodies, which are what we have referred to as exocomets, because the analogy is with exoplanets, right? Exoplanets are planets around other stars. Exocomets have therefore historically, that's the term coined for comets around other stars. Well, interstellar comet seems like a pretty good moniker for these kinds of things, because they've spent most of their lives in the interstellar medium. So I quite like interstellar comet. Exocomet could do.
Or you could say former exocomet. It's interesting because, I remember papers from a number of years ago now that had looked at the Kepler data and detected what appeared to have been exocomets, as you said, in young star systems moving through. And they actually had a certain very specific profile. It was really interesting. But my question would be is that as you get better observational ability, say you build a super Kepler spacecraft, could you work out if that comet passing by the another star, could you determine if it's interstellar, moving through another star system at a hyperbolic orbit? But I don't think anybody's thought that far ahead. Doctor, thank you for joining us today, and I wish you great luck in continuing to study this object. And I'm making the popcorn, so to speak, to look at the chemistry of this object and how that evolves as it passes through the star system.
Thanks a lot, John. Yeah, we still got a lot of work to do.
Marshall Eubanks is Chief Scientist at Space Initiatives Incorporated, where he works on lunar communications systems and mission concepts to explore interstellar objects. He previously led interferometry programs at NASA's Jet Propulsion Laboratory and the U.S. Naval Observatory, helping build the navigation and timing systems behind modern spaceflight and GPS. He is the lead author of the recent paper 3I Atlas, Direct Spacecraft Exploration of a Possible Relic of Planetary Formation at Cosmic Noon.
Dr. Marshall Eubanks, welcome back to the program.
I am not actually a doctor. I'm sorry, but I am not.
Really? I didn't know that.
No,
You're
I'm a
master's.
physicist. I just have a master's, yes.
So that who was famous for that was Freeman Dyson. Also was master's.
And Bill Kalla also.
Yeah. And Dyson on purpose because he didn't like the PhD system.
And I could spend an hour talking about me, but I'm not going to.
Now, we have what is arguably the most interesting object to look at in the solar system in quite some time, at least since Oumuamua, maybe since Borisov. We can give Borisov a little bit of a boost there, but we have the third confirmed interstellar object we've ever seen, 3I Atlas, and it's turning out to be extremely interesting because it's possible from a statistical point of view that it's very old, significantly older than the solar system, and originates from an area of the galaxy called the thick galactic disk, which went through a very interesting period called cosmic noon. Can you give us an overview of the idea of what cosmic noon was?
Well, the idea was that during the early period of the galaxy, and this is really early, so the galaxy looked rather different. It didn't have spiral arms. It had a higher gas density, and gas density means the production of stars and planets and planetesimals and things like 3I could be. And it's called cosmic noon. This, in astronomical terms, this would be a redshift of about 2 we're talking about. So about 10 billion years ago. I think in our paper we say 9 to 12 billion years, but something like 10 billion years ago. And a redshift of 2 is pretty far away. And so to see these things in the right now by looking out into space, deep space, they're all like far away galaxies that we can't see very well. And of course, we can't see what our galaxy was like directly at all 10 billion years ago. I mean, we don't have any old photos lying around. But the one interest, the consensus model for this is that when the universe formed, it was mostly hydrogen and helium, a little bit of lithium. maybe a little beryllium. And then the first stars, the so-called population 3 stars formed, and they made some elements, and then things went on from there. And the the cosmic noon was a period when this process was really in sort of midway, you might say. And so star formation was more intense. The stars, in star formation, it's very common to have big stars and little stars form. The big stars form supernova fairly quickly because that's what big stars do. And then they both radiate, they both spread out the elements they form, but they also radiate, the supernova remnants radiate the other stars. That seems to have happened to the solar system in its early days. In cosmic news, things were much more intense. There were predictions of maybe that any solar system forming then would typically have a temperature of 300 Kelvin, i.e. more or less room temperature, or, well, a little cold for room temperature, but more as the kind of temperatures you might have on the surface of the Earth. Really different from the very cold temperatures that stars form in now. But also another interesting thing is that there's several ways to form elements, and they take different times. And the heavier elements, the iron peak elements as they're called, and the ones heavier than that, form in supernova that take a long time to happen. They're smaller stars like binary stars. They take a longer time to happen. And as a result, we think that, well, in fact, from stellar data, we know that the stellar spectral data, that in the cosmic noon period, the iron peak, all the really heavy elements were really depleted. They just hadn't had time to form yet. And so we see alpha elements, ones that are, ones that are made by taking carbon and adding helium-4 alpha particle to it, and then taking that and adding another one, so you get like oxygen-16, carbon-12 to oxygen-16, and so on. And they should be enhanced in that, or relatively enhanced in that, and anything higher than that, like the iron peak and above that, should be depleted. So these things are different. And if you're really interested in astrobiology, you have to think, well, what did that do to the astrobiology then? Was astrobiology possible? You had different elemental compositions, you had different star formation, planetary formation going on. And the answer to that, I think, is we just simply don't know. There's some papers on this, but do we really know? No. And now we think what we're seeing in 3I. Remember, back a fair ways, but this became sort of pretty widely known in the astronomical community in the time of 1I, Oumuamua, pardon my Hawaiian pronunciation. The probability of an object that forms and is in a stellar system, like a comet or an asteroid or planetesimal, whatever, and then is lost from that system for whatever reason, whether it's because the star explodes, or whether it's because the two stars nearly collide and disrupt the system, or whether it's just the planetary formation stuff like we think happened in the solar system, where Jupiter and Saturn moved in and out, and they moved Uranus and Neptune in and out, and thus most of the early asteroids were sent into deep space, and a lot of them were lost. And all this stuff should be going on with early objects, and things will be lost. But the probability of one hitting or coming close to a planetary system, like within, say, a few astronomical units, is very small. And so it's most likely that what we're seeing with 3I right now is the conditions, the state it was in after it was born. It's something like a newborn baby. It has just been out there ever since. That doesn't mean necessarily things didn't happen to it early on. It might have formed from a collision of two planets or something. We don't know. But it's most likely that since whatever that was in the early days, 10 billion or so years ago, it's just been traveling freely. And then you might ask, well, why do we think this? And the arguments right now are primarily kinematic, and that means primarily statistical in nature. So they're not proof. They're just statistics. 3I has a very high velocity. And this velocity at infinity, the velocity it had when it was near the solar system, but before the sun's gravity started affected it, 58 kilometers a second. It's hard to get across how fast that is. That's multiple times faster than the Voyager spacecraft, our fastest spacecraft. That's something like 60 times faster than a typical fast rifle bullet. That's fast enough that you would pass an Earth radius in 100 seconds. So you would go, you would go past the whole Earth in 200 seconds or so, 3 minutes, just the whole planet would go flying by. It's really fast. And there's another celestial happenstance here. It's going to pass by the sun closest on the far side of the sun. And there's no deep reason for that. It's like throwing darts at a dartboard. Sometimes the dart's going to hit to the right, sometimes the dart's going to hit to the left. It's not like there's a deep reason. It's just, well, as it happens, the dart is hitting on the left and we're going to be on the right. So that means the Earth will not have a good view. It is not in a prime, box seat for the closest approach of this comet to the sun. And so we have to rely on other things. And we will get back to that. But the fact that the velocity is so high means, and the velocity out of the plane of the galactic disk is also high, both of those two facts together mean that it does not seem like this object is a thin disk object. The sun sits in a thin disk, which is this more or less plane. It's maybe 100,000 light years across, and maybe at most, again, a statistical thing, but something like 1,000 light years thick or something like that. Not Oumuamua, 3I Atlas's orbit takes it out to 1,000 parsecs or 3,000 light years. So it's further away. Now, again, that's a statistical argument. That's like saying if somebody is walking around near near a bank robbery, they might be a bank robber. Well, it's not proof. And what we're trying to do now with a whole bunch of astronomical observations is to try and get some proof.
Getting proof and more observations, because it seems to me the most important thing we could be doing in regards to this object is looking at it and looking at it repeatedly and watching it evolve and change as it nears the sun and begins to change its outgassing profile. What's particularly interesting is it's already a little odd for what it's outgassing, the lack of iron, yet you see nickel compounds and things like that. Well, it's interesting to wonder about things like a crust that it might have formed on it, being out in the interstellar medium so long and being exposed to, and reddened so much by cosmic rays. But what can we do as far as ground-based observations first from here on out and get as much data as we possibly can on 3I Atlas?
Well, 3I is also in the plane of the solar system, well, more or less. It's within 5 degrees of the plane of the solar system. It's a so-called retrograde object, so it's going through opposite to the sense of all the planets in terms of which way it's moving, but it's very near the plane, and that's actually good for observations. And it's going to get very close to the sun well, not very close in a distance sense, but as seen from the Earth, it's going to get very close to the sun around the time of its perihelion. It gets close to the sun about a week before the perihelion. Perihelion is October 29th of this year. And yes, with comets, that's when you expect things to happen. That's when you expect the most observation, the most flares or jets. Borisov actually threw off a fragment just after its perihelion. It was a much smaller fragment, but it actually, they could see it separating off. And that could 3I do something like this? Of course, we just don't know. But comets are like cats; they do what they want and they have tails. One answer, the answer to any observational problem in astronomy is always more. Right? You always want more data, more frequencies, more observations, higher resolution. You always want more, but we don't have infinite resources, and it's useful to say, well, these observations would be very useful to have. These sorts of things would be very, very useful to have. Spectra, for example, very useful to have. And observations nearest to perihelion passage would be very useful to have. I'm not 100% sure about the crust idea. I've seen that. I forget which paper it was in. These objects will be in some sense meteoritically gardened, sort of like the moon is, because meteorites will hit them. Interstellar meteorites that hit them. We actually have very little knowledge about what the flux of interstellar meteorites is. We don't know when it was last hit by anything, even statistically, I don't think we have a good handle on that. Of course, it could have been hit yesterday, but we don't know, right? So maybe the crust idea would work, or maybe it would be sort of like the moon, where you have some sort of just mixture of stuff and it's not crust-like, or maybe it's, if you look at all the asteroid surfaces we've looked at have been pretty different from each other. So I would expect surprises.
And you mentioned Borisov throwing off a fragment. I imagine that's on its way out too, along with Borisov. But the idea of a comet leaving a tail. We go out and we see the Perseid meteor shower and things like that, which are, a number of those are basically the tails, the past pathways of comets. Sometimes we even know which comet it was, and it's still, doing its thing. Will there be anything that we can study that this thing leaves behind in its trail as it outgasses further?
Well, I think yes. Now, the meteor showers you were talking about are all because those are repeating comets. They have come through the solar system more than once, and they leave debris. And basically you have sort of three kinds of debris coming off, or stuff coming off. You have the gas, so it has ice on the surface, and so water sublimates, and you have water vapor going off. You have dry ice, carbon dioxide, or maybe you have carbon monoxide, same thing going on. These things go out. The sun's UV photoionizes them, and they turn into a plasma, and that's the typically straight tail you see from comets. And a lot of times that's the biggest and brightest tail. And so a lot of times when you see a picture of a comet, there's this long straight tail. That's the plasma tail. All right, that is gas, and if you happen to fly through it, and we will get to that, if you happen to fly through it, you could see that gas, and you could see the magnetic fields and so on. You're not going to see that as a meteor shower. It's because it's molecules, or ions, single atom ions. And back in the days of Halley's Comet, people said, oh my goodness, there's phosgene and other poisonous things. We'll all be asphyxiated when we fly through the comet. Well, no, through the comet's tail. Well, no, it's actually a very, very good vacuum. It's just over a large scale, you can see it. And then there is the small stuff, the dust. So these are grains. I mean, they're about the size of cigarette ash dust. I mean, maybe nowadays not a lot of people haven't seen that, but very thin ash or dust of some sort, the sort of dust you might find on top of your counters or something, or behind the clock or something like that. Very thin dust. And that is actually affected by solar radiation pressure. And so that goes away from the orbit. And so that's typically a curved tail. And I believe are seeing both of those from Atlas right now, 3i Atlas. Now, I'm not an observational guy. I haven't been taking these observations, but that's what I hear. And also some coloring in it. That's also very interesting. And then there is the larger stuff. If you imagine just sort of you're heating up ice, water ice or CO2, whatever, and it has jets coming up. Well, if there are pebbles or rocks or whatever around that, they can also, and the attraction of the gravity is very low, so they can also be thrust off and you lose them. The comet loses them. And those tend to stay in the orbital trajectory of the comet. Those get spread in mean anomaly. They have very low velocities going off because they're heavy, and they're not very affected by radiation pressure from the sun or anything else like that. And so they just sort of drift along. And over time, those will build up, and that's what causes we think that's what causes most of the meteor showers. I mean, there might be other objects that are a little bigger that get pushed off to boulders or whatever. And so you might have the occasional large meteor, but that's basically the idea there. We don't expect to see that from 3i. However, we do expect to see the dust tail, the curved dust tail. But we are seeing, there's pictures, I've seen some today from like yesterday or so. This is, it's growing. The tail is growing. It's like 2 arc minutes long, I think, right now. The dust the dust tail and the plasma tail are there. They will likely grow. We, of course, can't really predict very well how much they will grow, but that's something we want to observe. The comet showers will not happen. And as it happens, it is very probable that 3i Atlas is leaving stuff behind it as it's traveling, and maybe stuff in front of it of pebble size and larger. The trouble is, we're not going to pass through the orbit in time. The Earth won't pass through, or near the orbit. Mars, as it happens, Mars just passed through where 3i Atlas is going to be about a week ago or something. It's not going to pass through it again for a whole Martian year. And by that time, whatever 3i left behind is just going to be long gone. However, that doesn't mean that all is lost, because 3i could have been, well, I mentioned it might be hit by meteors, interstellar meteors. That could have been going on for a long time. It could have been having stuff thrown off, probably not by heating, but by meteor hits over, billions of years. And so it should be, in fact, I think, surrounded by a cloud of debris. We know very little about this process right now, so we don't know the densities and all like that. but it means that it is possible that we will have meteor showers on either Mars or the Earth, or you could see them possibly hitting the moon if they're large enough, that will come about. And for the Earth, it'll be in December. This is actually all in the paper. And maybe the Mars rovers could see them. I don't know if they're planning to observe, but maybe they could see them. They would appear to, in the usual meteor shower fashion, they would appear to come from a certain radiant. We know where that radiant is. It's 19 hours minus 19 degrees declination. It's the place where 3I appeared to come from. And so if you're on the Earth, my guess would be the rate would be very low. So it's not like you'd see one a minute or even necessarily more than one a night. But, here's a case where amateur meteor observers, I think, will have an opportunity to do things because they could go to Mars, obviously, but they could go to Earth, places on Earth, and say, okay, I want to look for these meteors and see if I see them. And even if only one or two were detected, I mean, again, these arguments are going to be statistical. If you see one thing that kind of sort of comes from the radiant, that doesn't prove anything. But if you see multiple ones that are coming from the same radiant, then yes, you could say those are coming from 3I. And, I think amateurs and also the professionals who are operating the cameras that, like the full sky cameras that look at the sky every night I have no idea what the chances are. I really don't. Maybe it's near zero. Maybe it'll be obvious and, a lot of people see it, but I have a feeling it'll be a sort of occasional thing. But I think that's one of the things that the ground observers can do. Would this be a good time to talk about the general? Let's talk about what we can do in space.
Let's transition to space and a spacecraft being in the right position to end up in that cloud that 3I Atlas leaves behind and use whatever instruments it can to take a look.
We are unlucky for the Earth. The Earth happens to be in the wrong side of the solar system. It's just, there's nothing we can do about that. It just is, It's just, like I said, if 3I had come through 6 months before or after, we'd been in a really good position. It isn't, and we aren't. However, we are also lucky in that there are a number of spacecraft that are on the right side of the solar system, so to speak, the 3I side of the solar system. And that is luck. I mean, we have all the spacecraft at Mars. We have the JUICE spacecraft that just had a gravity assist at Jupiter on the 31st of August. Or it's not Jupiter, on Venus, and is going up, to another gravity assist and eventually going on to Jupiter. We have the Europa Clipper spacecraft. We have the Lucy and Hera spacecraft. We have all these spacecraft out there. We have the Psyche spacecraft that's going to Psyche. All of these spacecraft happen to be on that side of the solar system. That's not a necessity, right? At a different orbital phase, Mars will be near the Earth, near opposition, so on the Earth side of the solar system. I mean, all of these things move around, but as it happens, there's quite a lot of numbers interplanetary spacecraft on that side of the solar system. And so early in July, 3I was discovered on July 1st. By July 2nd, it's moving so fast. By July 2nd, we were quite sure it was interstellar. I mean, that's of course a U.S. holiday period. It's also my birthday, and July 3rd. And it was about the 4th or the 5th before I realized, yes, this is a comet, and it's going to be on the other side of the solar system, and it's opportunities are going to be poor from Earth, but good from spacecraft. And so it just seemed to me, we being my company, Space Initiatives, but also the I4IS Institute. The Institute for Interstellar Studies and the Initiative for Interstellar Studies, which are the US and UK versions, respectively, we should look at this. We should see what the spacecraft can do. And we rapidly concluded that for imaging, the 3 spacecraft were Psyche and the spacecraft around Mars. Well, I say 3. The spacecraft around Mars, of which there are a bunch, and the JUICE mission. JUICE is right now not that close to where 3I is going to be, but it's climbing out of the solar system because of its Venus gravity assist, and it will get there. And Mars will have the closest approach. Psyche had the approach on September 4th. The Mars spacecraft will be closest on October 3rd, and the JUICE will be closest on November 4th. And I started sort of bugging spacecraft people saying, and I wasn't the only one. There were other people who were saying, a lot of people are focusing on Mars because Mars is going to be the closest approach in early October, but you have to make a case. And so I tried to make a case in the paper we wrote that yes, this is probably a thick disk object. If it is a thick disk object, it has these certain characteristics. These are things we should look for, and that justifies using your spacecraft to look for them. And I can tell you that there are a numerous spacecraft team, a number of them have been really working very hard the last few weeks. I mean, the last month and a half or so, to try and do observations of 3I. It is not trivial. It is not, it's not like just saying, oh, I'm on a bus and I'm just riding by the Empire State Building or whatever, and I'm going to take a picture out the window. No, it's not like that at all. It's like I have this very complicated system that, is millions of miles, millions of kilometers away. I can't touch it. I can't fix anything if it breaks. I have to be very careful about using it. And somebody like me comes along and says, yeah, do something different. That is not trivial. That is, I really take off my hat to those people, take my hat off, because it's like they have been working hard. I hope they can all get observations. In some cases, I'm not even sure that they know whether or not they can get observations, but they're certainly trying. And so the periods are, early October and early November and in fact, November 2nd to 25th are the periods when the Mars spacecraft and the JUICE spacecraft, respectively, will be getting their images and other data on 3I, and it'd be very, very good if people on Earth, including the amateur community, tried to take simultaneous observations during that period. Now, I can't, there's many, many people on Earth that have telescopes and stuff, and both professional and amateur, and I can't say, oh, this whether or not what you can do or not. But I know that, I'm sure that some of the amateurs are going to try and take observations of the tail and the like when it's very close to the sun. And I think, they should. And I think anything they can do around that period could be especially useful. And there's actually, of course, two other things that spacecraft will do. And I will sort of do them in the order in which we worked through them. The solar I call them solar probes, but they're solar observatories and solar missions. There's two solar missions, Solar Orbiter and Parker Solar Probe, and then there's a bunch of spacecraft, some in Earth orbit, some in Lagrange points or in other orbits that image the sun. Well, they don't have trouble taking images of things close to the sun because they got the cameras designed to do that. The question is, can they see 3I? And that'll depend on how big it is and how bright it is. Things are looking actually fairly good there, but we think that the recently launched Punch spacecraft array, which is actually in Earth orbit, could probably observe it and probably detect it. They can all observe it. I mean, it'll pass through all of their fields of view. The question is, will they see it? Actually, that's not quite true. It won't pass through the stereo A field of view we found. So stereo A can't even observe it potentially. But is it bright enough to see? Is it big enough to see? And well, we don't know yet. But there's another amateur community that looks at the pictures from these spacecraft, and they will for sure be telling us whether or not they see it or not. I have no doubt about that. But if they need to redouble their efforts, well, they should do that too. And those data will be very useful because those could be day by day. And so it'd be like when we can't see it from Earth, those could be like, here's a day-by-day record saying what's going on. The interplanetary spacecraft stuff will not be day by day. It'll be, they observe it this period for a bit, and then they have to do other things, and they observe it this period for a bit. So it'll be intermittent. So I think that's useful. And then the last thing is, it looks like there's a possibility that Europa Clipper and Hera spacecraft and Lucy spacecraft could fly through the tail of 3I. Now, probably the plasma tail is the best bet there. So they could fly through the plasma tail. They might fly through the dust tail a little bit later because the dust tail will be curved away from the dynamics of it. And they will not fly. No spacecraft is going to fly through the orbit and get the meteor shower tail, if you want to call it that, the neutral tail, some people call it. That 3I is probably leaving behind. We don't have we won't be able to do that because we don't have anything in the right place. But I think it's a good chance that Europa Clipper and probably Hera too, because they're fairly close from each other, right? Just by happenstance, could both see the tail. And there's another case, and that would be the first week of November, probably. Again, hard to predict comet tails. There's another case where, and that's when it's still close to the sun, but any amateurs or whatever who could observe the tail at that time, it'd be very nice to know what's going on. Now, I should say that the tail that people take pictures of is the tail that's visible, but the stuff that comes off, whether it's the plasma or dust tail, doesn't just vanish because we can't see it anymore because it gets too thin to see. It's still, it's still there. It's still going away from the comet. And I suspect that these spacecraft will not go through the visible tail. In other words, the visible tail won't reach out 1 AU. Europa Clipper would be like 1.2 AU away. So I don't think the visible tail is going to get that long. It'd be lovely if it was, but I don't think it will. But that doesn't mean the material won't be there. And so that doesn't mean their plasma won't be there, and their plasma instruments can't see this and say something about what they're seeing there. And that, of course, would be very, very, very nice. Whether they go through the dust tail, we're still trying to figure that out. And that would be also interesting because potentially you could sample it that way. I don't know how realistic that is. I don't know if it's going to happen, but but we've been working hard too. And that's sort of the next thing we're trying to figure out. And they are actually working with some people in Europe, some collaborators in Europe. So we've expanded our team a little bit.
Well, speaking of Europe, happily, we now know by announcement by ESA that Mars Odyssey and ExoMars or Mars Express and ExoMars rather, are going to attempt observations. So this is happening. It's beginning.
Yes, and we do not know about the Hope spacecraft, which is from the Emirates, or the Tianwen-1 spacecraft, which is from China. And I've actually tried to contact people at both of those spacecraft to see if they will observe and to encourage their observations. And unfortunately, I've not heard much of a response. There could be political difficulties there too. I don't want to get into that, but
now regarding tails and two separate tails. Now, in pictures of comets, including many wonderful amateur pictures of comets like Hale-Bopp, you remember that one back in the day? Spectacular. I photographed it myself.
I saw that with my naked eye.
Me too. Yeah, me too. Good one. And it was, I watched it. It was very visible.
In fact, I remember I went to some opera or something down in DC, and I actually saw it near the Kennedy Center with my naked eye. I was astounded. I looked up and there it was,
Yeah, there it was. And I was actually observing it from St. Louis, and it was, obviously St. Louis has a lot of sky glow, but there more so now than it did then. But there it was, and you go out and look at it every night. But I would also go out into dark sky locations and do long exposure photography with it. I actually still have those. One of these days I'll pull those photographs out. But the thing is that sometimes when you see these pictures of these comets in the past, you can visibly see in the photography, if not visually, the two different tails. Mm-hmm. You see the chemical tail curling and then, the dust tail, going off. And this is actually something you can see, but probably not with 3i Atlas.
And that's actually what causes the anti-tails occasionally, where it looks like there's a tail in front of the comet. It's just a projection effect. You're seeing the dust tail, and the angles are such that you're seeing it projected.
That's an interesting distinction to make, because as 3i Atlas is showing us, there's really two types of an anti-tail. There's one where it's preferential heating causing gases to shoot forward, which is what's happening with 3i Atlas, which to me seems like a true anti-tail. And then there's the perspective effect, which isn't really an anti-tail. It's your perspective on how you're viewing it. You're seeing the comet's path is what you're seeing effectively.
Good point. Yes.
So I wanted to make that distinction that there are two types. Comets can do this two ways, and it is not rare for either. Comets do this, and a lot has been made about the anti-tail regarding 3i Atlas, but no, that's not that unusual, right?
I mean, none of the stuff I have seen with 3i Atlas, except for the chemical stuff to some degree, I regard as unusual. Its action as a comet seems, and I'm not, that is not my direct area of expertise, right? But I have been involved with this for a long time, and it just seems like really a pretty commonplace comet, as did the 2i Borisov. Again, I'm not talking about the chemistry. I'm just talking about, they both had tails. They both, when they became active, all that kind of stuff seemed pretty normal,
to me too. I was like, well, it's becoming active right about the time it should start, releasing CO2 and these things that they do. But the chemistry, that's interesting because now we're getting a profile of chemistry. You know, you can compare it to objects ostensibly of different ages. Oumuamua and Borisov were both of radically different ages.
Yeah, we think one eye was pretty young, and of course we never got a spectra from one eye, a real spectra. We don't know anything about what chemicals it had. I mean, we can guess, but
And the only thing I ever heard it was reddened, which is you expect that from the interstellar medium.
yeah, I mean that's kind of a spectra, but it's not like it tells you, you know, reddened doesn't mean oh it's made out of this. It just means well it's red.
No, it just means interstellar medium. A lot of cosmic rays out there. Now, Marshall, the chemistry question, though, is perhaps the most interesting one here because it is doing a few things that are a little bit weird chemical-wise, and it may simply be a product of age or in an environment it passed through or did something to it, you know, to make it look a little bit strange. Low CO2, low iron, that one's really puzzling, and things like that. What can we learn about that using the spacecraft and ground-based observations to get a characterization of the object?
Well, on the spacecraft side, some of the instruments we're talking about on both the Mars spacecraft and the DEW spacecraft can look into the UV, and so they can see the areas where the spectral lines where, you know, like you mentioned the lack of iron and the presence of nickel. Now, I should say that that is not an indication necessarily that of this iron peak diminishment that I was talking about, because, well, for one thing, nickel is also an iron peak element, so you expect them both to be diminished. But also we suspect that the chemistry here is rather different. Although I have to say the notion, I mean, some of the earlier comets, the one from 65, for example, got so close to the sun that they had iron and whatnot spectra simply because it was ionized. The iron was, you know, melted and vaporized, and you had vaporized iron, and so you had spectral lines from vaporized iron. That's pretty hot. And it was a real surprise, I think, to the community to find that, no, comets can do iron and nickel, and the nickel seems more prevalent, even way out, you know, multiple AU from the sun where it's not hot. There's just no way the iron on the comet is vaporizing. I mean, on 3I right now, you know, or any time during its path through the sun, it doesn't come close enough. It comes a little closer than Mars, but, you know, Mars is pretty cold. I regard all that as is something of a mystery. There's some the idea that I guess you could say the consensus is that there's some element, some compound, some molecular compound that is both volatile and has nickel in it, and maybe also volatile and has iron in it. And these things are being vaporized on the comet, and then the solar UV flux disassociates the nickel or the iron, and you see it. And that sounds very plausible, but you know, I don't have a really good feeling that we really understand it that well, in the sense of why are those compounds on the surface? What's causing this really? Is there something deeper? Or is this just a happenstance? But that's not going to, unfortunately, because I was at one point hoping it would, but it's not going to answer the question of like, well, is this an early alpha element dominated comet? Because if it's from the thick disk, it should be alpha element dominated. Now, alpha elements are like carbon and oxygen, and those are common. I mean, you have water, you have CO, and you have CO2. And I actually think that the better chemistry thing is you shouldn't have super volatiles. You shouldn't have things that, because in the models, the cosmic noon era, star formation should have happened in very warm regions. They should have had lots of, you know, very high star formation rate, all very close together. Something like I think it's called the Tarantella Nebula in the Magellanic Clouds, except more so, and so much more violent than the Orion Nebula star formation region that I'm pretty sure everybody has seen at night, and thus much hotter. Now, there's a paper that claims it might have been as hot as 300 Kelvin, i.e., above the room temperature. I mean, something like room temperature, above the melting point of water, and well above the vaporization point of water. I think that can be ruled out. I think the temperature, what we're seeing is lots of CO2. I mean, lots of CO2. Not too much water, but some water. Not less CO. So that's surprising. So that right there says it came from a warm environment. It either came from early in some solar system, I mean, some closer to the sun, a stellar source of some early solar system, or it came from a warm star formation environment. And since we predicted a warm star formation environment, I kind of view that as, as sort of a win for our side, you might say. But it would have been about 100K, something like 100K. So that's certainly warmer than deep space, but it's not that hot. And so you get CO, but not CO2. CO, carbon monoxide, CO, is very volatile. It goes off first. And I don't see much sign of that. Now, as I was saying earlier, this is sort of science by press release. All of this could be changed by once the papers come out and the papers analyzing the papers come out and everything is digested and all like that. But that is just the feeling I have right now. I think we need more, though, to be sure. And I'm hoping that we will get that. When something is passing behind the sun, every telescope system has sort of the minimum elongation it can do. And once you get inside that zone, I mean, for the Hubble, it's 55 degrees one way, plus minus. That's very wide. Hubble basically will not be able to take more observations, I believe, until December of the Hubble Space Telescope of 3I. And Webb, its zone of avoidance started in August and will go into late December. So we're kind of up to the Earth telescopes and the sky telescopes. And I haven't heard anything from ALMA yet. ALMA can see some of these molecular lines up in the hundreds of gigahertz region. I'm really looking forward to seeing what ALMA says about this. I'm sure somebody's got plans to use ALMA. ALMA can actually observe, I believe, down to 15 degrees elevation from the separation from the sun, and so that means it'll only have about a 10 days, 2 weeks period where it can't observe 3I. But some of the telescopes on the interplanetary missions, especially JUICE and some of the Mars missions, including the Mars MAVEN and the HOPE spacecraft, have the right kind of instruments, I think, that they could say something about what's going on. And there's another chemical that I really hope somebody detects and we can say something about, and that's PAH, or polycyclic aromatic hydrocarbons. And the PAHs are both hard to pronounce for me, and one of these things that they're kind of really mysterious. I mean, they actually were detected in space spectra in the infrared by spectral lines that nobody could explain. And if you know what a benzene ring is, it's carbon in a ring. And PAHs are basically benzene rings stuck together to form larger things. So you have lots of benzene rings. And so they have different modes of, the rings can squish like this, or the ring is flat, things can pop up and down out of the ring. And those are all those modes. I mean, it's very much like a weird musical instrument, like sort of a drum made out of metal rings. All these modes of excitation, just like modes in a drum, are effectively sounds, except in the with infrared light, it is a spectral line, but it's this. I mean, it's the same thing. It's the same basic physics in a sense. You're seeing these spectral lines from PAHs. For a long time, we didn't know what was causing it. It seemed very mysterious. These lines nobody knew anything about. Typically up in the so higher infrared, all the way up to 13 microns, I think. But now we understand a good deal more, and it seems like a lot of the carbon in the universe is in the form of these PAHs. That doesn't mean that, if you go to Mars, you're going to find PAHs on the surface or whatever. No, I'm talking about the carbon in the universe, which is mostly in gaseous form out in space. There's a lot of this stuff out in space, and it's very, very common. And it's also present in, like planetesimals and star formation, and the different star formations do things to the PAH. They change. I mean, basically the temperature has a control on the size of the particles. And at one point I thought that there's papers that claim that the radiation environment can also change the size of the particle. I think that's actually probably not true. I think that I've been in contact with some experts in this, and it's really just the temperature. But that would be even if you don't believe the thick disk hypothesis, it would be very nice to know what temperature this object came from. And I think we're kind of getting that. And I think if we find PAH emissions, which again, I think ALMA could also see, chance of getting a handle on that. And one of the things I've been thinking about a lot is
polycyclic aromatic hydrocarbons. Now, these are interesting chemicals, and given that we're seeing them abundantly, we also see them in meteorites. We see them in, solar system comets and things like that. But these are also linked to potentially the origin of life, because we're dealing with the chemistry of carbon here. Now, what would a profile of that tell us from another star system, perhaps, especially if it's ancient, of what the conditions might have been like? And maybe, I mean, could the universe teem with life if there are PAHs everywhere?
Well, PAHs, of course, were really mysterious for a long time, and in fact, are still pretty mysterious. They were detected, they were first, just as helium was first discovered when somebody saw helium spectral lines in a solar eclipse, people saw weird, unexpected spectral lines in infrared data, and they didn't know where it was coming from. And for a long time, decades, it seemed, nobody really could figure out what's coming from. And now we think it's all PAHs. And let me just say, it's just a little bit about what that is. Most people who've taken chemistry know what a benzene ring is. It's a ring of carbon atoms around it. So it's 6 or something like that carbon atoms, and it's just a ring. A PAH seems to be just many benzene rings connected together to form kind of a carpet. And these rings have, this carpet has modes in it. So it has a mode where the rings squish together, and it has other modes, and it has a mode where the one of the side of the ring is popping up and down. And just like in a drum, if you strike a drum, the surface moves, and that causes sound waves. Particularly if a ultraviolet photon from like the sun or some other star strikes a PAH, it vibrates, and that vibration, that sound, if you would, is not sound in hearing, it's sound electromagnetically, and that's infrared light, and we can see that. And I have not seen a claim of detection of PAHs from 3I, but 3AHs PAHs are ubiquitous in the universe. They seem to be it seems like most of the carbon in the universe is in gases in deep space in the form of PAHs. And these are little tiny blobs, if you would, of carbon material, pure carbon. And they can have other things like nitrogen and so on sort of stuck in there too. And that changes the spectrum so it can be detected. And they're present in star formation regions. And so they should be present on what we think is a planetesimal-like body, like 3I, and they have been detected in comets. They have been detected in some of the asteroid samples sent back to Earth. I don't think they've been detected on the moon, but the moon has a fairly harsh environment, the surface of the moon. The PAHs can tell you something about the temperature of the environment that the object formed in. And that is, I think, really sort of why I really hope that we can find PAH emissions from 3I. We generally think of comets as forming deep in deep space, and just, so the temperature they were formed at was basically like 3 degrees Kelvin, or, something like that. Of course, for something from cosmic noon, it'd be more like 6 degrees Kelvin. So it's not that much warmer, a little bit warmer. A redshift of 2, after all, or the equivalent of a redshift of 2. I think that the current data is sort of indicating that 3I was formed at a temperature of about 100 Kelvin, and that's fairly warm for star formation. And so that actually is somewhat consistent with a formation, in early cosmic noon. Now, PAHs could help confirm that, the discovery of PAHs. So that's why I hope they find it. And also, the alternative there would be, well, what if you just were like in a normal thin disk stellar system and you just happen to be closer to, this is a piece of something that formed closer to the star. Because after all, we know that some stuff formed fairly close to the sun, and presumably that happens with other solar systems, other stellar systems. And I think that the chemical relationships we find could help to resolve that. And we shall see. I mean, I think this is a very exciting time here, and I really hope people find PAHs from this, and I really hope that we can then take that and use that to say something about the formation conditions of this object.
Now, the future. What can we do to be ready since we have the Vera Rubin telescope coming online that will probably discover many more of these objects? What can we do to position something out there to catch the next three-eye atlas when it comes through, an object of great interest, and be ready and go and sit there and let it intercept us?
Well, so Ian Fleming in his Goldfinger character and novel said that once is happenstance, twice is an accident, three times is enemy action. And now this is not enemy action, but I think with one eye, a lot of people thought, well, is this going to happen a lot? Some people thought it was going to happen a lot, like immediately we'd be finding more, and well, we haven't really, one eyes. But with three of them, yes, we're going to find a lot. I think that's clear. I think there's no question of that. We're going to be finding a lot. With Rubin and the other surveys, Rubin in the southern hemisphere and surveys, improvement of the surveys in the northern hemisphere, we're going to find a lot of these objects. And yes, we do need to think about how we deal with it. And I've actually been thinking a lot about that because it's apparent to me. I mean, for example, you come out of the blue and you go to a spacecraft operator who's running a, billion-dollar spacecraft maybe, and you say, could you please do this, like your Oliver Twist or something? Can we have some more? Could you do something you're not intending to do? That needs some sort of structure, I think. That needs like the IAU or I don't know, I haven't thought that through that well, but some sort of structure where we say, these are the kind of objects we're likely to be seeing. Here's the kind of observations we would likely be take. Here's the priority we can give to them. I thought, for example, that it was just the simple fact is that 3i is going to be the opposite side of the sun. So spacecraft observations have to take that load. You can't just, otherwise, and it's only going to come through once. All of these objects are only going to come through once. That's really clear. We got one shot. Any data we don't collect will never be collected. There's no replacement there. There's no others going to come by in so many years or anything like that. They've all been different so far. And, that may continue for a while. And also, by the way, so I've been thinking a lot about what 3i is teaching us in a sort of larger sense about dealing with new interstellar objects. I mean, Ian Fleming had his Goldfinger character say, once is a happenstance, twice is an accident, three times, well, he said enemy action, but three times is a pattern. We're gonna see more of these. I think that's clear. After one eye, some people thought there'd be lots of one eyes coming by, and some people thought, well, including myself, well, maybe not so many. We haven't actually seen another one, but with three of these objects, we're going to see a lot. Now, I got to make the point, sort of forcefully, that we have one chance with any of these. We have one chance with 3i. It's going to fly through the solar system. We can't stop it. It's going to go through. Once it leaves, well, potentially in the far, far future, we could send a spacecraft out there, like when we start traveling to Proxima Centauri or something. But for our lifetimes, we will probably not be able to get to this object. So that's it. I mean, we will get what we get, and that's all we're going to get. And so the real thing there is, we got to get the data we can. But on the other hand, we got get as much data as we can. But on the other hand, it's asking a lot of a spacecraft operator to just come in out of the blue and say, well, here's this thing. You need to observe it. Yes, you particularly need to observe it because you just happen to be in the right place at the right time. That's asking a lot. And I think it's really a testament that, people like me who are just sort of basically coming out of the blue, although I knew a number of these people already, but still, it's like, the UN didn't pass any resolutions. The Congress didn't pass any resolutions. The acting head of NASA didn't say, oh, we have to do this. Nothing like that. It's just people on the ground, so to speak. And I wasn't the only one by any measure. We're saying this needs to be done. And people started listening to it. And it would be good if we had some mechanism or some structure for that. So in other words, for example, suppose something like 3i comes by and it's on the Earth side of the solar system. Well, do we need to engage all the interplanetary spacecraft? Some, is it, can we rank observations like this? These would be nice to have, and these are essential. And when I say we here, well, who? just the community? Just, yeah, we're going to do this on YouTube or Facebook or something, or probably not. On the other hand, I would hate to say, well, it's got to go be reserved to the result, deferred to the IAU and the IAU vote on it. I mean, that'll take a while, and that may not work that well. I don't know. I mean, actually, the next IAU meeting is coming up, and it'll be interesting to have that discussion there. Like, how do you set sort of priorities and stuff? And I do know it's useful to have scientists say and write papers saying these observations would be good because they could solve these problems. Because I do know that I do think that the spacecraft operators find that very useful. That it's like they can say to their, why are you doing this? Is you just trying to, like, score brownie points or get publicity or something? It's like, no, these scientists said that this is a good thing to do. And so, I encourage people to write papers on this. We got 3 months or 2 months, really 2 months, get out there and write. And tell, if you feel like I'm not writing it right, write a different paper. And, I think the more the merrier there, because again, whatever we get is what we're going to have. And I actually think that people are getting this, and there will be a lot of data from this. I think you're going to have a lot of data from the Earth. You're going to have a lot of data from near-Earth spacecraft, and you're going to have data from the interplanetary spacecraft. And so, a lot of people have been surprised by this and put in a lot of work. And my team, we worked on this pretty intensely for over 6 weeks. And that's a lot to just have something come in out of nowhere. And one, by the way, for which there's no funding. So, it's just like, we got to do this, not, this is something we just have to do, and then go do it. So I'm really looking forward to seeing all this data that's going to be coming. And I'm really glad that I could play some small part in helping it to happen.
I have a sneaking suspicion that this caught the attention of a whole lot of astronomers. It's hard to ignore it because it's an interesting, in the very best case scenario, it is a fossil, from an earlier period in the universe. Worst case scenario, we figure out what it's not, or what, anything like that. And we learn more about interstellar objects. It's sort of a brave new world of study, because I think we're going to see a lot of these at this point, as you mentioned with Ian Fleming. And I wish you luck, and I hopefully you'll come back as we further explore interstellar objects. Thanks, Marshall.
Well, thank you very much. Thank you. Thank you for the time. And yes, it's exciting times here. I can't wait. It's like a Christmas present, right? That's coming early. I can't wait till December to see what we've got.
Absolutely. And everybody, there is a link to Marshall and colleagues' paper in the description below. Daryl Seligman, welcome back to the program.
Thank you for having me, John.
Daryl, Chemical Mysteries with 3i Atlas. It is a weird one, and it turned green since we last spoke. And the chemistry seems unclear, even though comets turning green is actually fairly normal. But this one seems to be doing it a different way. Do you know anything about that?
Yeah, I think the turning green thing, like you said, that is something that's typically seen in comets every now and then. So that was, I think, a little less surprising than people made it out to be. But I think the one there's been several, I know that you're kind of alluding to this, but there have been several different compositional things that were maybe surprising. The most remarkable, I think, were those JWST observations. So that CO2 detection.
Got a lot of it, but I always try to keep in mind that this is from another star system. That's right. Under conditions that we don't know what the conditions were that this thing formed in. So maybe there was more available CO2 in that star system or something like that. But what throws me for a loop, honestly, is the nickel to iron ratio stuff. Where is the iron? But I think we're going to find the iron, and it might have been masked. What are your thoughts on that?
Yeah, so the nickel to iron ratio stuff that is somewhat mysterious. I mean, if we just take a step back for a minute, you might remember that back in either 2020 or 2021, it took a while. It might have been 2021 that it was published, but there was a paper published in Nature where they actually detected something very similar in 2I Borisov. So it is not actually unprecedented to see that. I'm just going to look it up real quick. I think it was 2021. Yeah, it was 2021. I'll send you the link to the paper, but it was atomic nickel in the coma of interstellar comet 2I Borisov. So I think this kind of puzzled everybody. And I'd say that there hasn't been, I don't know, maybe there hasn't been that much attention to that paper even back a couple of years ago. But I think it was primarily because people didn't really know what to make of it. And then the fact that 3I Atlas, we're now seeing atomic nickel, or, you know, there is the nickel to iron ratio is weird, but we're seeing that again. That seems to be a common theme actually in interstellar comets.
Yeah, and I'll go out on a limb and start wondering about the nature of the supernova that populated that. Is there something we don't quite know about nickel versus iron production in supernovae, or can iron be depleted somehow in the interstellar medium? You know, because this thing's been floating around out there for billions of years, apparently, in the ISM. What's that do to an object? You know, there's all sorts of questions. What is the latest now, as of today, with 3I Atlas? What do you know, perhaps, about the Mars observations?
Right. So the Mars observations, those are, yeah, I'm glad that we're get there. And I do want to circle back to the weird composition, because that is, there are lots of interesting, I think one thing that maybe has gotten lost and it's worth focusing on is what possible natural interpretations there are for the iron to nickel and the CO2. The Mars observations right now, that's pretty exciting. The unfortunate thing is that this government shutdown happened just within a couple weeks of 3I Atlas's closest approach to Mars.
It's outright maddening.
I don't know. Ross was texting me about it. Yeah, exactly. Maddening, right? I want to caveat this with saying that I am not part of any of those Mars spacecraft missions. So I want to be really careful to not speak for any of the missions or speak as if I'm one of the people making decisions for any of those missions, because that's kind of, all of that is like well above my pay grade. So I don't want to speak for any of the specific Mars missions, but, you know, we have this really exciting opportunity to look at 3I Atlas up close. You know, we don't get to see it. We can't look at it from the Earth right now. And it's very maddening, as you said, because when a comet gets closest to the sun, so at perihelion is when that's when most of the fireworks go off. So that's when you really want to see, because that's when you have the best chance of seeing not only the most activity, that's when you get the reason it's so important to look when it's close to the sun is that's when you get the most holistic or realistic view of what the nucleus is. Because when you look at stuff really far out, a lot of the volatile species that you'd expect to be there could very easily be there, but it's not warm enough for them to be active. A measurement of a hyperbolic, for example, like CO, really, really far away, that is very interesting. When the comet is really far away, that's interesting, but it also isn't necessarily telling you about that's not an unbiased view of the composition of the nucleus, because water isn't even supposed to be active. It's not even warm enough for water to be active when you're past 4 AU, say. So it's really, right now is when you really want to get information on 3I Atlas. We already knew that we weren't going to be able to observe 3I Atlas from Earth around now, back when we discovered it, because we could map out where it was going to be. So as maddening as that is with the apparition, we had months to kind of get over that, right? So we were upset about that, but we kind of figured out we weren't going to be able to look at it from Earth during this really important time going on right now. But I think a lot of us were banking on the Mars spacecraft being able to observe it. And the good news, I think you'll be happy to hear, is that as far as I know, with the caveat that I don't want to speak for any of the missions, as far as I know, every single space mission which was planning on observing 3I Atlas during this time, which is basically every single one which could have, they're still moving forward with those observations. So all of those observations are still happening. It's just that because of the government shutdown, they're not able to like publicly release any of the observations or any of the data. So they can't even, for example, if you are, it's kind of, I mean, there's pros and cons of working at NASA, but if you are, I am not officially a government employee right now as a Michigan State professor, but there are a lot of scientists, especially a lot of ones that work on missions or parts of missions. They work at NASA or at Goddard or JPL or something like that. If you're in one of those camps, then just to submit a paper, you might hear my cats freaking out in the background.
Makes for interesting listening.
Yeah, we just got a kitten, and my kitten is annoys his older brothers all the time. So that's what that was. Sorry if you could hear that. Where was I? Right. Yeah. So if you so there are lots of great things about working at NASA, but one thing is that any paper if you're going to be a co-author of a paper, you have to get that paper totally cleared and okayed by different offices, depending on exactly what part of NASA you work at. So I think right now with the government shutdown, they don't even have the ability to get there, even if they had all of the observations that they took with the Mars missions analyzed and ready to go, ready for public release. They don't even have the ability to submit the findings to a journal, which is certainly I'm imagining, I don't want to speak for any of the scientists who are on those missions, but kind of like empathetic to them right now, because I imagine that it's very, very frustrating.
It is fun to imagine, though, because one of the observations will be done by the venerable Mars Reconnaissance Orbiter, which is one of my favorite spacecraft ever. And it is old now, but still unbelievably capable.
Right.
And that should, my sense is, allow us to sort of constrain the actual size of the object and finally lay that to rest. Do you think that that's the case, or do you think that the Hubble Space Telescope observations basically nailed it as far as size, nucleus size?
Yeah. Okay. So I think those Hubble Space Telescope's observations were very enlightening. So it was somewhat surprising that we didn't get a better size constraint from the HST observations. But remember, because basically the way that Dave Jewett sets up those HST observations of a comet, it's like basically very fine-tuned to nail the size. So one of the most important things to measure for a comet is the size of the nucleus. And as you know, it's very difficult to measure the size of a nucleus of a comet when all you're seeing is Coma, right? It's much easier to get the size of an asteroid. So Dave is very good at setting up the observations with HST such that they're able to get a nucleus size. It's very tricky to do it, but the way you do it is basically you get a sufficiently sensitive image such that you can take the Coma and actually remove the Coma from the image and see a little bit of excess light in the center from the nucleus. And that's how you then constrain, say, like an upper limit on the size, or even a detection of what the limit is. So for example, when Borisov came through, Dave was able to do that with HST and was able to actually measure the size of the nucleus with some uncertainty, of course, but very good measurement. And then with 3i Atlas, the issue was something went wrong with HST. So I think it was some gyroscope issue. I'm not sure exactly what happened, but they ended up executing significantly less time than the observations were supposed to. So I think I'll have to go and double check the numbers, but I think it was like they only ended up with something like 10 minutes worth of HST observations. So we should be kind of thankful that it worked as well as it did, honestly, based on the difficulty with the situation that was going on. The HST observations provided they didn't detect. So in those observations, they did not detect the nucleus. So that basically gives you an upper limit on how big it could have been. And I think that exact upper limit that Dave calculated was something like 2.3 kilometers. I think it's that. Don't quote. Well, I guess you have to quote me on that, but I can look it up if you want. But it was that, but it's very possible that it's significantly less than that as well, because they didn't actually detect it. So more information about the nucleus would be very welcome at this point, because the size of the nucleus tells you so much about things like the formation of the object, possible formation mechanisms for the object, and subsequent evolution. Like how, if it was, for example, if it lived in an environment like the asteroid belt today, you'd expect that things that are pretty big typically will end up having a lot of impacts. And then you get some of those collisions can actually fragment, and you'd actually expect there to be a lot more smaller objects, for example. So it is really important to get the nucleus size. I don't want to say too much about, while I agree with you, John, about how exciting it is with some of these Mars missions, the possibly getting the nucleus size, I don't want to speculate too much on the success that they're going to have with doing that, because a lot of that are kind of, well, obviously we're going to have to wait for some of the results, which is frustrating, but it seems like, I think optimistically we can hope for that, but realistically we also have to kind of remember that all of these space missions, which are hoping to observe or planning on or currently observing through Atlas, none of them were meant to observe to take observations of an interstellar comet. So a lot of those, I mean, for some of the things at Mars right now, I mean, some of those cameras are like 20 plus years old. So it's amazing that it's amazing how good of a condition they're in and that they're still working, but they certainly weren't designed for this. So I think it's going to actually, I think we should have some, I don't know if respect is the right word, but have some respect for the teams of people who have to analyze this data, because it's not as simple as it sounds, right? Because they're trying to get observations of a comet that is still like, while it's close to Mars in like solar system context, in terms of the actual instruments that exist on things like the rovers, the comet is way further away than things that they're meant to be observing or taking any measurements of. So we should be grateful for any information that we get, but with the understanding that these mission teams are working very hard to try to interpret and reduce, analyze, and interpret observations of this interstellar comet that these instruments were not designed to take, right?
Yeah, but it's still amazing because they thought of something that they could do, and we'll get what we get from it. But it's still pretty amazing because MRO also was not designed to take a picture of another Mars craft parachuting down and landing.
That's right.
So I have a lot of respect for those people, and I'll bet they'll tease stuff out of it that we may not have expected. Now, any word from ESA and their probes?
So right now, there is close to nothing being circulated, right? Like, as you know, I think we're in a very similar kind of situation where maybe it's not quite like a government shutdown that's affecting things, but a lot of times when NASA or US assets go down, that also affects other countries significantly, because a lot of times the US have some participation. Like a lot of these ESA missions have things like international, what do they call them? They're like international science programs. So you can have like basically a whole subset of the team are American or some other countries. So NASA will be heavily involved with some of these other countries' missions, even if it's not the primary funder. So the government shutdown really bleeds over into the whole space asset global space asset ecosystem, if that makes sense. So I think it's really, really detrimental. But right now, I think we can be excited about like you said, we could be very excited about the results that have to be coming in the next couple of weeks, but there's nothing super exciting to share just yet.
Yeah, but I'm content with the idea that the observations are still being made.
Right.
Data is being taken. It's just the interpretation and getting it out there and all that's held up. But the spacecraft did observe, so we will get something.
Absolutely.
No matter what. And I do also, even though none of these spacecraft were designed for this, we also have an array of them. I believe there's 4 spacecraft looking at it, and they all have different instrumentation. So that'll be interesting. But back to the chemistry. Let me ask you my usual off-the-wall question. When a solar system comet comes cooking through and it comes to a perihelion much closer to the sun, say it evaporates, does that actually tell you more about the comet if the whole thing just sort of disintegrates going that close to the sun? Just in general about comets.
Wait, so let me make sure I answer the right question. Are you saying in general, just any comet, not just typically an
any comet, anything that any dirty snowball that comes in, is it better observationally for it to get as close to the sun as possible to characterize its chemistry?
I see what you're saying. That's a good question. So I think generically the answer is yes, with some caveats. So I think for most cases, yes. And the reason is that basically what I was trying to get at before about getting the most holistic view of the comet nucleus. So let's take a step back. When a comet gets close to the sun, right? It starts the surface, you're getting more irradiation from the sun. That means more solar photons hitting it. It's heating up and more ice is turning into gas and sublimating. What ends up happening is that the closer you are to the sun, the warmer it'll be, and you'll have different types of ices starting to sublimate. So, for example, when you're really far away from the sun, when you're out past like 4 astronomical units, like 4 times the Earth-Sun distance, you're not even able to see water, really. Like, water isn't really expected to be vigorously sublimating because it's not warm enough for that. So the closer you are to the sun, the warmer you are, and then the more kind of, it's kind of like once you get warm enough for a certain ice to sublimate, you're always above that temperature. So that ice always, if it's there, if it's still in the nucleus of the comet, it should still be going. So you can't get too warm, but you can't, if you are too cold for a certain ice to be active, then it'll just shut off. Fundamentally, the most informative thing you can learn about a comet is what different ices there are, but most importantly, what the ratios of those ices to each other are. So, for example, how much water there is compared to CO2. So just the CO2 detection is, while the JWST CO2 detection is it's like a great scientific achievement. It's an amazing discovery. What's really powerful is the CO2 to water ratio. So how much CO2 there is compared to water. So in that regard, the closer that you get to the sun, absolutely the better it is for interpreting what the composition of any comet is, because that is real. Those ratios are kind of what tell you the fundamental things about that comet. In some sense, those ratios are more fundamental to the nucleus of the comet than any single species detection by itself. And those ratios, because they are fundamental to the comet, they also tell you things like where the comet could have formed. So, for example, if you measure, this is just an example, but if you measure that a comet has a really high amount of water compared to how much CO2 it has, when you're warm enough for all of those species to be active, then you know that, if there was more CO2 there, it would be actively sublimating the way that the water is. That's telling you really fundamentally that nucleus of the comet has more water in it than CO2. And then that tells you that it probably formed in the kind of closer regions in the solar system, for example, because if you form at a closer region, potentially you could form where water freezes out, but CO2 is not frozen out. Does that make sense?
Yes, it does. It just occurred to me, it's really interesting time for comets because it's not just the 3I Atlas coming through. There's also 2 solar system comets.
Right. That's
that
right.
are binocular. They're binocular level detectable at this point, all at the same time.
Yeah, it's amazing. Have you been able to see any of those?
Not yet. I think it's going to take me a few more days to spot them at dusk, or spot 1 or 2 of them, whatever I can do at dusk. But I am going to try with 10 by 50 binoculars. And if I can get an actual position, I'll get a telescope up. But I am going to try to pick them up with big binoculars because, but the thing is, Daryl, it's ruined for me because I saw visually and photographically and everything else Hale-Bopp.
Oh, right.
And nothing has ever gotten quite that good. So I'm like,
Yeah.
nah.
Some old naked eye comet just doesn't do anything for you anymore.
Yeah, not anymore. I've been ruined since the 90s because of Comet Hale-Bopp. Now, my next question is this. All right. The sun spike that 3I Atlas is showing, which to me suggested that it was a matter of preferential heating somehow. What do you think the mechanism, what they call an anti-tail, but it's not actually an anti-tail. That's a different phenomenon. That's a perspective phenomenon with comets. But this is actually something the comet is doing. What do you think that is? Do you think it's just preferential directional stuff regarding the sun and composition of the object?
So there's a couple of different possibilities, right? And then just to be clear, you're talking about the sunward direct, like back a couple months ago, even we had hints of it, but the fact that the morphology of the tail seems to be pointed in the direction of the sun.
Yes, one way or another, it seems to be. Yeah, that's what I'm referring to. Yeah,
Yeah.
that may have changed, by the way. I mean, it may have gone away by now, but it was an interesting feature, sort of unusual.
Yeah, I think we reported that. Yeah, we reported. I was on some papers that reported that, but there are basically all of the observations that were taken from the get-go, from when it was discovered, up until a couple of weeks ago when we stopped being able to observe it from the ground. All of them agreed that the morphology of the tail looked like that, it was pointing in that specific direction. So that, first of all, it's not unprecedented, right? So you see stuff like that in solar system comets. It's not the most typical thing. In general, the morphology of the tail can tell you the morphology of the tail can tell you different things about both the physical processes and the physical properties of the things that are driving the sublimation. So one classic thing that you'll kind of hear, well, I don't know if everybody hears this classically because I don't know how much people typically learn about comets. I think it's not that much, but because I'm a little jaded right now because I'm teaching introductory astronomy at Michigan State for the first time. So I'm like, oh, right, everybody learns like the very, very basics, but that's totally not true because most people don't take intro astronomy. But one of the classic things you'll kind of hear is, okay, a comet will have a tail that's in the direction pointing away from the sun, right? The reason for that is that once the material blows off the surface, remember there's ice that heats up and sublimates, producing an outflow, but then there's also kind of little dust particles. So dust is our blanket term for things going from millimeter-sized rocks to centimeter-sized pebbles all the way down to micron-sized dust particles. So we've got all of these different kind of like sandy rock boulderish material that's getting blown off as well. What happens is that eventually radiation pressure from the sun, so the solar photons then hitting the tail, will push on some of the dust grains in that tail and push them all away from the sun. And so basically one way to what's actually going on is a lot of times when you see those like magnificent tails pointing away from the sun, a lot of times that material actually blew out first in the direction of the sun and then was pushed away. Because the most natural thing if you think about what's going on the surface of the comet, the most natural place for the ice to be outgassing from in the first place is in the direction of the sun. Because that's kind of, if you think of the comet, if you think of the surface of the comet, the part that's pointed at the sun, I wish I had a diagram right now, but like the part that's illuminated by the solar, if you look at the nucleus of a comet, if you put the sun down and let the solar photons kind of illuminate one of the hemispheres, then you'll see that half of the surface at any given time is illuminated by the sun. That is also the part of the surface that is most vigorously heated at any point in time. So that part that's illuminated, that's where you'd imagine the ice kind of, at the very zeroth order, ice will sublimate and come off the surface, and it'll actually be blown in the direction of the sun. Then after that happens, solar radiation pressure, so that means solar photons come and then they kind of hit the dust particles that are in that cometary tail and push it away from the sun. And that will then drag some of the gas along with it. So a lot of times when you classically see the cometary tails pointing away from the sun, that's actually because radiation pressure has acted on them after the fact. So like after they've been blown off the comet. For 3i Atlas, it's unclear exactly what's going on. I think we need a good amount. We basically haven't had time to do really we haven't had time to do detailed numerical or computer simulations to try to figure out exactly what could produce the tail morphology that we're seeing, because it kind of it depends on things like, oh, how far away from the sun were you? How far away from the sun were you? How much heating you got? And what different type of ices were there, and what different types of dust grains you allowed to be in the coma. But I would say for now, like right now, it seems like the fact that that sunward feature of the tail, that's probably telling you something actually about the physical properties of the dust grains that were blown off. Like the dust grains, it's possible that those dust grains were on the larger size. Like we know that happened in 2I Borisov, that the dust grains typically were quite a lot bigger than those that you see in solar system comets. The interpretation of that is kind of still up in the air. But if something like that happens, then they won't be as affected by radiation pressure. And so it's much easier to see a sunward tail if you have those larger dust grains. Does that make sense?
It does. And you can sort of visualize this process by thinking about snow in the sun. And if it's in the sun, it goes away faster than snow in the shade does.
Right.
Because it's in direct sunlight, so it's being heated. And so that you would have it preferentially moving towards the sun to begin with, but the sun is working like a windstorm and it's pushing it back. So you've got not only light pressure, but solar wind, particles, all kinds of stuff that push it back and create the characteristic long tail of a comet. But one of the interesting things about comets is that they can create, if you go through that tail, it can create a meteor shower. And that means that you can also collect samples of it. Are the particles and dust, especially, because I want some of that dust from 3I Atlas, can we send out a mission to go and do a sample collection after the fact in where it actually passed through and maybe get a few particles of 3I Atlas? Is it possible to do that kind of a mission and get some dust from this long after the fact? I mean, 2 centuries from now.
Okay, so there are several different parts to that question, and I want to make sure I kind of address everything. So first, yeah, I love your analogy of the like sun and the snow on the ground and sun heating it up. Everybody can kind of relate to that. Did I answer your last question like sufficiently? The one about the sunward tail? Okay.
Sure.
Okay, I had a couple different thoughts popped in my mind. So the first one, okay, this also, I'm a little biased, right? Because like on July 1st, I was just obsessively working on 3I Atlas, and a bunch of us put together that first paper about the discovery of the object. In those first couple days, I was thinking exactly what you're asking me. Like, how do we get a sample of this object? It's like we were obviously going to have lots of observations, right? I mean, it's very exciting. It's really great. That lots of people worked very hard to obtain observations immediately upon discovery and since. So that's all really wonderful and very important. But I was thinking the first couple of days, like, how are we going to get how did you say it, John? It was like, how do we get like a couple of pieces from 3I Atlas or a few?
Yeah, just a couple of dust grains is all I want.
That's exactly right. So the first thing, like you mentioned, like meteor showers. So comets in the solar system do produce meteor showers. So you'll have these like comets, especially ones that get close to the Earth, they will produce these big cometary tails. And then the Earth kind of sometimes the tails, blow out in different directions, and then they get very diffuse so that you can barely even see them. But every now and then you'll get meteor showers and you can basically, the radar experts who take those measurements and track different meteor events. There are these meteor stations all over the globe and also in space that track meteors. You can basically look at those observations, and the experts there will say they call them the radiants, but it's like what direction are the meteorite particles kind of hitting the Earth from? And then can you tie that to any known comet or active asteroid? So in that sense, you can actually there are comets or active asteroids that you get pieces of them on the Earth that you could just go and get if they survive the fall and become meteorites. So that, I was like, okay, I think I was, this is like kind of embarrassing to admit this, but it was like after like July 5th, July 6th, like that was such a blur because I didn't sleep at all for any of those days because I was just like writing that paper. But I was also it might have been me going a little crazy. But I was like, oh, let's see if we can get any like meteorites or is it possible that 3I Atlas has deposited any meteorite action or will deposit any meteorite on the Earth? I think the answer is very, very safely no, unfortunately. So I think it's like I asked some meteor people if there's any shot, and they were like, Daryl, like not in a million years, because it gets like so far away. It's so far away that it's like there's no hope of getting some of the material from 3I Atlas on Earth. Actually, in fact, you had a much better chance of having meteorite material from Oumuamua hit the Earth because it got so close to the Earth, even though it didn't have a big obvious tail. If there was any stuff coming off of it, which we presume there was because it had its non-gravitational acceleration, it would have been much easier because it came so much close. Like how close you get to the Earth is definitely the most important thing for if you're going to get any meteorite material. And so, yeah, there's no hope of getting that from 3i Atlas, unfortunately. It's also retrospectively, it's kind of obvious because it's like, yeah, if you just there are a lot of comets in the solar system, and not every comet produces meteorite material. In fact, we know that it has to be kind of, I don't know, special. It's got to be kind of a special configuration to produce a meteor shower. So already we know that it's like a rare occurrence in the solar system comets. And the interstellar comets are way less common than solar system comets. So it's very, very unlikely that you'd get meteorite material from any given interstellar comet. However, I think where you're also going, is it possible that we send a spacecraft to get any in situ measurements? Is that what you also want me to talk about?
Yes, but let's get crazy with it, Daryl. Let's. I'm gonna one up it. I'm gonna ask a question that probably no comet scientist has ever been asked on a YouTube channel before. So, say in an ideal world, and we have a large comet that comes through, a fairly sizable one that's enough to have craters, and we mentioned that earlier. And we have a sample return mission ready to go intercept it. We go and we get it. Now, we accidentally picked up a meteorite sample, a carbonaceous chondrite sample in the Apollo moon rock samples. So is it marginally possible that we would...
Sorry about that. My cat just like sat on my keyboard. So that's what all that... all that was.
That's fascination. The cat is fascinated. I have one of those too, but I actually, my studio is separate from my house, so the cat is safely over there sleeping in the sun, sublimating, the sublimating cat. But anyway, so say we get the sample return mission out there at an interstellar object large enough to have been hit by meteorites from the other star system. Could we end up with a smorgasbord of materials from that star system of origin when it was still there getting hit by meteorites, and be able to differentiate and say, well, look, this is analogous to a chondrite, but it's stuck on an ice ball. This is separate. This is a different sample. Can you get a 2-for-1 from an interstellar object sample return mission?
Yeah, that is a crazy question, but it's super interesting for sure. I have never even considered really that possibility, but presumably, I mean, maybe we can basically use that as part of the rationale for why we convinced NASA to get something together to go smash into an interstellar comet. So it seems like there's no... Besides it, I mean, it seems like an unlikely occurrence, but there's no showstopper reason that I can think of off the top of my head as to why that definitely won't work. So, okay, if we take a step back, if we are ever in the situation, John, where you and I can basically talk on air about the results of an interstellar comet mission, I think my life's work will be complete. So I'll be pretty satisfied just because we got something to an interstellar comet and potentially brought it back. So I won't be upset. I don't think I'll be upset if there's not micrometeorite material or carbonaceous chondrite material from the samples that we get back from an interstellar comet. I think if we're able to, it would be a remarkable achievement of both scientific and engineering achievement and humanity if we were able to do a space mission to an interstellar comet from another solar system. So if we're in that position and then people are arguing about the interpretation of the data, I think that's a wonderful situation to be in. It's possible, I guess. I think the hardest thing actually, so while I like where your imagination is going, the hardest thing probably would be figuring out like how to access that type of material, because it's going to be one thing to remember, right? If we're going to just think about 3i Atlas, like it's moving super quick. So we wrote this paper, this undergraduate I've been advising wrote this paper. His name is Atsuhiro. He wrote this paper that was just accepted about sending potentially, like outlining what kind of spacecraft could do a rendezvous with 3i Atlas. And we did this back a couple months ago when it was still feasible. So we showed that if we had sent some of those Mars spacecraft basically like before the end of September, we could have actually probably pretty easily gotten to intercept 3i Atlas. That's now probably infeasible. But back then, I mean, that's why we did the paper in the first couple of weeks. So we were thinking maybe we could send something. The thing is that the object's moving really fast. So if you allow for significant wiggle room, given the like fact that you only have a couple of weeks to get there and you don't have like years to do the trajectory planning and all of that, you really need, I think, a large room for error. What that means is that you're way more likely to intercept the tail than to intercept the nucleus for any given interstellar comet, because presumably that tail is kind of, as we've kind of already talked about, it's either getting blown out by radiation pressure or it's getting blown out from the comet to begin with. It's very diffuse and it like occupies a large volume of space, while the nucleus is a really tiny target. So I think it's much more likely ideally we live in a world in 10 years where we're discovering interstellar comets left and right, and we're sending space missions to them left and right. So that would be great. But I'd say that the first space mission we send to an interstellar comet, there's a good shot that we just get the tail, right? And if you just get the tail, you're kind of, what's the word? You're kind of biased. You know what I mean? But like, you're kind of biased in the material that you're sampling. So you really are, when you're going through the tail, yeah, you're getting some stuff from the surface, presumably that came along for the ride, but you're really probing the ice that's sublimating. And that stuff presumably is primordial. So it's like primordial ice that the comet was made from, / that it was built up from when it was forming. So it is totally feasible. I mean, it's really a remarkable idea, John, but it is totally feasible that an interstellar comet that comes through the solar system would have some, meteor type material from impacts with other objects in its host solar system, and some of that stuck to the surface, and you've got kind of crazy, what'd you say, a smorgasbord or something?
A smorgasbord or a sampling. It's its own sample collector, essentially, is what I'm suggesting. And so my whole overarching idea here, Daryl, is get a large sampling of another star system, because it's being delivered to you on your doorstep. You don't have to go there. It already did the space travel for you. But I'm going to up the ante again, Daryl. That's how I operate. A manned mission in the far future to an interstellar comet that is outgassing. Would you go on that mission and try to be the first person to set foot by proxy in another star system, even though that thing is blowing off carbon dioxide and all sorts of stuff? Would you do it?
I think I couldn't say no. I mean, like, this sounds like something that you'd write a book about, like the science fiction book about, but it's crazy that it's potentially not even, I mean, something like that maybe would happen in our lifetime. I mean, it's entirely science fiction, I guess, at this point, since we are legitimately talking about sending spacecraft to an interstellar comet. I guess, yeah. I think, yeah, I guess I would have a hard time turning that down, even though I have no desire to ever go to space. I think if that were the opportunity to see one of those things up close, to being one of the first people, being the first human to like get up close to an interstellar comet, how could you turn it down?
Yeah, and you can play with other ideas. Like, for example, if it's an interstellar asteroid, just an asteroid cooking through, and we're to the stage where we're mining asteroids, somebody might say, I wonder if there's any platinum in that thing, and go out to the interstellar and mine the interstellar material and melt it down. Sorry, were you done? Or do you have something else you were going to say? No, I trailed off into a giggle as is my way.
Yeah. So like another thing is that, so I'm rotating off, but I'm still basically, we call it like the early career logistic coordinator for the NASA Small Bodies Assessment Group. But that's basically NASA runs these AGs. They're called assessment groups, but they're supposed to basically be we hold these couple of meetings every year, and we get all the scientists in the community and write up the findings of everything that we like most want from NASA for NASA to do, and NASA then like responds to those findings. There is a whole part of this SBAG, like you can go look it up if you want, if you're interested. Like it's all public facing, so there are public facing goals documents that we update. So all of the like goals, things that we want NASA to kind of prioritize funding wise. There is a whole subset of SBAG that is devoted to human exploration. And by human exploration, like the SBAG is the Small Bodies Assessment Group. So we're talking about comets and asteroids. So specifically, there is a subset, like there is significant interest from NASA to do human exploration of small bodies, meaning like land a human on like an asteroid or a near Earth object or something. And one of the reasons is the asteroid mining thing, but I mean, the main reason is that they see it as a stepping stone to Mars. So it's not like the craziest thing ever that you're asking about. Like we have legitimate scientists, NASA has legitimate interest in sending astronauts to asteroids. So it is not I mean, while it is a little out there, it is not showstopper crazy, never going to happen to say go to an interstellar asteroid or comet.
Well, I think that was actually a suggestion that hit pretty high in politics, because I think Barack Obama suggested it. Let's go to an asteroid, and nothing ever came of it. But that was actually something that was mentioned back in the day.
I guess I was I was pretty young when Obama was like, I was like less than high school age. So I was not following like politics very well, I guess. So I missed that he said that.
I was unfortunately in my 30s. Anyway. Now, next question regarding 3i Atlas and its chemistry. So do you suggest or expect, as the chemistry evolves, to start seeing interesting chemical species reactions going on there? Because I'm presuming that's what this nickel is, and that it's a reaction, nickel compound forming from other things. And do you expect to see that this thing evolves? And what do you expect to see after it's done passing the sun? Do you expect a different character to this object after its perihelion and its closest point to the sun and highest sublimation rate?
Yeah, that's a good question. So you're right. I was going to say that earlier about the iron and nickel stuff. So at face value, right, that nickel detection is weird because when they observed the nickel, 3i Atlas was way too far from the sun for nickel to just be vaporizing.
So I wonder about the chemistry. What else is going on?
Right, exactly. So the interpretation is for sure that there is some type of chemical reactions that are happening to form the nickel. There are a couple different avenues, like chemical networks that you can go through to produce that. And it's still kind of up in the air exactly what it is, but you can blanket the way that we're talking about right now. You blanket it with the Comet experts basically say like non-thermal processes, which means it's not hot enough for the nickel to just be vaporizing, but some other things are going on. I mean, there's a lot of really interesting chemistry that goes on in the coma of a comet. So that's certainly what we're seeing. But the exact chemical network to get there is unclear right now.
Yeah, but it's extraordinarily cool because when you're dealing with an object that's much older than the solar system is, that's what I'm worried about. I'm like, well, what was the universe's conditions for star formation and disks, debris disks and everything forming planets back then compared to now?
Yeah.
Was there a difference? Have we had a few more, having had a few more supernovae around us, does that change over time? Does the Milky Way's way of forming solid objects evolve?
No, that's you're exactly right, John. Like that is the money question. And like from exoplanet science, we know that it does. So we know that there is, for example, one of the best known rules or empirical trends of all of exoplanet science is that you're more likely to find a hot Jupiter exoplanet if you have more metallicity. If you're looking at a star with higher metallicity, which means a higher total amount of metals. Presumably, like the obvious interpretation of that is that, oh yeah, well, there were more metals in the disk as well because the star is more metals, so there's more metals in the disk, so you were able to form more planetesimals and comets, asteroids, and then planets. But at the same time, we also know that because, as exactly what you're saying, as the Milky Way gets older, more supernovae go off, and the supernova enrich the interstellar medium with metals. So one possibility is that actually you're enriching as you get older, you're enriching stars with more metals. And so that metallicity dependence, or the fact that you're more likely to see a hot Jupiter around a metal-rich star, maybe it's actually you're just more likely to see a hot Jupiter because more hot Jupiters formed in the more recent Milky Way. This interstellar comet, 3i Atlas, is probably significantly older than anything that we've seen in the solar system before because there are a few caveats that we probably should say, but it was going wicked fast at infinity, which is at least consistent with it being billions of years old, potentially potentially older than the solar system itself. And so it could be, if it really came from one of those planetary systems that formed way before a lot, like in the lower metallicity Milky Way galaxy, before a lot of the supernovas had gone off and enriched the galaxy with metals. Maybe it's kind of like one of those, maybe its composition is weird compared to solar system comets because it was formed in a disk that had much less metals. And it was one of those kind of like weird outlier things that formed. Like, I don't know, I'm just spitballing, but you see what I'm saying?
Yeah. And what part of its disk did it form in?
Mm-hmm.
I mean, well, being so carbon dioxide rich, probably formed pretty far from its star, right?
Yeah, well, that's I think at the beginning episode I said I wanted to focus on the JWST observations. So it was JWST and Sphere X. Yeah, JWST and Sphere X got the CO2. It was Swift that got the OH and the H2O. But yes, so the high CO2 especially the high CO2 to water that was measured, that is kind of remarkable because you can think of it basically like if you just blanket it like H2O, CO2, and CO, those as the three kind of main drivers of activity in comets, you could think of it like basically the existence of those species tells you where in the disk it formed with respect to those respective ice lines. For reference, the H2O snow line in our solar system is around Jupiter. The CO2 snow line is around Saturn, and the CO snow line is around Neptune. So the fact that it had a lot of CO2, but not a lot of CO and not a lot of water, potentially is telling you that actually it had to form in this like sweet spot. Like, yes, far out, but not too far out. Because if it formed too far out, carbon actually would rather be a CO than a CO2. So I think it's actually the reason those CO2 observations are so amazing to me is that it's telling you that I think that 3I Atlas had to come from a relatively narrow region in its protoplanetary disk. So that actually kind of like, even though with an interstellar comet, you can't trace it back to a host system, that tells you a remarkably specific amount of detail about the ambient environment in which 3I Atlas formed.
Do you think that goes so far as to be able to determine the type of star that it formed near? Meaning, obviously, it's overwhelmingly likely to have been a red dwarf, but do you think that the profile might change if it formed in a system of an F-type star or something like that, and we could maybe tease that detail out of an interstellar object like this?
Yeah, I mean, that's actually like exactly what my one graduate student is working on right now. So the short answer is yes, I think potentially. You can't trace any interstellar comet back to any given star because the galaxy's orbits are chaotic. But you can kind of roughly say the speed at which they're entering the solar system kind of roughly correlates with what type of star it comes from because older stars in the galaxy move faster on average. So then there's the fact that the chemistry traces it to a location in the disk. So I think that by combining, basically what you have to do is you combine the information, you get all these different pieces of information. If you put them together, there's basically the chemistry you're seeing on the comet. That's kind of giving you a narrow region in a disk. It has to be. And that narrow region of a disk, like those locations of the disk that has CO2 frozen out, but not CO and not water, that changes as a function of how hot the star is. And then you have the information about how fast it's coming in. So that kind of tells you which stars types it's most likely to be coming from. And then you can go a step further and say, now we've narrowed down some different kind of, basically we've narrowed down stellar type, some combination of stellar types and snow line regions in the disk that it could have come from. I think then once you compare it to, if you say, for example, that this thing was ejected by a giant planet, you go to what we know from exoplanetary science and we say, well, which stars are most likely to have a giant planet in the right region to eject a CO2-rich 3I Atlas? I think you might actually get somewhere in terms of figuring out what the most likely host stars are. But kind of stay tuned for that. Like my grad student, Tessa Frinke, who I think is on, you've talked to her before on the show. Yep. She's working on that right now. So we should have some results about that in the next couple of months.
I look forward to it. All right, Daryl, thanks for joining us again today. And I look forward to talking to you again as we continue to get a profile of 3I Atlas and future interstellar objects, because Vera Rubin is up and running.
Absolutely. Thanks, John. Thanks, Ross. Thanks for having me. Always a pleasure.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.
It's not over yet. Join me as we continue to travel through the cosmos on a gentle wave into another episode of Event Horizon with your host, John Michael Godier.
Daryl Seligman, welcome back to the program.
Hey, John. Thanks for having me on again.
Daryl, you made an interesting discovery, to say the least. The third interstellar object ever, 3I Atlas. And this object has been causing a bunch of controversy, of course. Interstellar objects, everyone except Borisov caused controversy. And the thing about Borisov is that it was very clearly a comet. And at this point, it seems that a solid case can be made that 3I Atlas is also a comet. It appears to have a coma. Now, you did recent observations, and these observations are interesting because they made use of the Vera Rubin telescope, which is in testing, but already giving us science. And there seems to be further evidence that it is indeed a coma-producing comet. Tell us about that.
Yeah. Okay. So I guess the first thing that I want to say, just to clarify, is that I think you're giving me a little too much credit. So even though I led one of the early papers about the preliminary observations of 3I Atlas, I was not the discoverer. And I don't know if you want me to get into the story of what I did do in those first couple of days, but it was...
Go for it.
Sure.
Go for it. Tell us the story.
Yeah, it was just an absolutely crazy time. But so basically the Atlas team discovered the object, which makes sense. So the key people in that are Larry Deneau and John Tonry, everyone else who works on Atlas and part of the collaboration. But John Tonry, who is a faculty member at University of Hawaii, basically built Atlas and got all the funding for it and had the inspiration to do it. And then Larry Deneau, like looking at the images, if you look at, I think it's the first figure in our paper, but those were the actual discovery images that he spotted the object in while they were doing routine maintenance or something on the survey. So they found it. And what happened was the first night, I believe it was July 1st, maybe it was the night before that, but I basically was going to bed and there was like buzz about potentially another interstellar object, but nobody really knew what was going on. And that was right after Larry had spotted it. But the buzz was starting to leak out, and I emailed Karen Meach and Davide Farnokia and Marco Micheli. Davide, and those are all people that I've done dark comet stuff with and people who are experts at tracking objects throughout the solar system for planetary defense reasons, but also mission planning reasons. And I was like, is this thing for real? Because like, it's pretty typical actually that we'll get an interstellar object scare. So we find something and it's like, oh, this thing looks like it's hyperbolic. And then we get a few more data points and it's like, okay, no, this thing is actually a long period comet, or it has an eccentricity right below 1 or something like that. So I went to bed around 9:30 or something. I sent them an email being like, is this for real? And then I don't sleep very well typically. So I woke up at around 1 a.m. And to my like shock, I got emails from both Marco and Davide, who are basically NASA and ESA's expert at this, being like, this is for sure interstellar. And so I was just, I was kind of in shock at first. Like I was like looking at my email and just like, there's no way we found a new one. And then it was like 1:30 in the morning. And I was like, well, I guess I slept like 3 hours, but there's no chance in hell I'm going back to bed. So I kind of like jumped up, and I think I was just really excited. I couldn't decide, like my heart was just like racing. I couldn't decide what to do. So I went to Dunkin' Donuts and I got an extra large iced coffee. And then me and Marco was in Rome at like, so it was like 8 a.m. for him or whatever when we were working. So I threw together like an overleaf, which is where we write the paper, and started writing stuff. And both of us were trying desperately just to get as many telescopes to look at it as possible and get the orbit better. And then it was just, for the next 5 days, we just kind of furiously wrote the paper. And then everybody who was getting up, so many people who were getting observations started like coming, like, because I guess news got out very quickly that we were writing a paper. So everybody just was trying to give us their data so we could like include it in the paper. And so it grew to like over 50 people on the author list very quickly.
Dunkin' Donuts has excellent coffee. I have to point that out. That out of the coffee availability market, Dunkin' Donuts ranks relatively highly.
Yeah, it was hilarious because that was like 1:30 a.m. So I got that huge like cold brew at Dunkin' Donuts, and then the next 2 days, it was Wednesday and then Thursday was July 4th, I think, or Friday. I don't even remember, but there was the long holiday weekend. So I just spent I basically didn't sleep at all for like 6 days and worked every minute that whole time and finished the paper and submitted it.
Now, it was clear, though, from the very start in the early photography of this that it seemed to have a coma.
Right.
And you would expect that. And there was controversy, there was controversy about, well, this object's very bright for what it is, which that's relative. It is not very bright. It's like 18th magnitude or something, but for what its distance and all that, it's bright, which would imply that it's large. But a comet's coma is large.
Right.
And if the nucleus is tiny, which is what you would expect. Small things are far more common than big things in the universe. But the comet's coma is big and reflective. It's like a cloud of dust and gas coming off the comet as it nears the sun and warms up. Now, that seemed clear, but there would have been a problem had it been an asteroid and had not exhibited this. Tell us about that.
Yeah, you're exactly right, John, as always. So what happened? Actually, I was actually exactly wrong. So what happened was, so we put the paper together, and so me and Marco Michele, so we wrote the paper super quickly, right? And at first, those first couple of hours, the first couple of days, really, I mean, everything blurs together because it was such a just like blur, and I didn't sleep at all. So I was running on like no sleep, but I'm pretty sure the first couple of days it was not obvious that it was a comet. And so we thought it was inactive. There's also there's another important piece, which is that we know that solar system comets, like when they come in from the outer solar system, they don't always activate. And by that, I mean like ice starting to sublimate and produce dust coma. They don't always activate until they get closer in. So you wouldn't even necessarily expect this thing, when we found it was like 4.2 AU or something like that. So you wouldn't even necessarily expect it to be sublimating vigorously at that point in time. So we thought at first it was just an asteroid. So what I did was, I guess I had the first paper on archive. And so what I had about the object, so what I had done was you take the absolute brightness that Marco measured in some of the first images, and you say, okay, if it's that bright and this far away, and you assume that there's no coma whatsoever, you assume it's an asteroid, and then you assume an albedo like other asteroids, which is like, well, I don't know, we guess like 0.05 or 0.1, which means 5% reflectance, 10% reflectance, something like that. That gives you a size of on the order of 20 kilometers. And so we kind of said, okay, if it were inactive, although we'd expect this thing to eventually activate, it's the nucleus size is 20 kilometers, but that's probably an upper limit. And then it turns out, I mean, that's also a crazy size, because if that's real, if that were the real size, that would imply a huge amount of mass in the galaxy in interstellar comets. So it would imply that on average, something like every star is producing on average 0.1-ish solar masses of comets that they're ejecting. So that's a very high number, because stars don't have that much material and metals, or what astronomers call metals. So that would be remarkable if that were the case.
And you would see that difference in the stars themselves, in their makeup. You would see that metallicity would be anomalous.
Yeah,
it would be higher,
right? Presumably. But we also, I mean, independently, we kind of know, well, if these are planetesimals that form in protoplanetary disks, you kind of roughly know, not very well, but approximately to kind of order of magnitude how massive disks are on average. So it's more massive than all of the disks put together. So if that were actually the mass, that would potentially tell you that, maybe these interstellar comets don't actually form in protoplanetary disks. Maybe they just form in situ in the interstellar medium. I don't know. But much more likely was that it was like we said, it was an upper limit, and had some cometary activity. But then somewhere in that span of like 5 crazy days, we got some images where you could start to see the cometary activity. So we're like, oh, right. Okay. So we kind of applied the asteroid, this is the size it would be if it were an inactive asteroid, but it's actually looks much more like a comet. So it's probably much smaller.
Now, the data from Vera Rubin, which I'm very excited about this telescope.
Right.
This telescope is already delivering and it's in testing, but yet there's already scientifically usable data, and it's already discovered 2,000 asteroids just on a test run. I mean, it's just amazing, and just the idea of a survey telescope like that is just exciting because you get to see things moving, and that's what we see with the interstellar objects as they move through. But what in this data is, it further indicates for the Vera Rubin telescope data that this is indeed a comet. What's telling you, what do you see that's consistent in that data set from the new paper, which there will be a link in the description below that's saying, you know, this is consistent with a comet?
Right. Yeah, and you basically said this, but it is worth stating that the data that we got of 3i Atlas from Rubin, it wasn't even in the LSST, so it wasn't even in the big survey that they have planned because that hasn't started. These are just essentially just, you mentioned it, right? But it's essentially just testing images. So they were doing what they call science validation. That's the stage that they were at in like at June, July. So they were just looking at doing kind of preliminary testing of the camera and things like calibration, stuff like that. And then we totally independently, and just remarkable coincidence is that Atlas discovered this crazy interstellar object right after Rubin was getting first light. But really, remember, this is not as powerful as what the survey, it's not operating like what it will be in the future, which is going to be much more powerful. So it's remarkable. It's a remarkable testament to the Vera Rubin Observatory just in general that we were able to get anything from just the science validation images. But we ended up basically getting, I forget the exact number, but we got images of the comet from back to, I think it was June 21st, I think is the first one we got. So yeah, 2025, June 21st, all the way through July 7th, almost every night, we got recovery images of the object from essentially just engineering time, which is remarkable. And it is also worth saying that Atlas did a phenomenal job in finding this object. So although, John, I love your excitement, and I have been on this show before, and we have done entire episodes just about Rubin and how amazing LSST is going to be, it is worth giving credit right now to Atlas, which is still going to be operating and very well could find more interstellar objects in the future. So I think, Atlas really did a great job here. But yeah, so we got, basically, there were several people who were leading this amazing effort with the Rubin Observatory because it was, so the paper's on archive now, but it was a huge effort. You'll probably be able to see that there's 150 or more people on the paper, but really Colin Chandler, Pedro Bernardinelli, and Mario Jurek and Meg Schwam did this huge effort just to put everything together in a very short amount of time. And it's, these days it's exciting, things are exciting, but also the pressure's on because you want to get the information out to everybody else in the community as quickly as possible so that we can all kind of plan our follow-up observations while we have the chance to observe this object. So it's kind of time critical to get this stuff out as quickly as possible. And because the survey was operating at a science validation stage, it was non-trivial. Like they didn't expect to have to release any of the data, let alone publish it. So it was a huge lift just to jump through all of the hoops for this unprecedented discovery, just to be able to publish this and put it on archives so that all the other scientists could take a look at it and people in the public can take a look at it. But what we were able to see is, there's pretty clear evidence of cometary activity in the Rubin data. And it's kind of some of the earliest pre-covery images we have on 3i Atlas from a large 8-meter class telescope. So there's lots of exciting things that we'll be able to do and continue to be able to do with something as powerful as the Vera Rubin Observatory looking at this object. But it's great to see it so far, what they've been able to do just with the pre-covery stuff.
Reactive science. You only have so much time.
Yeah.
This thing cooking through, And this time we saw one coming in, as opposed to like Oumuamua, which was on its way out when it was spotted by Pan-STARRS, and University of Hawaii, as you mentioned, Karen Meach. The thing is, though, this one is coming in, so we can watch its evolution as it moves through the solar system and then leaves it. And I know also another reactive thing is the Hubble Space Telescope is going to take a look and hopefully get a high quality image. Is there any idea on the time frame on that?
Yeah. So to your first point, you're absolutely right. So it is, all I could say is remarkably fortuitous, but it's, yeah, just remarkably fortuitous that we caught it coming in. And not only coming in close, I mean, at 4.2 AU, like, it's just like hats off to Atlas. It's just remarkable that they were.
It is remarkable, and it gives us months.
Yes, exactly.
Months.
Yeah, so we have months to observe it. And, Borisov, we had months to observe, but then there was the COVID pandemic, which shut down basically all the ground-based facilities, which is just terrible timing. But so Atlas, it's lucky in that we caught it as it's entering and as it's 4AU, but it's also, remember, this thing is moving crazy fast. So because it's moving so fast, we don't have that much time. And so it's going to have perihelion in the fall, but the problem is that it kind of goes from the Earth's, it's a bad apparition with respect to the Earth. So like we won't be able to observe it during its perihelion in the fall, but then it'll pop back out in November and we'll be able to see it. So we'll have lots of time to get observations of it, but it's not as ideal as we'd like it to be. And then you asked about the Hubble Space Telescope observations. I have not seen those yet, but Dave Jewett was able to immediately obtain a director's discretionary time. So he basically immediately convinced HST to look at the object. And I believe his observations started last night. So, and last night, I mean, I know this episode is going to be released after, so we can look up the exact dates with respect to when you air this episode. But so he would have just gotten it, I guess, very recently. He is kind of a ninja when it comes to the telescope. So he can usually get stuff out and get information out to the public very quickly, but it'll take him at least a couple days to reduce the data and take a look. So I think I would expect hearing more about the Hubble results on a timeline of something like 3 weeks, but I would say don't quote me on that, but I guess we're recording, so you'll quote me on that. But
well, I can say this, I can for reference, it is Monday, July 21st.
Right. Yeah, so hopefully we'll learn in the next couple of weeks. But Dave was able to get a huge amount of information from the Hubble images that he got, and the Hubble data that he got on 2I Borisov. So just from the Hubble data alone, he was able to figure out the size of the nucleus, basically. So he wasn't able to nail it. I mean, nobody was able to nail it down completely, but he was able to independently put upper and lower limits on the size of the nucleus. So we know that it was kind of in the sub-kilometer range, like 200 to 800 meters-ish. Also, he was able to, from his Hubble data, kind of predict that a breakup was going to occur, which it then did. So he's kind of there's a reason he's a super famous observer, but he kind of is able to get a lot out of data, even when you have a unfortunate, I mean, it's remarkable we observed this, but in some aspects, some aspects of the geometry or of the apparition are somewhat unfortunate. So I have full faith that someone like Dave is going to be able to get as much out of the space-based assets that we currently have as possible.
Now, is there any advantage, and people are specifically going to ask this, so I'm going to ask it, is there any advantage that the James Webb Space Telescope, which also has some built-in time for serendipitous events where it can swing around and look, is there any advantage for that telescope to take a look at an interstellar comet like this?
Yes, certainly. I think the best way to think about it, though, is not like a competition of which asset is the most important to look at it. It's just more like, how do we get the most comprehensive wavelength and resolution coverage of this interesting object that everybody is interested in? Because, that was part of the reason of, I basically opened up the author list on the paper that I wrote that ended up being one of the discovery papers to anybody who was interested and wanted to collaborate and wanted to publish their data quickly, because we're all in, like, everybody in the world, every astronomer and amateur astronomers too, right? Like, everybody is looking at this object. We're all collectively interested. And there's no reason to be competitive about things. Like, the goal should be that collectively we get as many photons of this object from as many different wavelength regimes as we can, so that we can learn enough, because in 6 months, we're never going to be able to look at it again. And this is one of the most fantastic small bodies we've ever observed passing through the solar system. So I think that's the way to look at it. And HST, right, I think is mostly looking like, the unique thing that HST offers is space-based ultraviolet observations. It can do infrared stuff, but it is unique in that it is the only really real, like it is unmatched capabilities at ultraviolet wavelengths in space. And then the James Webb Space Telescope, what that will really be great at is looking in the infrared. So I think basically they're entirely complementary. So we want as much time as possible on both JWST and HST, and at as many different points in the trajectory of 3i Atlas as possible, because things change in comets. When comets, you already hinted at this, John, but or you said it, like when comets get closer to the sun and further away, they change and they have different ices that activate, and that can tell you about things like what is the composition of the nucleus that it formed with, and also how deep are the different layers of those ices. And then some of those ices you can only see in with JWST in the infrared, and some of the ices you can only see in ultraviolet wavelengths. So there's kind of really compelling science to be done with both of those assets.
Does the infrared profile change as a comet gets closer to the sun? In other words, warming it? Do you see it brighter in infrared as it gets closer to the sun, or is it just simply too cold?
No, you'll see that. So with the infrared measurements, you can potentially, especially if it's inert. So if there's no cometary activity, you can, based on how bright it's shining in the infrared at different wavelengths, you can do things like constrain the albedo because it's, thermal, because it's just heating up and emitting. So you can do stuff like constrain the albedo and the thermal properties of the nucleus. But in the case of a comet, I think what we're expecting is you spectroscopically with JWST detect things like maybe H2O or CO2 or CO, so water, carbon dioxide, or carbon monoxide directly being outgassed. And that for sure would change. Like that is not that's not even contentious. So we see this happening. We see comets. For example, the production rate of something like, by production rate, I mean how many molecules per second, but you'll see things like the production rate of water changing over time and the production rate of CO2 changing over time. And that's because as you get closer to the sun, it's receiving more solar photons. So you're literally able to sublimate more of that ice. And it just, as it goes through its trajectory, it's probing deeper and deeper layers from the top of the comet nucleus. So you're seeing deeper and deeper into the nucleus of the comet as it sublimates.
You're seeing deeper and deeper, and that leads us to my next question, is that this object appears to be very ancient, originating from the galactic disk where a lot of very old stars reside. And this appears to be a very ancient object from an earlier period in the universe, which means that it is very important to see what the makeup of that comet is and compare that to comets in the solar system. What does a comet that formed 4.5 billion years ago look like versus one that formed 8 billion years ago, something along those lines? Tell us about that what can we learn about the earlier universe from studying 3i Atlas?
Yeah, John, I swear you should just be writing scientific papers yourself, because you're always asking the questions that are like the key questions about what we're trying to figure out when we come to this stuff. But you kind of hit the nail on the head, but it's even more extreme than the numbers you quoted. So the way it works is the speed of one of these interstellar objects as they enter the solar system kind of roughly traces. There's kind of big uncertainty on it, but it roughly tells you how old they are. And that's because as time moves on, if you're just an object floating around the galaxy, the more and more time there is, the more time there is for you to get gravitationally scattered off of things like giant molecular clouds. So older things in the galaxy move faster. So Oumuamua was moving so slowly in the galaxy with respect to everything else that even though we don't know for sure, it's very likely that it was younger than about 100 million years old. While 3i Atlas was moving more than double the speed. It's like 58 kilometers per second versus like 26. And that corresponds roughly somewhere between 3 and 11 gigayears. So significantly older object. And Borisov, weirdly enough, is kind of right in the middle. So even though the age kinematic relationship of these objects is very kind of order of magnitude-ish and uncertain, because it's kind of fundamentally, it really applies more when you have ensemble of objects, so many objects, it is kind of peculiar, or at least curious, that we found three interstellar objects, and you get one that's really young, one that's really old. So the really young one, right, is Oumuamua. The really old one is 3I Atlas, and the one that's smack in the middle is Borisov. And I think that means, so this is what Astor Taylor, who I think you just had on your show, what they kind of showed in a paper we wrote a couple days ago. It's very roughly, I think if you look back, if you think of these objects as tracing planet formation, or as tracing the efficacy of planet formation during a certain amount of time, I think it's kind of telling you that at all of these stages throughout the Milky Way's lifetime, or the last 100 million years, the last billion years, and approximately the last 10 gigayears, you have roughly equally ubiquitous planet formation. So another way of saying that is that 3I Atlas, I think, is telling you that planet formation was going pretty efficiently at the earliest stages of the Milky Way's lifetime. And even the lowest metallicity stars were still efficiently forming and ejecting interstellar comets, which is, I mean, if that's not astronomically beautiful, I don't know what is.
Well, it creates more questions than it answers, because
That's true.
if you have planets that early, Fermi paradox, where are they? Those types of questions start arising, and that this has been habitable for a very, very long time, the universe. Now, the youth of Oumuamua, that it was a very young object, is it possible that there's something hidden in there that would account for the weirdness of that object? Just simply, it's something in a young state that, you know, maybe it hasn't had enough time to pull itself into a more spherical position or something like that. If it's a shard from a destroyed planet or something like that, does the youth possibly speak to the weirdness of that object?
I don't know. That's a good idea, but I just don't. I would flip it on its head to you. I would say the youth is like the weirdest thing about it. I don't know. It's still a mystery, to be honest. Like, I am obviously biased to my own theories or theories that I've co-authored, but it's still a mystery. I'm hoping, actually, like, I think Oumuamua's youth is one of the weirdest properties of the object. Like, why did we, given the age of the galaxy, like, and there should be more stuff that formed further back in time, like, why was the first one that we got the really young one? That is weird. It might be, though, the fact that, you know, Oumuamua was moving really slowly in the galaxy. I mean, obviously it sped up as it was entering our solar system. It looked fast compared to the solar system objects that we study. But I think that's something that Dusan Marcetta and I showed in a recent paper, was that typical interstellar objects, when LSST should be able to find them, they move really fast across the sky. And when you're moving really, really fast, they're really hard to detect, because in order to detect them, you don't have to just see them in one image. You have to see them in multiple images. And if objects are moving fast enough that they move out of the image, by the time the telescope comes back to look at them, maybe that explains why Oumuamua was so young. And that was the first one we got. Although I don't think I could authoritatively say that. I'm just speculating. In any sense, though, I think one, you know, fundamentally, and John, we were talking about this offline, just you and me. Fundamentally, these interstellar comets, as they travel through the galaxy, they are telling you, I think they're going to tell you about the differences in planet formation across the galaxy, but also how does this planetesimal material get processed in the interstellar medium? And the older they are, the longer time they've been exposed to things like high energy radiation and cosmic rays. So maybe when comparing what we see with our telescopes, with our assets like JWST and HST and all the ground-based stuff, if we compare the composition and dust profiles and stuff like that, that'll tell you about what happens to a comet after it's been processed for 100 million years versus 10 gigayears, and how different does that look? Because that has ramifications for stuff in the solar system. Like, there's stuff in the Oort cloud, these long period comets, that get processed by the very same stuff in the galaxy as these interstellar objects. So maybe that can help tell us about our planet formation in our own solar system and in exoplanetary systems.
Well, that was one thing that I found interesting, is the reddening that was detected early on with 3I Atlas. And, you know, that's a keen interest because that's usually organics, right? That you know, just exposure to the cosmic rays and, you know, the interstellar medium reddening objects like that. But that's due to organic compounds, isn't it?
Okay, so it can be. So the observations that we have do not preclude those from being there. There's a confounding point though that we have to be careful about. So it could be that we're seeing organics or something like that. But there's other things that it could be. It could just be material that's gotten broken down from the galactic cosmic rays, like ices that are broken down, not necessarily organics. Also, the most important caveat. So at face value, if you look at just like, I don't think in the LSST paper we have this because we just have some colors in the LSST paper. But if you look, I don't know if you want to show it on your episode, but if we look at I think it is figure seven in my paper, the one where there's a spectrum and colors that we got, that shows you that the object is reddened. And it also shows you how it looked, how the spectrum and the reflectance looks. And by that, I mean how the color of 3I Atlas compares to both Borisov and Oumuamua. And it kind of looks consistent with what we saw with Oumuamua and Borisov. The problem, not a problem, but the important difference is that Oumuamua, you weren't seeing significant dust coma contamination. But for this object, we've already noticed photometrically even that there is a coma. So that means that it's much brighter than it would be without the coma. So a lot of this light that we're seeing reflected is coming off of the dust in the coma. So what that means is that might not really be the color of the nucleus. That might just be the color of the dust. So the interpretations of that, and as to the extent of which, is it really organic chemistry and organic stuff that's going on the surface, or just reddened dust for various reasons, I think is unclear as of now. As much as I would like to tell you some amazing discovery, currently it's unclear, but we might be able to get more answers with follow-up observations.
Now, statistical populations that we've seen, a young one, a medium one, and an old one, would suggest that if we continue to see that trend with interstellar objects, future ones that are detected, which is what the LSST, that's one of the beautiful things about that, is that it will detect more of these along with the other telescopes. That will tell you, if you keep seeing that trend of relatively equal amounts, and you need a lot more for this, of course, I'm well aware of that, but if you see that trend where it's all three of them are about equal in numbers in population, then what does that tell you? In other words, what can you tell from seeing that variance in the population of interstellar objects? What does that tell you about mass and things like that? And I think more importantly is, in the case of 3I Atlas, shouldn't that be the rarest type coming from an earlier period in the universe?
Yeah, no, you're totally right, John. I think it's funny to even be talking about that with you now, because I feel like in the last several years, like I was hoping so badly to find more of these objects and we were not finding them, that I didn't let myself think about what the repercussions or interpretations would be if we found them, that now I get to speculate on that. Just that in itself is kind of exciting, because it's what I've been wanting to do for a while, but I've been scared to let myself. But now that we found the old one, I think, yeah, it's fair to say, if we find more and we see this trend where we see, just ballpark, you see a third of them are really old, a third of them are really young, and a third of them in the middle. I think that's telling you that planet formation, yeah, I think we could go on and on about caveats, but there's the caveats of like also, these things could get destroyed during their travels through the interstellar medium. So older stuff might get selectively destroyed as well, but I'm gonna just speculate. So don't hold me accountable for what I say here, but it could be telling you that, the stars in the Milky Way at the youngest epochs of star formation in the Milky Way galaxy were efficiently forming planets. And remember, John, you had alluded to this earlier, but the younger times in the galaxy, there have less supernova have come off. I think all of your listeners are familiar with this, but I'll just expand a little. Just as supernovas go off, as the galaxy ages, supernovas go off and they produce metals, and those metals will then enrich the interstellar medium. And then as new stars form, planets that form in those disks, there's more metals to form planets out of them. So the youngest stuff in the galaxy is lower metallicity, very approximately. Again, there's some caveats there, but I think it's telling you potentially that the youngest stuff that's at lower metallicities was also efficiently forming planets. And it's like we're not just talking about forming planets kind of generically, like we're talking about forming planet formation, like violent and vigorous planet formation occurring to the extent where you have like a hugely massive thing like Jupiter and Neptune, which is able to move around and eject Earth masses worth of material of interstellar comets like Atlas and Oumuamua. Like we're talking about vigorous dynamical instabilities occurring at very young stages. So yeah, I think there's a lot potentially to learn.
You know what would be freaky? I'll speculate too. So say that in the future, 150 years from now, we're able to go and do a sample return mission to an asteroid that's moving at this speed, dating it to that period in the universe, and we go and we look at it, and we look at the iron levels, and they're exactly the same as today.
Yeah.
I think you understand what I'm getting at there. That would be weird, really strange. But what would be interesting is to compare that, because that would give you some data, I guess, on if you had enough of a sampling of these objects, sample returns, and looking at the iron, that would tell you a lot about supernova rates during the early universe. So there is a lot of reasons to study this stuff.
Yeah, it's almost like I think you're getting at, right? Like it's like an unprecedented window into star formation throughout the galaxy and supernova rates and everything. Supernova rates is a function of time, even something like that. If you had enough interstellar objects that you got up close observations of, or even in situ samples.
And it pays to remember here that these three detected interstellar objects so far represent 3 different other star systems. Yeah. You don't have to cross space-time to go and look at other star systems with a spacecraft or a light sail or whatever you're using. It's coming to you. You won't know exactly what star system, but you're going to get a profile of star systems in the Milky Way by studying interstellar objects. And that absolutely blows my mind, because that is an alien rock. That's not from here. Totally. That formed somewhere else.
Absolutely. And another thing is like, it's not like, it's a subtle point about it. You saying you don't know where it came from, because it's true that you can't trace any one of them back to any given star, but you can say something about where they come from. Because you could say, if you detect a lot of them, you could say stuff like, oh, these ones are probably older on average, and these slow ones are probably younger on average. And you can say, oh, well, these kinematics look like they were moving with this stellar association or something like that. So you can kind of you could say more about the origin, at least the origin stellar population. You could say more about that than nothing.
True. Now, let me ask you this. Comets create meteor showers. Basically, the Earth moves through the former path of a comet, and we see it as a meteor shower. So they're leaving material behind. Would an interstellar object leave material behind that possibly could be collected in the future, like this object in its wake as it goes past perihelion and heats up and it's throwing off dust? Could you go out there and perhaps collect some of that dust, or would you not even be able to differentiate it from the normal dust of the solar system?
Yeah, no, that's an excellent question, John. So the one you want to do that with was Oumuamua, because Oumuamua got really close to the Earth. So they did that. So Quanzi Yi and Qicheng Zhang, they were looking into meteor radar data to see if they could detect any meteor showers from Oumuamua. Unfortunately, that all turned up non-detection. So that was just all we were able to get from those non-detections, which are still useful as limits on the production of stuff that came off of it. But absolutely, that is something we could do. The issue with 3I Atlas, although it's vigorously outgassing and producing dust, much more so than Oumuamua obviously was, it gets nowhere near as close to the Earth as Oumuamua did. So it is basically hopeless. It is hopeless to get particles from that object on Earth that we could identify. It's just like it's not going to cross Earth. But that doesn't mean that it's not shooting out stuff into space that if we had a spacecraft close to it or in its wake or something like that, you couldn't sample. Like absolutely, you could sample a coma of a comet.
Send in JAXA. They're experts at this.
Yeah, exactly.
Now, let me ask you this: volatiles and depletion. In other words, given that this object is very, very ancient, but yet it's producing a coma, does that suggest that it was never close to its star? In other words, it was never a comet that, as we normally see them, solar system comets on their orbit, but rather just some distant object that formed from the star way distantly, like in the Oort cloud, whatever, and got ejected that way, and that this is the first star that has come close. And if you ever saw a comet that performed very, very strongly or very, very weakly, would that imply that it had in its past passed close to a star?
Yeah, no, that's a really good question, John. So, yeah, presumably everything you said is correct and the correct interpretations. I think the natural thing to think is the fact that this thing is sublimating pretty far out, like it has volatiles that haven't been depleted. It couldn't have spent too much time really close to a star. It's very unlikely, even for 3I Atlas, just because the galaxy is so, I don't know if porous is the right word, but the galaxy, there's so few stars are spaced out so far apart from each other. It is extremely unlikely that any interstellar comet would have had any, that we see passing through the solar system, would have had any close encounter with any other star, like really close. So presumably any interstellar comet we ever find has almost certainly never been close to a star since it was ejected from its home system. If they still have volatiles like ices left in them, then yeah, I think it's safe to say that that object probably didn't spend too much time close to its host star if it formed in a protoplanetary disk before it got ejected. But one thing, I mean, sitting in the interstellar, I mean, we don't really know. We don't know what's going to happen to a comet if it sits in the interstellar medium for like 10 gigayears. Like, I think one exciting thing is, how far back was this thing actually sublimating? Because Jenny Bergner and I think we did an episode with you, but Jenny had this awesome theory about Oumuamua being radiolytically produced H2 in amorphous H2O ice, where you get basically, as you get a water-rich ice that travels in the interstellar medium and gets zapped with cosmic rays and stuff, you get these radiolytic H2 products, so radiolytic things like hydrogen and oxygen trapped in the ice, and then as the ice comes through the solar system and heats up, you release that stuff. I mean, it's possible that you have something like that going on with 3I Atlas because it's way older, so it should have actually been exposed to a lot more high energy radiation. So I don't know. And I mean, you could also probably fine-tune things in such a way that you did spend a significant amount of time close to a host star, but then this thing traveled through the galaxy for a while, and then it shed some of its, like as it comes through the solar system, it lost some of the outer shell of the nucleus, and so you're revealing fresh ice from the interior. I don't know. There's a lot of question marks, but we're just spitballing, speculating. But what you said is presumably could be accurate.
It's going to be interesting to find out because these are the beginning questions.
Yeah.
This is where you start. And one thing I wonder about is, all right, as an amateur astronomer, the one thing that I have not seen, I've seen close, but not the way that they're described historically, is a great comet. The great comet of whatever. Now, Hale-Bopp was very, very obviously visible to the naked eye and photographable, and I guess it got sort of close within my period, and that was the 90s. We haven't seen one like that since, but they're rare. But is it possible, since this is fresh material from other star systems, that under the right circumstances and passing close enough to Earth, you could have an interstellar great comet?
I think as much as I would love that, John, because I guess I'm younger than you, but I didn't see Hale-Bopp. Like, I would love that. I think it's highly unlikely. Just because, like, I mean, just think about, like, just seeing a naked eye comet is a pretty rare event, and there are many, for every interstellar comet, there is a very large number of regular comets that we can see even with telescopes. So I think you'd have to be extraordinarily lucky for an interstellar naked eye comet to come through the solar system. But we had to be pretty. I feel like we were lucky for that Atlas caught this guy. So weirder things have happened. So maybe I'm not going to say no.
It'd be interesting to go back and I don't know that we have any data on the movement of the great comets that we haven't traced. Right? I mean, some of them we know exactly what comet it was. Halley's Comet being a famous example, but which was spotted and passed in the 10th century, something like that, long ago. People have seen that comet, and that led Edmund Halley to say that, well, this is periodic. But anyway, it would be interesting if you had enough data on those past comets to infer that that thing was moving really fast and was an interstellar object. But I don't think that exists in the historic record, at least maybe the last 300 years, but not before then, when great comets were noted in the 1600s and all that.
That's a great idea, Don. I would also trust someone like you to do a better job of digging that up than me, because you're
actually, I will attempt to do that. That just occurred to me, so I can't report anything, but I'll take a look at it. But it's an interesting idea that, because interstellar objects have been cooking through the whole time.
Yeah.
And another thing that I wonder about is we have a big meteorite collection on this planet in the institutions and private collections, and laying out in the desert and everywhere, bottom of the ocean, all of it. There's many meteorites. Surely at some point an interstellar one has actually hit. Now there's of course the claim that there was one, but I that doesn't look like a meteorite. But just looking at isotope ratios and things like that in the meteorite collections might yield something interesting at some point.
Yeah, no, I actually have a paper under review that should be coming out soon. I'm slowed down because of Atlas. So I stopped working on the referee report because I wrote this paper, but I was looking into what the population of interstellar objects that hit the Earth should look like. So I am also, just like you, pretty interested in that idea right now. But yeah, I think I think we've talked about this before, John, but yeah, it's possible that there's something in the meteoritic record that was interstellar. I think that the difficulty is, like, we have no idea what it should look like chemically. So I think you'd be more likely to nail down something as interstellar from its orbit than the composition. But I don't know. It's interesting.
It might be. It is interesting. And there is, let me tell you, there is weird stuff in the meteorite inventory. There's one particular fall that isotopically came in as very, very close to the Earth, but it can't be the moon, the origin, which led to a hypothesis, and this is very, very obscure stuff, but it led to the hypothesis that that thing was blasted off of Theia.
Oh, I know what you're talking about. Yeah.
You know what I'm talking about? Yeah. It's like, wow. Yeah. All right. Catching up and taking a look at 3i Atlas and seeing sending a spacecraft. People are all, asking me about that. And it's
of course
we have
the most exciting thing we can do.
It's the most exciting thing we can do. And there's been talk obviously about Oumuamua, but now 3i Atlas to go up and take a look at it. And unfortunately, it doesn't seem to be in the cards for anything we could launch from Earth. I think we've missed the window. We certainly can't intercept it. That window passed over a year ago. But you'd have to catch up to it, and it's moving very, very fast. So you'd have to Parker solar probe that thing, flip it around Venus 11 times or whatever to get it up to the velocity that you would need. However, there is stuff already in space. Tell us about an option, maybe, to go and intercept it.
Okay, so I think John, sorry. I think it's less negative than you're making it out to be. I do not think we have missed the window. So we have this paper coming out that I have this brilliant undergraduate working with me. He is the first author on this paper, which we just submitted like 3 hours. That's why we had to do this call like later in the day, because he submitted it like 3 hours ago, and it's going to be on archive tonight. But it is feasible that we could send a spacecraft to 3i Atlas now. And I highly encourage you to talk to him in detail about this on your show in the next couple of days.
It's on the agenda.
Essentially, option one is you send something from Earth. So we have spacecraft on Earth that were ready to go and visit asteroids, like the Janus spacecraft, who Dan Shears at CU Boulder is the PI of, was shelved. So that was supposed to go do a rendezvous of a couple different binary asteroids. So we have a ready to go spacecraft. If you just slap that on a Falcon Heavy right now, I am not convinced that you couldn't get to 3i Atlas, because we caught 3i Atlas pretty far before perihelion. So if, like, what Hiro is going to show in his paper is that there are trajectories that don't have ridiculous energetic requirements from Earth. that would be attainable, because you don't have to orbit match it. You just have to get close to you don't even necessarily need to intercept. You just fly by it, but it's pretty close, and you'll still, get a rough image of the nucleus, but you'll be able to do a ton of interesting stuff just by getting up close. But even what I think is more potentially realistic is that this orbit, for whatever reason, whatever random reason, it gets a lot closer to Mars than it gets to the Earth. So it's hard to get there from Earth, but it is not that hard to at least fly by 3I Atlas if you started from Mars. Because I believe in October, I think it's like October 3rd, is when Atlas has its closest approach to Mars, and it gets closer than 0.2 AU to Mars. So you don't have to go very far from Mars. And it just turns out that we have a bunch of existing and near end of life missions at Mars that presumably it's not all entirely transparent how much fuel they have left, but presumably have some fuel left that could get to a flyby of 3I Atlas. And it wouldn't take much. So if we went, Hiro showed in his paper, if we sent something from Mars in August, we're talking delta V's of like 4 kilometers per second or less. So it is not infeasible. I think the limiting factor was at first how quickly he could finish writing his paper. So we finished the paper very rapidly, which is very impressive, because you should give him some kudos when he goes on your show, because this is his first author paper ever, and he's a senior in college. So he's very brilliant and very dedicated. But the rate limiting factor now is probably if we could actually get our space agencies collectively together and get moving quick enough, convince everybody who has to say yes to go and send something. But it is not impossible.
Daryl, I am going to make a wild claim, an extraordinary claim, and I can't back this up. We would have to fact check this, but I believe you are the first human to ever have been compelled to go to Dunkin' Donuts by an interstellar object.
I think that's right.
I think you got a good shot at that one, man.
I get a Nobel Prize for that, I guess.
I don't know if they'd give you a Nobel Prize, but Dunkin' Donuts might give you a free cup of coffee.
Yeah, maybe I'll get a free coffee on my rewards account.
All right, Daryl, it's always wonderful checking in with you, and I look forward to the upcoming papers and learning more about this interstellar comet.
All right, thanks, John. This is a great time and great to talk to you as always.
In today's episode, John is joined by Asta Taylor and Tessa Franke. Asta Taylor is a PhD candidate at the University of Michigan's Department of Astronomy and a 2023 Fanny and John Hertz Fellow. Asta is interested in the dynamics of solar system bodies, particularly their non-gravitational accelerations. They are also interested in the formation of giant planets and a myriad of other topics. Tessa Franke is a PhD student studying astronomy and astrophysics at Michigan State University. She is a graduate from the University of Toledo with a Bachelor of Science in Physics with a concentration on astrophysics.
Tessa Franke and Asta Taylor, welcome to the program.
Hi, thanks for having me.
Thank you very much for having us.
Now, you guys have found the third ever interstellar object, 3I Atlas, which recently actually got that name. It was up until just a few days ago being called by its original designation. What caused that? What was the renaming of the object? Is that just by following some IAU convention or something like that?
Generally, yeah. It is traditional that when we name an object like this, we name it after its discoverer. So 1I Oumuamua is a bit of an outlier because it was named by the IAU directly, but 2I Borisov was discovered by Borisov, and this object was discovered by the Atlas instrument, and so it's been named 3I Atlas pending IAU formal designation. I'm somewhat hopeful that we'll get that formal designation because all caps Atlas is not a great name, and it makes it very confusing with the actual instrument, but that's the general naming scheme behind these objects.
So they get designations, and this would also get a designation as a comet, right? It would have a completely separate designation.
Yeah, so I will admit that I am less well-versed in the comet designation. In general, I believe the format is C/year it was discovered, and then just a increasing counter of number of objects that have been discovered in this year. So in this case, it's C 2025 N1, but we will generally be calling it 3i Atlas for the foreseeable future, just because it is significantly more impactful as an ISO interstellar object than it is as a comet.
Now, this object is large compared to the other two confirmed objects. Oumuamua was tiny, and Borisov was relatively small, but this is up to 12 kilometers. Is that what are the constraints on the size of this thing?
So I will say that that is an upper estimate. 12 kilometers in radius is an upper estimate for the size. The thing that we have to be careful with is that the way we estimate the size is we estimate how bright it is. We can calculate that from observations. And then we say, okay, how big does this need to be for a comet-like reflective object to be this bright, given its position and given where the sun is? And if you do that calculation, you find that it's 12 kilometers, which is that implication. Unfortunately, though, if there is a coma, the coma also contributes to the brightness, but not to the size. And so the presence of a coma means that this is a definitely an upper estimate and not a true value. We can also sort of say that this is almost certainly not the real value. I would estimate it's more like 2 kilometers across, which is still large, but not so large as 12. And the reason that we would make that estimation is we can calculate the number density of these objects in the galaxy, and we can calculate how big the object is and how much matter there is in it. And we can calculate how much matter per star needs to be ejected in ISOs in order to make this number density. And the answer is 1/10 of a solar mass per star, which is way too much. The average star is 0.5 solar masses, and that means you get 5 times as much mass in stars. But there's the additional problem that stars are made of gas, and these are made of what we astronomers call metals, which are much less abundant. And so the end result is that in order for it to be 12 kilometers across, you would need to have the galaxy be 200 times more efficient at turning matter into ISOs than it is at turning matter into stars. And we just don't believe that that's possible. And so we can make a much more reasonable calculation of, say, okay, instead of what if it was 100 Earth masses, and that implies an object about 2 kilometers across. And that's a far more reasonable answer. And so we're pretty confident that that 10-kilometer answer is wrong. We don't know what the actual value is, but it's certainly smaller than that, probably around 2 kilometers. That's still very big, but that's what we're working with.
Now, what is the average size of a regular solar system comet in comparison to that?
It depends, and Tessa, feel free to jump in at any time. It depends very heavily on what you define as the average. The vast majority of objects are going to be small, just because there's far more of them. The vast majority of objects we've detected are going to range from, I want to say, like 100 meters up to like 5 kilometers. We've found objects as large as 10, 20, 30 kilometers, but not very many of them. And we know there's tons more smaller than that. There's tons and tons and tons of little dust particles and pebbles scattered throughout the solar system, just because small things are much more common.
Yeah, I would agree. They have a range of sizes, but I think that 1 kilometer to up to maybe like 25 kilometer on the large side. But
now, Tessa, about the hyperbolic trajectory of this object, how does this differ from Oumuamua, for example? It's because this is moving faster and it's coming in at a different angle. How is it deflecting as it passes near the sun? Is it more marked, or is it just going to barely be deflected? Or will this go off in a completely different direction? And what direction in the galaxy did it come from?
yeah, so the comet was coming in from an angle, and it just passed within Jupiter's orbit, and it's at about 4 AU from the sun right now, and it will pass pretty close to Mars at some point in early October, and then it will get pretty close to the sun at about 1.3 AU, and then come back out at a similar angle, similar to the angle that it came in at a pretty high speed. Coming in fast, leaving fast type of trajectory.
Guys, recall it's like 60 kilometers per, that's fast.
Yeah.
Yeah.
Which What
Super
does
fast.
It's
what does
extremely
that
fast.
tell you about the potential age of this object, Aster, that it was moving so fast? Because you remember, Oumuamua was out at the local standard rest. It wasn't really moving
Yeah,
compared
exactly.
to the solar system. This is cooking through. Does that tell you that it's a younger or older object?
That tells you that it's older. The way that the galaxy works is as stars form, they form in the thin disk of the galaxy. And then over the lifetime of the galaxy, they get kicked up into higher and higher orbits and go faster and faster. And so you can calculate for a given galactic potential, so sorry, galactic velocity, what the expected age of this object is. And for this object, from the velocity alone, you'd expect it to be about 10 billion years old. And if you do a more advanced calculation, and I have a paper on this that'll be out pretty soon, hopefully, it's more like 3 to 11 billion years old. That's significantly older than Oumuamua, which, as you may recall, was about 100 mega years old, maybe up to 1.5 billion years. And so the fact that it's moving so quickly means that it is much, much older than Oumuamua. I will also say, by the way, that the direction that these objects come from doesn't matter very much at all. The effect of the stars is to kick them around a lot. And so by the time they've gone a few parsecs away from the solar system, we'll have no idea what direction they're going in, just because the stars will have kicked them around into random, almost completely random directions. And so we can't learn very much from that alone, unless it's very young, like a Oumuamua. And even still, it was just a little bit too old for us to get any reasonable estimation of which system was its parent.
Yeah, you can't really figure out what system, but you can. What could you tell about the type of system? In other words, can you characterize what this thing is made out of? And I find that really interesting because I would definitely would like to see an 11 billion year old rock. You know,
I think we all would.
yes, I think there's obvious reasons for that because that's very early,
Very early.
very early, and that could be some of the earliest material that other than gas that formed.
100%.
Yeah, and that tells you something about planet formation that early.
Exactly.
That's good stuff. What can you tell? So, what can you tell about the composition as observations continue? What can you determine about what this is made out of?
So right now we can't tell much. Our observations are, we haven't had enough spectra of high enough detail to get anything super comprehensive. We can tell it's probably had some volatiles in it because we can see the outgassing, the coma, which we presume is from outgassing. But we'll have to see as it gets closer to the sun if that gets more and more active. Other than that, I'll actually leave this over to Tessa, who has doing some observations at this object right now that will hopefully be able to give us some insight there.
Yeah, for sure. I mean, like, it's speculated that interstellar objects are ejected through a gravitational interaction between, like, the larger body, like a planet or a sun, but it's really difficult to say based on what we know right now, where the origin of the object and what it's made of at all. But definitely, like Astor was saying, as we're able to get better and better spectra, as the volatile materials are starting to evaporate as they get closer to the sun, and we get spectra of that, we'll get more information about what type of materials we're seeing, and based on the gas that the comet will be ejecting. Yeah, like I said, it's difficult to say right now, but it's kind of crucial in the next couple of months to take these observations and to collect spectrum of the object as it gets closer and closer to the sun.
We're also very hopeful, of course, for JWST to take a look at this. That would be a massive, massive boot to take a look at this as it gets closer to the sun and as this coma becomes more active. There have been some discussions of this, and so I think we're going to be able to get something. We can also, even with these low resolution spectra, we can still see that it's got a kind of red surface, somewhat similar to Borisov. So I'm expecting it to have a composition somewhat similar to Borisov's, which is volatile rich, but a little bit weighted. I'm trying to remember which way it goes. There's a little bit more CO2 than there is H2O in Borisov. And so I would not be surprised if this object had something similar. I did not remember which way that went.
Yeah, that's correct.
And so I would not be surprised if 3I had a similar composition, but we'll have to wait and see as the outgassing gets more significant and as more spectral observations are taken when there's actually a significant coma.
Yeah, and to add on to that, you were right. It does have a more significant CO enrichment relative to the H2O, and that is, that's a bit different than our typical solar system comets, right? because they usually they're more rich in H2O and have relatively less CO, I think.
Now, you're doing observations, Tessa, tonight, as in this is very much ongoing. Tell us about what you're doing this evening.
Yeah, of course. So tonight and over the next 2 nights, I believe, if I have that schedule correct, but in my mind. But these are some follow-up observations that we took, or we're going to take after we took some images and spectra last week on July 2nd. On Tuesday, I believe that was Tuesday. We took some spectra, low resolution spectra with the SOAR telescope, which is in partnership with Michigan State University Department of Physics and Astronomy. And we took some data last week, but now we're doing some follow-up this evening, actually, taking some spectra. We're hoping to take spectra, but it's not for sure since we're pretty close to the moon right now. But it is really exciting to see what we'll get. I think the best bet is just to take some images in some of the red bands and to see if we can get some better to calibrate some astrometric data rather than getting spectra tonight because of the uncertainty with the moon. But it's been pretty cool to see how this all shapes up with the SOAR spectra.
Well, thankfully, the moon moves and moves fairly quickly night to night. So,
yes.
If not now, what other future observations are planned by your team?
We don't have any currently planned, but we do have the following night. So we have tonight and Wednesday night for observations scheduled so far. And then if the moon messes up our plans a bit tonight, I think we will probably do some follow-up in the next couple months or even weeks, since time is of the essence, to do some exposure over multiple nights. That will be better to constrain spectrum data.
There are also going to be joint spectral and photometric data taken in August or November, at least if the proposal goes through, the MDM Observatory in Kitt Peak. And then I happen to be aware that there's some ALMA proposals being submitted. There's some JWST proposals and Hubble proposals for emergency observations being submitted. And so there's a lot of plans, but not both from our team, which I believe Tessa is on that MDM proposal.
Yes.
And from a lot of other teams looking into getting observations of this thing from now until November and December when it becomes undetectable.
Yeah.
Now is the time where it starts. Now that the first paper's out, now we get to see the flurry of snowflake papers coming down like snow.
Exactly.
And as people find out new stuff, and it's always fun to watch that because, you look on archive every day and, every few days paper shows up as people try to constrain it. Now, reddening, Aster, and that also is an indication of age, right? In other words, reddened objects, that's the interstellar medium doing that. Isn't that correct?
To some degree, yeah. So we expect that the ISM is going to help redden these objects as it passes through. And so that will indicate that it's relatively old. Of course, we don't have a lot of ISOs. We only have 3 of them, and we're not quite sure what their composition looks like. And so the thing that we're going to run into is it's very hard for us to determine, is this reddening definitely from the ISM, or is it red because this object is just red? And that's what these objects look like. And so we are doing our best to try to understand how these objects work and how they get older and how they change as they pass through the interstellar medium. But it's really a difficult to constrain question. And there are also even more sort of, I'll say, exotic suggestions. Like, I don't know if you've had Daryl Seligman on before.
Oh, many times, yes.
I don't know if you've ever talked to Jenny Berkner, but she and he had a paper 2 years ago now where they showed that as an object like Oumuamua moves through the interstellar medium, cosmic rays can produce H2 in the surface. And then the water itself just changes phase, which releases the H2 and causes the non-gravitational acceleration. And so you can have these sort of weird exotic effects of moving through the ISM that are very, very difficult to constrain and very difficult for us to understand since they only occur in the ISM itself.
Now, the path again, back to that, Tessa. The closest this is going to get to a planet in the solar system is Mars, right? This will not pass anywhere near Earth, but it will pass by Mars, correct?
Yes, that's correct. The object will pass within, I believe it's 0.19 AU, which leaves a lot of great opportunities to do some observing with some missions that are already there, and also to perhaps directly image the object if we're able to pull resources and take advantage of that close approach.
I think that's one of the coolest aspects of this,
Mhm.
in that we will be able to serendipitously observe an interstellar comet with a probe in orbit of Mars. I don't think that happens very often.
Definitely not, yeah.
Yeah, that's a new one. Now, the brightness of this object is very, very dim, obviously, but not necessarily dim for an asteroid, or an interstellar comet or object. Is this within the range of a very well-equipped amateur to also do observations?
I think so, yeah. I believe that it may be visible. I think that even a amateur astronomer was a part of some of the follow-up observation. I may be wrong. Aster, correct me if I'm wrong, but I believe that.
Going to be completely honest, I have no idea what the magnitude limit an amateur astronomer can see to is.
Yeah, I'm not sure either, but
It's
I'm
currently magnitude 15,
yeah.
which is pretty dim, and I'm trying to recall the limiting magnitude of a telescope of a given size. I think you're going to need a pretty big telescope, certainly at least a foot, and very low light pollution. But you can do it with the meter-sized telescope, but those are not exactly amateur astronomer quality. I'm going to unfortunately say that I do not know the answer. My guess is it's in that bounds where maybe is a possibility. I'll also say that right now it's going to be very, very hard to make observations, just because it's in the middle of the galactic plane. And so all the detections that we've had to do so far need very complicated algorithms to try to remove background stars that amateur astronomers will not necessarily have access to. It's just very, very difficult to separate this object out from its background. That's making observations difficult with even, with small or large pixeled professional quality instruments, and it's going to make things even harder for amateur astronomers who do not have the resources that we would.
Mm-hmm.
Yeah, that is a problem. Well, anybody
Yeah.
that's looked at the Milky Way with a telescope, that's very, very, very dense. And picking it out, which is amazing it was discovered in the first place right now, at this time, because that's hard for even you astronomers to do. Now, what was the circumstances of the discovery? In other words, what went into finding and picking this out? What happened?
So Atlas, the instrument, is an all-sky survey looking for asteroids and comets. And it serendipitously, as many of these surveys do, found this object. It has very good background subtracting algorithms. And so it managed to pick it out and got astrometry over the course of a few days. And the orbit fit to that astrometry has an eccentricity of 6, which is just really ridiculously large and is absolutely inconsistent with a solar system object.
Yeah, isn't the threshold 1?
The threshold is 1.
Yeah.
And there's uncertainties on that number, right? But at plus or minus 2, still too big.
Mm.
And so the consequence that we ran into is that we found it like that. And then we have follow-ups to further constrain the astrometry to get better and better and better observations. And that ends up in the discovery itself. This is also sort of how we found Oumuamua and Borisov, although Borisov's a bit of a weird story. But Oumuamua was found in a very similar way, using the Pan-STARRS instrument. And we're expecting that this is going to be the primary way that we find ISOs in the future, is these large-scale surveys looking for asteroids, amongst other things, finding an asteroid, fitting an orbit to it, and finding that that orbit is not at all equivalent to that of a solar system object. And then with that, we can start doing follow-ups and really nail down that it's definitely an interstellar object and take further looks at it.
The Vera Rubin Observatory has come alive and is now making observations.
We're all very excited about it.
Very timely indeed, and that's my next question, because they turned it on, looked at one spot of the sky, and discovered over 2,000 asteroids in a week.
Yeah, very timely occurrence.
I mean, it was just stunning.
I believe it was 10 hours at observation.
Yeah, it was just mind-boggling.
Yeah.
Of what use will Vera Rubin and that survey be in trying to characterize this new object?
Quite a bit, obviously. So actually, I'll say not for this new object. Rubin is not a targeting instrument. It is not going to be looking at 3i and trying to figure out its properties. It is primarily a survey instrument. And I don't know the exact fraction, but it's at least 90, as large as 100% of its initial 10-year time is devoted to the legacy survey of space and time, which is just a truly massive all-sky survey of huge amounts of data every night, finding transients like this object, finding transients in the extragalactic, in the galaxy, in outside the galaxy, and just really getting a very wide survey to pretty deep levels. That being said, it's a big telescope, but we're not going to be devoting it to looking at this object. The big thing that Rubin is going to be doing for us is finding a lot more objects like this. Depending on the estimates, somewhere between as many as 100 over the next 10 years, as many as 10 over the next 10 years. We don't really know, but that's what we're expecting out of Rubin as it comes online, is to find a lot more of these. And it's a very happy coincidence that we found 3I directly after Rubin came online. And the 2,000 objects is just a proof of how powerful this new observatory is and how good it is at finding objects like this.
I found it very poetic that, the telescope originally was the LSST before it got named. And now the survey comes out as LSST.
Yeah. That was on purpose.
Yeah. I'm excited about it because you're right. This is going to find many more objects. And for asteroid mapping, it's
absolutely
just shocking. Very, very fine instrument. Doing observations in a way that we really never did anything quite like this. I mean, we have fall sky surveys and stuff, but nothing like this.
Yeah.
And it's very exciting that it's
nothing to these magnitudes.
Yeah, and the success it's already seeing is, it reminds me of the Webb Space Telescope. It was just stunning. All right, so it was originally thought when this was discovered that maybe an asteroid, but then a coma was spotted. What happened there? That one observation said, well, I didn't see anything. And then another observation said coma.
Comae are really hard to find, especially one this week. This coma is not very big. It's not coming out in a tail. It's just a sort of fuzzy cloud around the object. And in order to detect that, you have to have a telescope with small enough pixels that you can make out the difference of it's fuzzy right here and it's not fuzzy right next to it. And I think a lot of the initial observations are designed for large field of views and do not have the pixel resolution necessary to pull that out. So it's really just an observational constraint that it's really hard to detect a coma. And as we get better and better telescopes, not always say better and better, as we get telescopes with more and more pixels per square degree looking at this thing, we'll be able to see more and more of that coma. And hopefully we'll eventually get to the point where we can determine the difference between the central object and the coma, because you need to be able to do that to measure how big it actually is.
Yeah, and like we said earlier, like the field is very crowded in its current position. So being able to pick out the coma from all of that, it requires some reduction. And there is a good image inside of the discovery paper, the Daryl's first author paper that he just submitted and is on archive. There's a good image from the Canada, France, Hawaii telescope that you could see the activity a bit better than when you're just looking at the crowded field.
And you can compare that to the Atlas image, which is just, you can't see any activity in that. It's just a dot amongst the various other dots.
Right.
And so you really need this sort of high precision from a larger telescope that's designed for focusing on a single object, from something like CFH and something like that, to actually be able to detect these things.
Now, will that angle we're seeing it in, is sitting in the galactic plane, will that get better as it moves through the solar system? Will you have, the ability to take better observations if it moves out of that?
Yeah, it certainly will. And then especially after it moves away from its closest approach with the sun and it's like at a higher solar elongation, it will be easier. Like, I guess from Earth, it will be easier after that period, but also from the perspective of space telescopes as well. I don't know if Aster has anything to add to that, but
we'll get a lot better observations when it moves out of the galactic plane, and then we'll lose observations and then moves behind the sun, and then we'll get some we'll just keep on gaining them and losing them as the moon moves around. And then after it passes the sun, unfortunately, it'll be behind the sun for its closest approach. So we can't make any observations then.
Right.
But after its perihelion passage, we should be able to get some decent observations as it leaves the solar system and then eventually just disappears. There is some discussion of turning some of the telescopes on Mars satellites to look at this object when it's at perihelion, because Mars will not be behind the sun. So that'll be very cool, but we'll have to talk to NASA, and somebody else will have to talk to NASA and see if we can get that working.
Now, this object is really, as we were talking, really moving through here. So at the speed that it's at, I don't see how we could catch up to it to get a closer observation. So is there any possibility, any plan, or is this just going to unfold too fast before you could plan something? And would it be useful in the future to build a reactive system in space? And I know there's such a thing as for asteroids is in the works for interstellar objects. In other words, can we put something out there ready to go when something is detected and get samples of it or something along those lines?
Yeah, so this object is obviously too fast, and we would not have the mission parameters. We have to have, we're working on a mission for years already to be able to catch this. There is some discussion of showing that there could exist such a mission that could have caught this object, but that mission does not exist right now. So there's no way it's going to be caught right now. But like you said, there have been people talking about doing things like Comet Interceptor and other missions like that, looking for opportunities to go out and grab comets when they get very close to the Earth. So there's been discussion of a mission like that for this object. And it's quite possible that if there's a fourth ISO detected while Comet Interceptor is online, we may be sending Comet Interceptor to 4I instead. That's up to the ESA and all that. But there's been a lot of discussion after Oumuamua that we should develop a mission like this. The funding just hasn't been there right now, and this mission has never been approved. I think we should do something like that, but that's sort of the problem we run into. Is there's a lot of things that astronomers think we should do, and that the funding just does not exist to do. And so it'd be very cool if we could do it, but we're in a tricky situation with, Congress and NASA have not approved the budget necessary to build that mission.
Now, my last question for today is this. With Oumuamua, obviously there were very odd attributes to it that led to, increasingly spiraling out their theories as to how to explain it. But yet Borisov, nothing special, as far as anything peculiar. It's just an interstellar comet, basically. Mm-hmm. Is there anything in the observations of 3I that is unusual and difficult to understand? Or does this appear to just basically conform to everything you would expect from such an object?
So far, it looks like a normal comet. We have not seen anything that I'm not aware of anything in any of the observations that is difficult to explain by saying it's a comet like Borisov. We don't have a ton of data, so we may find more mysteries as we go into it, but it is certainly much less weird than Oumuamua, and currently seems entirely consistent with being another version of something like Borisov. Would you agree with that?
Yeah, I would totally agree. And in the coming weeks, as we're getting more data, as 3I goes through the system and gets closer to the sun, maybe we could see something interesting happening with the tail, or as it develops and some of those materials start to evaporate. But so far, it's looking pretty standard. I agree with Aster.
All right. Thank you both for joining us today, and I wish you great luck, and I can't wait to find out more about our third discovered and confirmed interstellar object.
Thank you for having us.
Absolutely. Thank you for having us, and keep an eye out for both of our papers in the, I don't know what your time frame is, Tessa, but in the coming weeks, for me at least.
Yeah, for sure. Me too. In the coming weeks, yeah.
Yeah, so it'll be very exciting.
Yeah. Thank you.
Thank you very much.
Dr. Avi Loeb, welcome back to the program.
Thanks for having me. It's a great pleasure.
Dr. Loeb, now we have a new interstellar object, I3 Atlas, and of course there's much mystery surrounding it and intrigue and a lot to learn, a lot to learn with this thing. But the one,
Well, that's the nature of science. Science is fun because it's an opportunity to learn something new. And unfortunately, many practitioners of science prefer to rely on what they already know in interpreting new data.
I think what intrigues me most, and I want to get your view on this before we get into what I'm really interested in, which is intercepting it. But before we get into that, the age of this object, inferring based on its speed, its motion, which is much higher than Oumuamua was and Borisov, both suggesting, at least in a typical framework, that it is very, very old. That this is, whatever this material is, whatever its nature is 7 billion years old. Do you agree with that interpretation of this object speed?
Well, I wrote a paper with my undergraduate student about that. And what we showed is if you extrapolate the trajectory of 3I Atlas, the new interstellar object discovered on July 1st, 2025, if you go back in time, you find that its trajectory within the Milky Way galaxy spans the range of heights above the midplane of the Milky Way galaxy that is associated with old stars. So it belongs to the thick disk of stars. If you just continue its trajectory back in time billions of years, you find that, yeah, it could have originated from an old star. This is not a direct measurement of the age. It's simply the fact that the velocity of this object is consistent with the thick disk of stars in the Milky Way galaxy. But just imagine that it was propelled by something else. For example, and we mentioned that in the concluding paragraph of our paper with my student Shokruz Kakarov, we say that any such object, if it was produced near a star, irrespective of the mechanism that made it, was associated with some ejection speed. Okay, so when you're saying the speed is high, therefore it belongs to the thick disk of stars, that ignores the ejection speed. If you were to eject it from a young star with a high speed, it would look just like 3I Atlas. So when people make reports to news reporters, about this object being old, that is assuming that the ejection speed was small relative to the speed that we measure for it. And therefore, it should have inherited a high speed that we often find in old stars. But it's not an age measurement. And also, it assumes that the ejection speed was small. You have to keep that in mind. And not to speak about the possibility that it's not a natural object, which we will get to.
Oh, we will. But again, on the age thing, so simply because something is moving fast calls into question the very, very, actually almost stereotypical interpretation of the motion of objects in the universe, is that because it's moving fast, as you say, it inherits motion. And therefore, since it's moving fast and it's also been swinging around the galaxy for however long, getting gravitationally affected by everything, that speed means age. But no, it doesn't, because if you're sitting in a race car at the Indy 500 or something like that, well, it's going fast, but only because of its own volition, not its age. It was probably brand new, right?
Well, that's one way to look at it, but also imagine that the car has an ejection mechanism by which it can eject you out of the car at a very high speed, even if the car is not moving at all. How would you know from the speed by which you are moving whether it was a result of the ejection mechanism or the speed of your car? So the only way to say that it must be old is by assuming that the ejection speed from the original star was very small compared to 60 kilometers per second, the speed by which it entered the solar system. But we don't know that.
Can you have some weird dynamical thing, like a binary star system, for example, that could fling something out at much faster velocities than what we're assuming here?
Oh, yeah. So in fact, I wrote a scientific paper that was peer-reviewed, published, that suggests that the most likely ejection of interstellar objects is actually with this kind of a speed. And the mechanism was very simple. The most common stars are dwarf stars. They have about a tenth of the mass of the sun and a size about a tenth of the size of the sun. And that means that they are very dense because the mean density of a star would be the mass divided by its volume. The volume scales like the size cubed. And since the size is a tenth of that of the sun, the density of the most common stars is 100 times the average density of the sun. And it so happens that the average density of the sun is just below the density of rock. So if you take the Earth and bring it close to the sun, the tide, the gravitational tide from the sun will not be able to disrupt the Earth before it gets into the sun. However, if you take the Earth and bring it close to the most common type of stars, a dwarf star, the high density of the star would mean that as you bring it close to the surface of the star, the tide would be stronger than the self-gravity of the planet. And so what would happen is the Earth would be spaghettified. It will turn into a stream of molten rock. This half of the mass in this stream of spaghettified Earth, this is called the tidal disruption event. So half of the mass that is being disrupted by this process will get injected to interstellar space. And now when I realized that this mechanism could happen, I immediately calculated what is the ejection speed that you expect. Turns out that if you take the most common type of star and you take a planet like the Earth and spaghettify it close to that star, half of the mass of the planet will be ejected at, guess what, 60 kilometers per second. Exactly this speed. Now, the reason I wrote this paper was in reference to an interstellar meteor that was reported by the US government satellites back in 2014. And that one had roughly 60 kilometers per second relative to the local standard of rest of the Milky Way galaxy. So I wanted to find a mechanism, natural process that would give this high speed. And this is a very plausible scenario because I'm talking about the most common types of stars, and all you need is some rocky material to be sent close to the star. How can you get that? Well, if you have a giant planet like Jupiter and then it gives some push to the gravitational push to the rock in the direction of the star, that can happen because there is a mechanism that actually increases the eccentricity of an inner planet thanks to the existence of a giant planet outside of its orbit. And this mechanism would bring Earth mass planets close to dwarf stars, in which case you will get interstellar rocks flying at 60 kilometers per second. And now what would astronomers say? Well, if they see such a rock at 60 kilometers per second, they say, oh, it came from the thick disk. It must be very old. No, it can be young and was ejected at that speed.
Need to really see the material, and we'll get to that in a minute. However, I want to ask a sort of oddball question. So we know of stars that have very, very high proper motion. It's in relativistic high proper motion, very fast moving stars due to interaction with supermassive black hole that flings them at extremely high speed. What is the upper end that you can envision for an interstellar object's speed? Could we see one much, much faster than the already fast 3I Atlas?
So here again, I published two scientific papers on stars that reach close to the speed of light as a result of them being near two supermassive black holes. So, where each galaxy has a supermassive black hole at its center, and when galaxies merge, and that is a common occurrence, that's how galaxies grow in mass, by mergers. So every characteristic time, which is a sizable fraction of the age of the universe, you get a merger. We will merge with, the Milky Way will merge with the Andromeda galaxy, that is our sister galaxy next door, within a few billion years. And the point is that when two galaxies like that merge, the black holes at the centers come together and they form a pair that tightens up as a result of dynamical friction on the background stars and gas. And eventually the two black holes might come close to each other. And the stars that are in between the black holes can be ejected at a speed of up to the speed of light. If the if the pair of black holes is relatively tight. And so I calculated in two papers that were published about a decade ago, what would we expect for the population of relativistic stars in the universe? Because these stars will definitely escape from their host galaxy and will fill up the intergalactic medium, the medium in between galaxies. And so there is a population of stars moving at up to the speed of light, if you can believe it, right now through the universe that originated from black hole mergers at the centers of galaxies. And I calculated the population, how many of them do we expect per unit volume, and concluded that it would be really difficult to detect them because, it's difficult to detect a single star, even if it's bright, at intergalactic distances. But if you are living on a planet close to such a star, and you are ejected with the star at close to the speed of light, that would make an amazing journey through the universe because you will cross your own galaxy within, tens of thousands of years, and then you will get to intergalactic space and you could see other galaxies along the path. That's the best way to take a trip at close to the speed of light that I can imagine. It would be very difficult to construct a spacecraft that reaches the speed of light, but nature does it for stars that happen to be close to a binary black hole system.
Dr. Loeb, what occurs to me is perhaps something very apocalyptic. When you have two galaxies like Andromeda and the Milky Way merging, and those two black holes come together. Now, in a binary star system, a very close binary star system, they can rob each other of energy. They can rob each other of gases. They can distort into ovals towards each other. Can you do that with the event horizon of a supermassive black hole when you get two of them nearby each other, pulling on each other? Can the event horizon not be a perfect sphere?
Oh, definitely. It gets distorted, and eventually the two event horizons join. And then they obtain an area that is bigger than the sum of the areas of the two. The fact that black hole mergers lead to a sum of the areas that is bigger than that it leads to a total area that is bigger than the sum of the areas of the two black holes was a result obtained by Stephen Hawking in the 1960s. And based on that theorem that he derived, Jacob Bekenstein suggested he was a PhD student at Princeton, and he suggested that maybe black holes have entropy because that reminded him of the fact that entropy always increases according to the second law of thermodynamics. And his mentor, John Wheeler, said that the idea is crazy enough to be correct. And then Stephen Hawking heard about the conjecture that Jacob Bekenstein made, and he said, that makes no sense, and I will prove it wrong. So he started to do quantum mechanical calculations to demonstrate that black holes do not have entropy. And when he got the results, he realized, actually, they do. And because of that, they have a temperature. They have entropy and temperature, and they radiate radiation. And as they lose mass or lose energy, they eventually become smaller, and then they evaporate even faster. And they explode. They disappear. This is called now Hawking radiation, and it's the most important scientific result derived by Stephen Hawking. For astrophysical black holes, the evaporation time is completely negligible. It's much, much bigger than the age of the universe. The only black holes that can evaporate during the age of the universe, have a mass that is smaller than 3I Atlas, the new interstellar object. They need to have a mass of the order of a few times 10 to the 14 grams. And that is the mass of an asteroid that has a size of just a fraction of a kilometer. Such black holes, if they were made in the Big Bang, would show Hawking evaporation. So astronomers looked for any radiation that could have been emitted by exploding black holes. We haven't seen any. But it's possible that the dark matter in the universe is made of primordial black holes that are more massive than this limit, so they didn't disappear. They still exist, but they continue to evaporate, so we can search for the radiation coming from them. Just to give you a sense, if we are dealing with a temperature, Hawking temperature of about that of the sun, the surface of the sun. We are talking about a black hole that has a mass that is quite large, similar to that of the moon. And the amount of luminosity that such a black hole produces is around, tens of nanowatts. It's tiny. As you make the black hole smaller, then the luminosity gets higher, and eventually you get it to explode in a gamma ray flash. But we haven't seen any such flashes. Even if the dark matter is made of those primordial black holes, we didn't see any signature of them. And there is a range of such black holes in the asteroid mass range that is still allowed. It's not ruled out by existing data. And so it's possible that the dark matter is made of primordial black holes. And if so, we could potentially sometime in the future detect the Hawking radiation from these black holes.
It would be one of the more elegant answers to what is dark matter, because other than that, it's a particle or something like that, or something that we don't understand at all. So it just starts going further and further out there. But at least...
yeah, but you are correct that in principle, it's a very simple solution. The problem is, how do you make them? And what you need is, that within the horizon of the universe early on, the horizon is the distance that the light traveled since the Big Bang. So when you go back in time, that age of the universe was smaller and smaller as you approach the Big Bang. And if within the volume associated with the cosmic horizon, you have a mass density or energy density of radiation that exceeds a critical value, then that region would collapse upon itself to make a black hole. But as of now, all evidence indicates that the kind of inhomogeneities that existed in the early universe were at the level of 1 part in 100,000. And what you need to do here is enhance them to a level of order unity in order for primordial black holes to happen, so to be produced. And this kind of enhancement is not easily arranged. You don't want to make it easy, because then you will convert all the mass content of the universe into those primordial black holes, and we don't see that. I mean, we know that the cosmic microwave background dominated the mass budget early on in the universe. So we want to convert a tiny bit of the radiation into black holes, but then it becomes a problem of fine-tuning. How do you arrange for a process that will just make the amount of dark matter that we need, but not overshoot and produce much more of than that? And it's not easy to arrange for that. We don't know of a process that will do that. And so I would argue that actually some elementary particle being the dark matter is a more plausible explanation.
So a weakly interacting massive particle, essentially, the WIMP.
Well, that was... So since I started astrophysics 40 years ago, that was the popular view, that the dark matter may be a weakly interacting massive particle, and in particular, the lightest supersymmetric particle. Supersymmetry is a new symmetry of nature that was proposed, and people thought it's very natural, and various ideas that were floated about it gave whoever proposed these ideas honors, awards, and recognition, and everyone said, yeah, it probably exists, and the dark matter is the lightest supersymmetric particle that cannot decay into anything else, because it must be stable if it's the lightest. And then the Large Hadron Collider searched for supersymmetry in the natural range of parameters and didn't find it. And it didn't find dark matter either. There was no particle detected that could account for dark matter. And, that is something really fundamental about science that you have to understand, that, irrespective of what is the popular view of the mainstream is wrong very often. And the only way for us to figure it out is by collecting data that will test our ideas. Now, it sounds like common sense, straightforward. Of course, we need data to check our ideas, because the range of possibilities is far greater than the one possibility that is realized in nature. I could have had $1 trillion in the bank. I could have had $1 billion in the bank. I could have had many different amounts of money in the bank, but I do have a very specific value, and I have to build my lifestyle based on that. And so, of course, it could have been the case that supersymmetry existed in the natural range of parameters, but reality may not respect that, may not satisfy this symmetry. So it doesn't matter how many likes an idea gets on social media or within the mainstream of science. It is the guillotine of experiments that chops the head of ideas that are not describing nature. And that has to be respected. Now, why do I say has to be? Is because the mainstream of theoretical particle physics for the last 40 years, since the time I started astrophysics, had a very popular theory called string theory, imagining that there are extra dimensions and we can unify quantum mechanics and gravity if we just follow the math. And after 40 years, the math did not bring us to a unique theory that makes predictions that can be tested by experiments. And so that violates the very fabric of scientific knowledge, where we test ideas by experiments, and if an idea cannot be tested, then we cannot really know whether it's real or not, and therefore we are left in the dark. So you can work for 40 years on a mathematical idea and demonstrate that you are smart. It's sort of like doing intellectual gymnastics. But if you really want to discover something about nature, you need to seek the contact with experimental data, because without it, you're doing mathematics, you're not doing physics.
It reminds me, speaking of revising one's priors and revision, it's the steady state universe. There were physicists that worked their entire career based on the steady state model of the universe. And I believe certain ones like Fred Hoyle never did give up on it and was trying to argue it till the end that, there had been no Big Bang.
Yeah, well,
and now clearly this is not the case.
It's not the case. And, it's really important to recognize when the data does not support your theory to back off your theory. I mean, that was the big mistake of the Vatican, when Galileo Galilei looked through his telescope and said, well, I see these moons around Jupiter, and it implies that not everything revolves around the Earth. Now, the Vatican said, we don't want to hear you. We don't want the public to hear you. We will put you in house arrest. If instead they would have said, okay, that's what you say, but we will build a better telescope, look at the sky and prove you wrong. If they adopted that strategy of saying, we believe that you are wrong and we will show it by collecting better data, then they would have corrected course very quickly. Instead, what happened is, 350 years after Galileo died, they announced in 1992 that he was right. And that was very embarrassing, because it was 20 years after humans landed on the moon. So they couldn't really deny the fact that when you look at Earth, it moves around the sun. You can see it from a distance, from spacecraft. And what's the lesson from this? The lesson is that once you have good enough data, you should back off. And the best way to decide about wrong or right ideas is not by arguing that, I did very fancy mathematics to prove the point, or that I'm very smart. That is not really something respected by nature. The Earth revolved around the sun for 4.5 billion years before the Vatican even existed. And it continued to revolve around the sun after the Vatican said no to Galileo. It doesn't really matter what people on Earth say. They can fool themselves. They can be sure that they are the smartest in the universe, while they have a neighbor that is smarter than them. They can ignore that possibility. And, it's a self-fulfilling prophecy. If you're not seeking data, you will never show yourself wrong. And of course, that is the strategy adopted by the Vatican at the time of Galileo. But it's not a good strategy in the long term, because someone else will get more data. Eventually, humans go to space and they see that the Earth revolves around the sun. So what are you trying to prove? I mean, in 1992, you have to say, I was wrong, Galileo was right, okay? So you are just delaying the rate by which humanity is gaining knowledge about its physical environment. We either have a neighbor or we don't have a neighbor that is intelligent as we are or even smarter. It has nothing to do with what we say within our home to our family. We can ridicule the notion that we have neighbors. We can look at many houses on the street and claim that they have only microbes, which is pretty much the opinion of the mainstream of astronomy right now. The highest priority is to build the next generation space telescope, the Habitable World Observatory, that will search for the molecular fingerprints of microbes. And that will be at a cost of more than $10 billion. At the same time, no priority is assigned to funding the search for intelligent beings out there. And the argument is, imagining that these houses on the cosmic street that are just Earth-Sun analogs, and there should be billions of them in the Milky Way galaxy alone, these billions of houses only have microbes. We don't know. It's an extraordinary claim to imagine that something like us exists as a resident in those houses. And therefore, we should invest in looking for microbes, because microbes must be much more abundant. But good luck if you want to look through your window and search for microbes in other houses on your street. That is a very challenging task. However, if you have a neighbor, that neighbor might come to your front door, or that neighbor will construct something in the backyard that you can see from a distance, or you will get a tennis ball that was thrown by a neighbor. In all these examples, or you get a package in your mailbox, that's another possibility. In all these examples, the signature is very clear. Even though intelligent residents might be much fewer than microbes in this street, you will have an easier time to find them. And all I'm saying is, we should hedge our bets. It's easier to find intelligent beings than it is to find microbes. Microbes might be much more abundant. We should do both searches with comparable level of funding, because we don't know where the discovery will come from. And we should be open-minded to the possibility of discovering intelligence beyond Earth, because it may be out there. If we make it heresy to discuss that possibility, then we will just maintain our ignorance. But it doesn't mean anything for our cosmic environment. It will still exist.
My reaction in 1992 to the Vatican's apology to Galileo was, you people have been running serious astronomical telescopes and experiments for a century. The Pope has 2 observatory domes on his palace at Castle Gandolfo, and you're just now getting to this? You would think.
Yeah, I mean,
you would think that they would have been a little bit more efficient on the apology.
But this is not my only concern. I'm looking at science, and I'm really concerned that there is a lot of resistance to thinking outside the box, to walking outside the beaten path. I bring it up in the context of the search for intelligent life elsewhere beyond Earth, because, when young scholars, students, fledgling scientists are looking at the response of senior members of the academic community to a discussion about this subject, they are really afraid of going in that direction because they're worried about the prospects for jobs. And that suppresses innovation in science. That's the best recipe for maintaining our ignorance. And the public really cares about this question. It will change the future of humanity if we find another civilization as intelligent or more intelligent than we are, because they may know better physics. By the way, it will give us a shortcut to resolving questions of how to unify quantum mechanics and gravity. They may know the answer. It may feel like cheating in an exam if we find them without us finding the answer ourselves. But if it saves us a lot of time, we just had 1 century of modern science and technologies since the discovery of quantum mechanics and the general theory of relativity. So they may have had much more time. They may have had bigger brains that allow them to make progress much faster than we do. So altogether, it's an opportunity for us to grow. And also noticing them may bring people together, because we would feel that we, as members of humanity, are all in the same boat, the Earth, and there is someone else out there. And so we shouldn't fight each other, kill each other over territories here on Earth, because there is much more real estate in interstellar space. It's really narrow-minded of us. It's like kids fighting in a sandbox, and then realizing an adult comes to the scene, and they stop fighting and realizing, wow, there is something beyond this sandbox that we are fighting on. And that could be really an opening chapter in the future evolution of humanity. I see that as extremely important. So then, just like the wager that Blaise Pascal, the mathematician philosopher, made, he said that we don't know if God exists or not, but the implications would be huge if God exists. And therefore, we should consider that possibility. And I say the same thing about aliens. I say the implications would be huge. We cannot dismiss that possibility without collecting data, without following the scientific method. And by the way, the scientific method, that is often missed by not just some people in the public, but actually professionals practicing science. They miss the point. They ban discussion on some questions. The scientific method is all about allowing all questions. You can ask any question you want. You can think about any possibility you want. But the way to resolve whether that possibility applies to nature is by collecting data and ruling it out or ruling it in. It's just like a detective operates. So for that, you need to get experimental data, so you better ask questions that can be addressed by experiments. If you just spend 40 years on mathematical gymnastics without any contact with experiments, you're not really following the scientific method. You want to check whether you are going on the right path. It's sort of like, taking a herd of people with you, shepherding it, and leading it along a path and saying, this is the right path. But if it turns out to be the wrong path, because nature has nothing to do with the idea, the direction that you're taking, you can take the entire herd with you and you will be misguiding them. However, if you allow some members of your herd to examine other paths, other roads that were not taken, they might actually find the correct path that leads you to the resolution of how to unify quantum mechanics and gravity. So in the context of science, we should not limit the questions being asked in general or any conjectures we make. We should focus on those that can be tested experimentally. But the scientific method is about figuring out which option is the correct one based on data. And that requires investing time and money in the search for the data. So you can't just say it's an extraordinary claim to imagine something like us and then put zero funding federally to the search for extraterrestrial intelligence. That makes no sense because you didn't allow for this possibility to be falsified. So how do you know? If you didn't seek the evidence, how do you know that it's extraordinary? You don't know because you didn't put money into it. So let's put equal amount of money in the search for microbes and the search for intelligence. And then we can say something after a decade or 2 decades. And, if we don't find anything, we will not be at any different place than those people who argue that supersymmetry exists or that the dark matter is the lightest supersymmetric particle. They were wrong. We invested the money, we didn't find it. Nobody blames them. That's the way science is done. But claiming that it's an extraordinary claim to imagine that there is something like us or better out there, I think without funding it is non-scientific.
I think the problem is that there's a bias, and we see that with back in 1993. NASA actually had funding for a time, very short time, for SETI research, radio SETI, looking especially for a signal from alien intelligence out there somewhere. And it became political, and a congressman got the funding canceled, talking about little green men and all of this and how it was waste of money.
I know the history. Yeah, this history is really irrelevant because we are now so many decades after that. And my point is simple, that the search for radio signals is just like you say, okay, on the cosmic street, I may have neighbors, and let me wait for a phone call from one of them. So you are waiting for a radio signal that will communicate a message to you, just like as if you were waiting for a phone call. You are a passive observer, just waiting. And nobody may call you when you are waiting. It so happens that nobody from my street is calling me. Since I moved to my street 20 years ago, nobody from the street called me. I really see those people when I walk on the street and I say hello to them. But they don't call me at home because they're so close to me. However, a very different approach is to search maybe for a tennis ball that came from a neighbor's yard. I do find those. Just yesterday I found a ball in my backyard from a neighbor. So not everything that comes into my yard is made of rocky material, the type of objects that I see in my backyard. Every now and then there is a tennis ball, and it's not made of rock. Okay? Now, what is the situation with objects that enter the solar system, our cosmic neighborhood? The situation is that whenever we see an interstellar object that arrived from outside the solar system, the experts on asteroids or comets say it must be a comet. So, for example, Oumuamua, the first interstellar object, had no gas or dust detected around it, the way you see in a coma or a cometary tail around comets. So there was nothing around it. Yet now the experts call it a dark comet, which means there is a cometary tail, you just can't see it, it's invisible. And just to inform the conversation, this object, Oumuamua, that was discovered in 2017, had to lose about 10% of its mass in order to be propelled with non-gravitational acceleration that was detected for it. 10% of its mass. I'm not talking about a tiny bit of material. So they say that this 10% of the mass is invisible, even though the object itself was visible. So I feel as if I'm the kid in Hans Christian Andersen's tale saying the emperor has no clothes. I don't see any clothes. And then the adults in the room tell me, oh no, the clothes are invisible. And this is the mainstream view. Can you believe it? The mainstream argues that something exists that cannot be seen, that makes it a comet, a very visible conventional object. Now, it's just like saying that an elephant is a zebra without stripes. Okay? You would say, okay, stripes define a zebra. I see here an animal that doesn't have stripes. I call it a zebra without stripes. Why is that misleading? It's misleading for a simple reason that, for example, on January 2nd, 2025, this year, there was a near-Earth object. It was classified by the Minor Planet Center as a near-Earth asteroid, a rock. And then within a day, they realized that the path of this object follows the trajectory of the Tesla Roadster car that was launched in 2018 by SpaceX. So they immediately removed it from their catalog. Why? Because they knew about the Tesla Roadster car. This was not a rock, it was a car. And my point is, just imagine that Elon Musk is not the most accomplished space entrepreneur since the Big Bang, 13.8 billion years ago, and that there are interstellar cars. In that case, we would not know that it's not a rock because we don't have access to the trajectory that this interstellar car was launched in. So we would say it's a comet without a visible tail, or it's a rock. And when astronomers would say that, they would have no hesitation. But yet what I'm trying to argue is we need more data to figure out the nature of an object. Now, I defined a new scale a month ago that is now called the Loeb scale. There is actually a paper about it in the Astrophysics Archive, where 0 means a natural interstellar object, where we can see the cometary tail, or we can definitely infer that it's an icy rock for some other reason. And 10 on that scale is a definitely technological object that we can tell because it maneuvers, or it broadcasts a message, or it emits some artificial lights. It has a light source in it. It's not just reflecting sunlight. And I define also all the numbers on this scale between 0 and 10. I suggested that Oumuamua, the object I was talking about, has a rank of 4. And the same is true also for 3I Atlas, a rank of 4. Now, once we see a clear technological signature, then it will go up the scale. But if we see a clear natural signature, it will go down the scale. Science is a learning experience, and I would revise my rank based on the data. And of course, we might learn more about this new interstellar object, 3I Atlas, discovered in July 2025 by a half-a-meter telescope in Chile called Atlas, which happens to be, by the way, a neighbor of the Rubin observatory that was inaugurated in June 2025. And the Rubin team was able to find this new object, 3I Atlas, in the weeks preceding the discovery announcement. And so this small telescope scooped the Rubin telescope, which is 8.4 meters in diameter, with a camera of 3.2 gigapixels that will survey the southern sky every 4 nights, and actually could discover, based on expectations, an interstellar object every few months. And so this opens a new era where we will have a lot of interstellar objects, several dozens of them in the coming decade. And we could then ask the question, what is the rank of each of them on the Loeb scale between 0 and 10? And if any of them ends up being technological, this would be of great importance, because if it's a functional device, the question is there any threat to Earth? Because we are always talking about the existential threat from artificial intelligence, from global climate change, or from an asteroid impacting the Earth. We don't talk about alien technology. And it's very different from an asteroid, because in the case of an asteroid, there is this planetary defense office at NASA that is monitoring objects that may come close to Earth. And the idea is that once you know the trajectory, the orbital parameters, you can calculate whether they will hit the Earth anytime soon. And that's just following the laws of gravity. However, if you have a technological object, then it could maneuver. It doesn't follow just gravity, and it could pursue some task. So the defense against that is very different. And in the future, I'm not expecting anything to be done immediately until we will have clear evidence for a technological object ranked 10 on the Loeb scale. And then, of course, this would be a wake-up call. And we would immediately establish an international organization that includes people from all countries, because, the aliens do not really care about how we split territories on Earth. And whatever happens at one location on Earth could happen shortly afterwards at another location. So all humans should come together. No country, no nation should use this encounter to harm another nation. And based on all available data that one needs to collect with all telescopes, all assets in space that we have, those that are used for national security should be retasked to look at whatever technological object is visiting us. And based on that information, policymakers will decide about how to respond to it. You cannot decide ahead of time because you need to know the details. What we can imagine in terms of technologies is limited to our experience. And as I said, what comes from another star is a whole new ballgame. It could represent technologies that we've never imagined. Not even producers of science fiction films in Hollywood imagined, because it goes beyond the science and technology that we know about. So we will have to respond depending on the qualities and the intent of the visitor. I believe that this will change the future of humanity, because after we have such an encounter, there will be questions asked about future encounters. And, we will have to put perhaps an array of spacecraft within the solar system that monitors the solar system for any incoming objects and alerts the Earth for any technological object that may be coming our way. We might need to come up with an interception policy of what to do if there is an imminent threat, whether to use nuclear weapons or not, or whether to always welcome whoever comes to visit us. It's just like imagine having a person in your backyard and you are consulting with your family members what to do about this person. It's not like getting a radio signal or getting a phone call. In case we get a radio signal from a source that is thousands of light years away, we have plenty of time to decide what to do about it. We don't need to worry about an imminent threat. But in the case of a visitor in our backyard, that visitor may come through the front door. You have to decide immediately what to do about it. And that is a completely different situation. All of this is to say that what the SETI community did in the past, which is waiting for a phone call or trying to detect a radio signal, is very different from what can be done, which is detecting interstellar objects and checking whether any of them is technological. Because if that happens to be the case for one of them, it will change the way we think about space. It will change our aspirations for space. We might decide to visit other stars. It would change everything. It will change, if, for example, this new object 3I Atlas, as it comes closest to the sun on October 29th, 2025, if it maneuvers and takes advantage of a gravitational assist from the sun, the way our spacecraft often do. So in that case, if it wants to brake, it can actually do it most effectively closest to the sun. By the way, we won't be able to see it because the Earth would be on the opposite side of this object 3I Atlas when it comes closest to the sun on October 29th. But if we don't see it coming from the other side the way we expect, the stock market may crash.
Let me ask you this before we get directly into 3I Atlas and how we actually can observe it when it's behind the sun from Earth's perspective, but we have other spacecraft out there. But before we get to that, what are the statistical implications of turning on the Vera Rubin telescope and doing the surveys, which it promises to catch many interstellar objects so that we'll have a robust population to study, in coming years. But what happens if, because, back during the days of Oumuamua's passing, we, there were all kinds of ideas out there, and we talked about many of them in past shows. But you should be, given that it was the first thing we saw, and it was weird, and you pointed all of that out. It was weird. But we should see a lot of those. What happens if the Vera Rubin telescope fails to pick up any further objects like Oumuamua that have that strange
that would
of a group
enhance
of
the
characteristics?
mystery.
What would that mean?
Why did we see it only once? Of course, for natural objects, you can do the statistics and you say, okay, I looked at the sky with these sensitivities for a period of 1 decade. I found one object. Then I'm very likely to find more of the same in the coming decades. It's just simple statistics. Now, it doesn't mean that you definitely have to find, but if you have an instrument with better sensitivity so that you can look for objects across a bigger volume, then the number of objects you will find will scale as the volume that is being surveyed for objects on random trajectories. There is no way out of that. And the Rubin Observatory is much more capable than the Pan-STARRS telescope that discovered Oumuamua. And if it doesn't find, given its bigger sensitivity, bigger survey volume, it doesn't find any Oumuamua-like objects, that would make Oumuamua even more peculiar than it was. I should just mention that it was spinning or tumbling every 8 hours, and the amount of sunlight reflected from it changed by a factor of 10 as it was tumbling. And there is a detailed paper that was attempting to make a model for the shape of Oumuamua, and the best fit model at the 92% confidence was that of a pancake-shaped object, a flat disc-like object. So it wasn't just strange because it had non-gravitational acceleration, but it was strange in terms of its shape. And I'm just saying, when something looks strange, let's admit it. Let's not say there is a cometary tail, but we can't see it, it's invisible because this object is made of hydrogen, nitrogen. We've never seen any icebergs made of hydrogen or nitrogen. If the first interstellar object we see is behaving so strangely, it must be very common. So my point is, let's maintain our curiosity. Let's keep it alive. And, rather than shove all the anomalies under the carpet of traditional thinking. And to my surprise, practitioners, especially the SETI community, I should say, there are members of the SETI community that are violently opposed to considering Oumuamua or 3i Atlas being anything other than a comet or an asteroid. They are violently opposed to discussing that possibility, and they insist that the only thing we should do in the context of searching for intelligent civilizations is search for electromagnetic signals from far away. And I simply don't understand that, because people who search for dark matter, there are different proposals for what dark matter is. We mentioned two of them. One was weakly interacting massive particles. Another one was primordial black holes. I've never, I went to many conferences on the nature of dark matter. I never heard the group of people advocating for primordial black holes saying, we don't want to listen. We don't want any talks in our conference on the possibility that dark matter is made of weakly interacting massive particles. I've never heard that. However, the SETI community decided, as a rule, not to discuss objects near Earth in their conferences. There are unidentified anomalous phenomena that are objects not identified. We don't know what their nature is. That subject is banned from SETI conferences.
Well, do you think there is a deep-seated ontological fear or fear of ontological shock by finding that an alien civilization was closer than you thought it could be? Now, people will cite all kinds of statistics and say, well, what are the chances of having one right next to you or something like that? But we don't know what the rules are. We don't know what aliens do.
Exactly.
And we wouldn't know.
Yeah, exactly. It really, so let me illustrate that with 3i Atlas, okay? So when 3i Atlas was discovered and was announced, that night I had to wake up at 2 a.m. because I was speaking on Coast to Coast. And one of the listeners emailed me about this object. And as soon as I learned about its brightness, I calculated how big, if it's a solid object, how big it could be. And I found that it needs to be 20 kilometers in diameter in order to reflect enough sunlight for a typical reflectance coefficient, albedo, of 5% that is often observed for rocks, for asteroids. And a 20 kilometer is huge. It's bigger than Manhattan Island. It's twice the size of the asteroid that killed the non-avian dinosaurs 66 million years ago. And, there should be 100,000 objects like Oumuamua. If Oumuamua and 3i Atlas are both rocks, and we judge by what we find in the solar system, in the main asteroid belt, you would expect 100,000 objects like Oumuamua for any one that is 20 kilometers in diameter, like 3i Atlas. And we haven't seen 100,000 Oumuamuas before we saw 3i Atlas. There was Oumuamua, then there was Borisov, and now 3i Atlas, that's it. So that was very puzzling to me. On the 4th of July, just a few days later, my wife wanted us to go on a vacation, and I, of course, could not take the time off because I wrote a paper saying, it's not just the number puzzle, it's also if you calculate how much rocky material should exist in interstellar space per unit volume, and then you package all of it in 20 kilometer sized rocks. So imagine all the interstellar rocky material is arranged into rocks of size 20 kilometers. Then you should get one of those per tens of thousands of years in the inner solar system. And we surveyed the sky only for a decade, and we found 3i Atlas. So it can't be that it's a 20 kilometer rock. There is not enough rocky material in interstellar space to give it to us once per decade. And I'm talking about a discrepancy by orders of magnitude, not a factor of 2.
Yeah, no, it would be centuries.
Yeah.
You would only see that big every
millennia,
1,000 years,
10 millennia.
Yeah.
So the last time such an object came would be before humans documented their history, like 10,000 years ago. That's if you make the optimistic assumption of packaging all of the rocky material in such objects. So I said, that makes no sense. So of course, one possibility that I suggested in my paper was to say, actually, the nucleus of this object is much smaller, less than a kilometer. and it's surrounded by a cloud of dust which reflects sunlight. So what we are seeing is mostly the light reflected by this cloud of dust, the way comets look. And then I had the concluding sentence: the alternative is that this object targeted the inner solar system by design. And the editor wrote to me, "We will publish your paper as long as you remove this last sentence." And I thought to myself, amazing, isn't it? That just one sentence in a paper makes the editor upset to the level that he will not accept my paper for publication unless I remove the possibility that it might be technological and it's targeting the inner solar system. But, you know, the rebel that I am, because of that experience, I decided to write a full paper on the possibility that it might be technological. So at the end, it was not one sentence, it was a full paper that was published afterwards with my colleagues, Adam Hibberd and Adam Crowell from the Initiative for Interstellar Studies. In that paper, in addition to the argument I made about, you know, the object cannot be that large, and if it's not a comet, it could be technological, that because it targeted the inner solar system. So its arrival into the inner solar system has nothing to do with the rocky material in interstellar space, has nothing to do with that reservoir because it targeted the inner solar system. Now, it turns out that the trajectory of 3I Atlas is very fine-tuned, completely consistent with this notion. It actually lies in the plane of the planets around the sun to within 5 degrees. There is an illustrator that shows in 3 dimensions the trajectory of 3I Atlas, and what you see is an object coming from very large distance, and it's aligned with the planets. Now, the chance of that happening at random is 1 in 500. But suppose you say, okay, you know, miracles occur. Every now and then you have something very unlikely happening. You say, okay, I accept this trajectory. It's not designed, it's in the plane of the planets by chance. But then you can play with the arrival time. It turns out that the arrival time along this path is also very fine-tuned. You just look at the orbits of Mars, Venus, and Jupiter around the sun. You know, these planets are moving around the sun, around and around and around. This object, 3I Atlas, is getting very close to all 3 of them. And the chance of that happening with a random arrival time is 1 in 20,000. So I said, whoa, wait a minute. Could this trajectory represent a design that is intending to pass close to these planets and, you know, for example, release mini probes that will visit those planets or do a reconnaissance mission? The second thought that I had is, this is great. It will come close to Mars. We have some orbiters, some spacecraft near Mars that can look at it. There is a 0.5 meter camera, high-rise, that can look at it. And I actually communicated with the research team of that camera just yesterday, encouraging them to look at 3I Atlas when it comes close to March on the 3rd of October, 2025. On March 16th, 2026, 3I Atlas will come close to Jupiter. And there is a spacecraft called Juno that was launched in 2011. It was doomed to crash into Jupiter in mid-September 2025. So I wrote a paper saying, let's not push it into Jupiter, let's push it away from Jupiter so that it will come close to the path of 3I Atlas and can rendezvous it, basically come close to it, maybe intercept it or just come close to it, depending on how much fuel it has. And we calculated in the paper how close it can get to the path of 3I Atlas in mid-March 2026, depending on how much fuel it gets. It has. And even with 10% of the initial fuel that it had, it could come within 25 million kilometers of 3I Atlas. If it had the original fuel reservoir, it could have intercepted it.
Well,
So
you
a day-
calculated, though, you calculated based on its fuel usage. You got an estimate, right?
Yeah.
That it actually has a fair amount of fuel left, right?
Well, I spoke also with the team of Juno and asked them to estimate how much fuel they have. But Just a day after I submitted my paper for publication, I got a phone call from Congresswoman Anna Paulina Luna, and she wanted to get an update about 3I Atlas from me. And I mentioned this paper to her, and she volunteered to write a letter to the head of NASA, encouraging NASA to look into the possibility of using Juno to probe 3I Atlas. And I'm really grateful for her vision. But overall, this object 3I Atlas is described as a comet by the comet experts. It came from the direction of the center of the Milky Way galaxy, which is very crowded in stars. And that may be a good reason to come from there if you don't want to be identified early. That's why we discovered it only in July 2025. It also moves on a retrograde orbit, which means that if it sheds any mini probes, they would move opposite to the direction of motion of the planet, so they can easily meet a planet along its path around the sun. It doesn't need to chase the planet. So a retrograde orbit aligned with the plane of the planets around the sun, was the most unusual thing that I realized that this object possesses. And now the question of whether it's a comet, first of all, there were several teams that tried to detect the signature of gas around it, and they couldn't find the spectral fingerprints of any molecules, carbon-based molecules or oxygen atoms that are often found around comets. And then there was the best image that was obtained was taken with the Hubble Space Telescope. And in that image, we see a relatively compact glow of light around 3I Atlas that extends out to 10,000 kilometers. And it looks like a coma that is often associated with comets, but it leads the object. It's in front of the object. There is no evidence for cometary tail behind it. Now, the spectrum of this object, 3I Atlas, is reddened. We see reflected sunlight that is reddened. Of course, to get it from dust that is outflowing from a comet, you need dust particles that are roughly of the size of the wavelength of sunlight that is being reflected or reddened. But if they are a fraction of a micron, half a micron, the wavelength of visible light, then the radiation pressure from the sun would push them within a day, I calculated, to trail 3I Atlas. And so we should have seen a tail that is very often seen around comets. And so we don't see that. We don't see a bright tail of dust particles that are doing the reddening behind the object. And the question is why? And another mystery is, in the analysis paper of the Hubble image, there is a plot, figure 3, that shows the brightness profile around the nucleus. And projected on the sky, what you see is that the brightness scales inversely with angular separation from the nucleus to the third power. This is much steeper, a much steeper brightness profile than found for comets. Usually what you see is 1 over the angular separation, which you can understand because if there is an outflow, a steady outflow of dust from a comet, then the density of the dust will fall off inversely with distance squared. And then in projection, it would appear like the brightness falls off inversely with distance. So that's very often found around comets. In this case, it was 1 over angular separation cubed. So that means in real space, the brightness falls off inversely with distance to the 4th power. So how can you get that? Well, if you have an outflow of dust where the density declines inversely with distance squared, and you have a central source of light where the flux falls off as 1 over distance squared, then the combination of the two, if you scatter the light coming from the central source by the outflowing dust, you will get 1 over distance to the 4th power. So is 3I Atlas generating its own light, or is it reflecting sunlight? This is a question that I'm trying to address in my next paper. These are interesting questions. There is an anomaly about the brightness profile of this object. There is an anomaly about, the fine-tuned trajectory of this object. There is an anomaly of not seeing a cometary tail behind it. And I'm just saying, let's continue to monitor it. Because if it's a comet, then it would get warmed up as it comes closer to the sun. And we should see it erupting in volatiles, in dust particles, in gas. And we should see a beautiful cometary tail behind it. But if it's something else, we will not see that. And so we shouldn't prematurely announce that it's a comet like the ones we know about in the solar system. That was the case for 2I Borisov, which looked very similar to comets that we are familiar with. This one does not look like 2I Borisov at the same separation from the sun, roughly. So let's continue to monitor it and figure out whether it's a 0 on the Loeb scale or maybe a 10 on the Loeb scale.
Now, with this object, I have two questions. And the first is okay, it's passing somewhat near 3 planets in the star system, but it had an opportunity, had it been launched earlier from a different angle, to take advantage of something like, I don't know, the Grand Tour arrangement of 1970s and 80s, where you were able to, if you were coming in from outside of the solar system, you could have hit closely a number of the inner planets and then had all of the outer planets aligned. If you're going at these sorts of velocities and using gravity assist to go between the planets, you could have seen a lot more than 3. Why didn't it come earlier?
Well, maybe it did. The point is, we had the capabilities of surveying the sky only over the past decade. That's why all interstellar objects were found over the past decade. And of course, it cannot be a phenomenon that is just now happening. It could have happened before. But if we didn't really monitor the sky with, the kind of equipment that we're now using, we didn't have the computers we currently have to process the data, then we would have missed it. The timing could also reflect an interest of an alien civilization in us, because we keep broadcasting our existence without being careful about it. And by now, over the past century, our signals went 100 light years. Now, if you ask, when did 3I Atlas enter the outskirts of the Oort cloud, the outer boundary of the solar system, at 100,000 times the Earth-Sun separation? That happened 8,000 years ago, if you take the measured speed of 3I Atlas. So it entered the outskirts of the solar system 8,000 years ago. That's when humans started documenting their history. And that's assuming that it came from far out. If it happened to have originated from 1,000 times the Earth-Sun separation, it would have taken 80 years. From 100 times the Earth-Sun separation, it would have taken 8 years. So it all depends on where it started the journey. And of course, if it's a natural object, if it's a comet, it could, as we discussed before, it could have started the journey, 7 or 10 billion years ago. Just for comparison, Oumuamua was almost at rest relative to the local frame of reference of the Milky Way galaxy, the local standard of rest, when it entered the solar system. Solar system just bumped into it. That was an unusual fact, and it implies that with the same analysis that I did with my student, we found that if Oumuamua was a natural object that came from a star, it must have originated from a very young star that is only about 1 billion years old. 2I Borisov, the second interstellar object that was a comet, that one it was intermediate between Oumuamua and 3I Atlas in terms of its speed, and it could have originated from the population of stars that have the same age as the sun, about 5 billion years. So we got a sample of 3 different speeds, very different from each other. 3I Atlas is the fastest by a large margin. As far as I'm concerned, the fundamental question is, what is it? Why did it come in this very special trajectory? Because in general, interstellar objects like Oumuamua or 2I Borisov, they came at a large angle relative to the ecliptic plane of the planets. This one just came aligned with the ecliptic plane.
Yeah, that's strange that it would. Aligned with the ecliptic plane, even if just a few degrees off as it is, you're not going to see that very often. Yet there it is.
Well, 1 in 500 or several hundreds. And the point is, we didn't have several hundreds objects like 3I Atlas detected before we saw this one aligned. We just had this one aligned, and it's the fastest moving object, and it doesn't have a cometary tail, and it comes close to 3 inner planets. And so I just say, let's monitor it, let's pay attention to it.
Well, I think it'd be a wonderful idea because it's not just Juno that's, Juno literally is at the end of its life. They're going to deorbit it and dump it into Jupiter. Might as well reuse it if it can be reused. And I read Anna Paulina Luna's letter and I thought, well, that's good. You advocate in Congress, right?
Right.
To look. But we also have Mars. And I wanted to get your views on what could we do with the existent probes that we have sitting at Mars, like MRO,
Yes.
and gather other observations of 3I Atlas.
Yeah, so MRO has a large number of instruments, one of which is a 0.5 meter aperture camera, high rise. And I suggested to the team to actually look at the 3I Atlas on October 3rd when it comes close to Mars. Hopefully they will do that. They were quite positive, but of course there are issues with the direction of that it comes in and the fact that it moves fast. And but they're on target. They are thinking about focusing on this object at that time. And we need to keep our eyes on the ball, just like basketball players say. It's not about what is written on social media. It's not about the audience, not about getting likes. It's about keeping our eyes on the ball. 3I Atlas.
Well, obviously, take a look. It's right there. Take a look. Use, especially when you have a bunch of instruments that are at end of their lifetime. Take a look.
Right.
Use them. And I suspect NASA will, because they tend to do things like that. To give them their fair share, their fair due, they do things like this. So it would not surprise me if they repurpose these, instruments, or at least take a look. But I want to ask you this: with Juno going from Jupiter, with its instrument package, what could we measure if we got close?
Well, we can measure energetic particles, we can measure magnetic fields, we can try to image the vicinity of the object depending on how close we get to. And I think altogether it will be a boon to NASA because of the public interest. So here is another important point. Some of the SETI people or other people in academia were criticizing and saying, oh, forget about Juno. It's not interesting. It doesn't have enough fuel. It will not succeed to give us any information. We should keep it on looking at Jupiter and that's it. And this kind of dismissive approach.
Yeah, but it's only going to look at Jupiter for like 8 more days.
Yeah, but just to show you the state of mind of some of these people, they would rather not look. I find it really puzzling because the public, is extremely interested. Over the past 10 days, I had 250,000 people reading my essays on medium.com. 250,000 reading essays. These are not tweets. Okay. And there is a huge amount of interest. Every day I get hundreds of emails, many of them excited about observing 3I Atlas. This is an amazing opportunity to attract the public to science, to inspire young kids. And I see it everywhere. Like there is a carpenter that fixed our porch. He came to my wife and said, what is Avi up to? What's the latest on 3I Atlas? And I've never met him. So she asked me to come outside and I gave him a copy of my book. I signed it and he was taking a selfie and said, look, my hand is shaking. I can't believe that I'm standing next to you because I'm so excited about this object and I'm following everything you do about it. Another person said that he was with me on a Zoom call at a sports club in Santa Barbara. After he finished the conversation, someone came over and said, you mentioned the name Avi. Is this Avi Loeb? I can't believe you were speaking to him. There are millions of people in Spanish-speaking countries that read translations of my essays on 3I Atlas. And, over the past week, every day, on average, I had about 6 to 8 television, radio, newspaper interviews. And I'm trying to communicate the excitement of science that, it's all based on evidence. We can address exciting questions. Many of those critics are missing the point. Some of them are people who, didn't publish a single scientific paper over the past decade. These are bloggers or YouTubers that criticize the discussion on a possible technological origin. And I published over the past month about a dozen scientific papers. And they haven't published a single paper over the past decade. Yet they are attempting to save science. From whom? From the people who practice science. I'm in the trenches doing the scientific work. I also communicate it to the public because I think it's important. It might inspire young kids to become scientists if they realize that we can address fascinating questions that their parents wonder about using the scientific method. So we don't know for sure if something is a comet. We will find out by taking data. This kind of a message is an amazing message, that you cannot convey even if you put $10 billion into the Large Hadron Collider and claim that you detected a new particle. Because, okay, you detected a new particle, you're announcing it to the public after the fact. They don't follow the process. And they don't understand the implications. And it doesn't have implications to their private life. But if 3I Atlas happens to be a technological probe, it will change the life of everyone. It will change the future of science, the future of religion. I had a group of religious scholars that came to Harvard and wanted to meet with me. They belong to an organization called Christianity Today. And they asked me, if we find extraterrestrials, would it affect in any way our religious belief? And I said, well, I have 2 daughters. And when the second one was born, it didn't take away from my love to the first one. So imagining that God is like a parent that can attend only to one child is very limiting. You should be happy if there are many civilizations. If we have siblings, the only issue is if we have siblings, we might be jealous at one of them because that one is far more accomplished than we are. That happens if you have brothers or sisters and they are more accomplished than you are, you might be jealous. But other than that, it's actually a testament to your parents that they have more than one child, to their ability to manage such, so it's...
Well, but when you all right, I am not a religious person, of course.
I can tell you that they accepted this answer. They were very happy.
Well, I just immediately thought, it's if there is such a thing, and I'm like Einstein, I think in terms of the God of Spinoza and things like that. However, by definition, it would be omnipotent. It would be omnipresent, omnipotent, omniscient.
No, but the fundamental question here, even if you adopt Spinoza's view that the universe is identified with nature, the question is, does nature include more than one species of intelligent beings, more than one civilization? Given that there are billions of Earth-Sun analogs, would there be an issue?
No.
Imagining concept, irrespective of which concept of God you have.
No, you would think.
Would it be a problem to imagine
if you're
that?
Thinking in that framework, it can do anything. So so there you go. There's your answer. Is that it is omniscient, omnipresent.
Right.
It can handle anything.
Yeah. So that basically strengthened my argument that also if you imagine it being active, God is actually caring about us. It can care also about siblings the way parents do, and for us to meet our siblings in the Milky Way galaxy would be very enriching because we can learn from them.
Unless you meet them and they have their own religion and they're saying no, Zeus and Hera were the that's if you run into a religious conflict with an alien civilization, that's not going to end well. I don't think it never did with humans.
Oh no, but that happens also. That happens also when you meet a sibling that shares your DNA that was separated from your family. There is always the risk that they obviously develop different views of life and so forth. And, that has to be discussed, obviously. And we always, we don't know if we see technological spacecraft arriving into the solar system, and we don't know if their intentions are good or bad. And of course, the way to find out is to exchange a message or to get a better sense of what the technology includes. So if it's an object that is just passing through the solar system and moving out of it, and they just wanted to monitor whatever they see along the way, it's just like a car in a highway. You let it pass. You don't worry about the implications for your home. So it really depends on what it does. And, the fundamental perspective that I have is that we are not that important. That was the message that Galileo and Copernicus brought, that we are not at the center of the universe. And that may be also that we are not at the center of the intellectual center of the universe, that, they don't care about us. We just came to exist over the past few million years. They started their journey billions of years ago, before we existed. They're just passing by and trying to learn something. We can't fully understand it because they arrived at our backyard before we arrived at their backyard, so they're probably more advanced than we are, or had more time. And so, I'm just saying, let's just monitor what is happening on our cosmic street and in our backyard. Figure out whether we have an intelligent neighbor, not by assuming we know the answer in advance or making all kinds of intellectual gymnastics. Here I'm advocating exactly for the opposite of what is done in the context of string theory, where you have a conjecture that there are extra dimensions, but you can't really test it in the lab. Here, you make a conjecture that you can test by looking at the sky, and the only
go look at 3i Atlas. That's
look at 3i Atlas.
Go look at it.
Other interstellar objects. The only obstacle to that would be skeptics who argue we don't need to look. We know the answer. It's a comet, and how dare you discuss something else?
Well, I can't do that, though. I have to, again, you mentioned the Copernican principle, and I have to adhere to that, in that I do not think I'm a unicorn. I do not think human civilization is a unicorn in the universe, and I don't really think that there's a way to be alone, basically. Yeah. I don't think that we can be.
That's exactly my view. I was invited by the Polish government a couple of years ago to give a lecture in celebration of
Copernicus,
450 years to the birth of Copernicus in his birth town, Torun, in Poland. And the title of my talk was The Next Copernican Revolution. It's exactly what you just said.
Well, it's also the mediocrity principle. It's the same thing, that I do not assume that I can't assume that I am not part of a statistical population of like occurrences, like everything else in the universe is. So why would human civilization, technological civilization, be unique? I don't see how it could be. That does not speak to rarity. It may be rare. At any given time, you have the time issue where you may not exist at the same time as the other civilization does, at least within close enough proximity. But that doesn't actually mean anything as far as exchanging interstellar trash. So,
but my point,
the Tesla flying the ExoMusk that sent out the Tesla a million years ago that flies the solar system. Well, there it is. It has a much longer lifespan than any human. We don't know how long human civilization is going to last, or how long alien civilizations last in general. But if they last millions of years, their trash is going to be everywhere. Their Pepsi bottles flying through the star system. Isn't that wild of an idea, really?
My point is that there is a common thread between everything I said, and that is that we need a sense of humility. So humility says we shouldn't pretend to know the answer in advance. We shouldn't pretend to be the adults in the room. We shouldn't pretend to be those who know which path to take, but we should explore different paths. If we can search for radio signals, but we should also search for packages in our mailbox. We can search for microbes, but we should also search for intelligent beings at the same time, because we don't know what is easier to detect. And that sense of humility is basically driven by curiosity, allowing yourself to be curious, not to assume that something is more likely than another. And the only way to find out the answer is by collecting data. That also argues for a sense of humility in terms of who declares to be an expert that tells everyone else what the answer is? The public is pretty much fed up with that notion where experts, lecture in a conference room, at a press conference to the public what they need to know. Because very often what the experts are saying ends up after a while not being correct. And we see this culture of echo chambers in the way that funding occurs in science, where there are selection committees that are allocating funds based on echo chambers. They have friends that they allocate the funds to. They don't deviate from the beaten path because they want to get funded for whatever they do. And, that is a closed circle. You don't have oversight on where funding is going and how innovative the science is, and whether other paths are being explored. No, if the experts say this path should be studied, then we will all go in that path. And then if at the end of the day we don't find supersymmetry with the Large Hadron Collider, okay, we went in the wrong direction, but at least we know that we tried that. But then what about the other paths? What about other approaches to quantum gravity? What about other approaches to SETI, not just radio signals, electromagnetic signals, laser signals, but actually checking for objects that arrive close to Earth? What about that? Why not check that? And, we would never know that we are missing something unless we check it. And that requires a sense of humility, okay? It means that you shouldn't pretend to be the adult in the room. You should pretend to be the kid in the room that is exploring the universe with wonder, willing to learn something new. At the end of the day, if you look back at traditional religions, religion was all about telling people that there is a superhuman entity, and therefore, they are not the most powerful. And when Friedrich Nietzsche, said God is dead, and that was followed by a whole century and a half of modern science and technology. That's sense of hubris, that we humans are at the top of the food chain. That will very soon be violated by our own creation, artificial intelligence. Within decades from now, it may have superhuman capabilities, cognitive capabilities, and that will tell us that we are not at the top. It's actually a machine that we created that supersedes us. But even before that, it might be alien intelligence that is superior to human intelligence that we might find if we are only open-minded to that. In both cases, we will realize that we are not at the top of the food chain. Therefore, we should have a sense of humility, and that means that we should learn. And the best way to learn is from evidence, from data. But if you tell yourself, I don't need data, I know the answer, you will never learn that you were wrong.
I think perhaps and this comes from being a science fiction author, but I think the most fun idea is that if there is such a thing here, it's here to stop us from developing artificial intelligence that can escape the planet and threaten the galaxy.
Well,
you can't, we're here as a police maneuver. You can't develop that.
That's if they care about us. Frankly, my guess is that, for our own benefit, we should look for them to get inspiration and do better. We need better role models than we find in geopolitics. A better role model will come from another star, and that will be the benefit to us. It's not as if they need us. I think that they don't really care about us, and if they pass by, it's for another reason, and we need to learn from them. And therefore, again, with a sense of humility, and when Enrico Fermi asked in 1950, where is everybody? When he was sitting at lunch at Los Alamos discussing extraterrestrials, this question is a question that every lonely person asks. Where is everybody? Where is my partner? And what you tell a lonely person is, don't be so presumptuous. You are not that attractive. You need to go out. You need to look through the windows for neighbors. You need to go to dating sites. You need to be proactive. And, this is really, if you look at the scales of both time and space that the universe offers us, they are vast. And for us to imagine that we are the most significant creatures ever made, given that there are billions of Earth-Sun analogs in the Milky Way galaxy alone, and another trillion galaxies in the observable volume of the universe, and many more beyond the cosmic horizon. Just to imagine that we play a central role is really, wishful thinking. I mean, I remember my daughters thinking that they are at the center of the universe, that they are the most significant thing, because back then, when they were infants, their training data set, you can think of them just as large language models. They have a training data set, and their intelligence depends on that. So the training data set of babies is limited to their immediate environment. So when they were babies, they thought that the world centers on them, because all they saw is our home and the attention that the parents, we, gave them. And they thought they are the most important thing. When they grew up, they saw some houses from the windows of the home when they stood up, and they noticed that. But they never imagined that those houses may have humans like them, kids like them, that deserve as much attention. The shock came on the first day in the kindergarten when they saw plenty of kids like them, some of which are more talented. And we as a civilization, and also, members of academia, have not matured in the perspective we have. We still argue that we might be, the only thing, and the universe is really, that's a rare occurrence, and the universe is really all about us figuring it out, just the way my daughters were when they were infants. And I just say, it might not be the case given the number of statistics. Let's be humble. Let's have some sense of cosmic modesty. Explore the universe with curiosity instead of being dogmatic. The best way to tell the difference between a dogmatist or a conspiracy theorist and a real scientist is to give all of them a lot of data. The conspiracy theorist or the dogmatist will be very worried about that, because whatever data you give them or evidence may violate what they believe in. A genuine scientist will be extremely happy. The more data, the better, even if it goes against what the scientists thought before, because it's a learning experience. We learn from the data, we learn from the evidence. We know throughout the history of science that we were wrong. Very often, the mainstream was wrong. And just think about quantum mechanics itself. Nobody expected that. Nobody ordered that. It was a complete surprise that the physical reality behaves in ways that are not deterministic. That quantum systems show entanglement, spooky action at a distance, according to Einstein. He himself had an issue with that. It was not at all clear how to interpret that, not to speak about nobody expected that to start with. And what does it tell us? It tells us that if you establish a research narrative where you know in advance what you're trying to discover, then you will not discover anything. Why? Because whatever is defined as a major discovery is something that was not expected. And so you should have a sense of humility and find different paths towards the truth. And moreover, allow yourself to learn something that goes against your dogma or paradigm. Allow an object that enters the solar system to be anything. It doesn't need to be a comet. Let's see what the data tells us.
And let's collect the data. Now, I have two final questions, but I have to throw an observation out. If you run into an alien intelligence, a superintelligence that isn't biological, it may, again, to hammer this home, it may just be here because we're developing artificial intelligence. We may not be important, but the artificial intelligence is. And all of a sudden, we end up with the alien intelligence running off with ChatGPT off into the universe.
Right.
And everybody, human civilization is like, that was it?
No, that's a very good insight. In fact, Martin Buber, a philosopher, used to be at Princeton University a century ago. He came up with three types of interactions back then, a century ago. One was the interaction of humans with objects, the interaction of humans with humans, and he was religious, so he had also the interaction of humans with God. But obviously, there were no computers back then and no artificial intelligence systems available. And what we are confronting right now is additional interactions, human AI interactions And AI interactions, just think about how fast will AI accelerate if it were to correct itself and interact with other AI systems without the human in the loop. Finally, there is human-made AI interacting with alien-made AI. By the way, alien intelligence is also AI, so we should not abbreviate it. And of course, it might well be if both of them are based on silicon, the human-made AI and the alien AI are based on silicon, they might feel kinship to each other more than they do to humans who are made of flesh and blood. And as you say, now, it could, in principle, help us. Our own AI could help us decode whatever messages we get from a visit, because maybe our brain is not capable enough to figure it out. And it's just like the Enigma code during the Second World War that was figured out by Alan Turing's team using computers. I mean, in principle, it may well be that we will need a superhuman AI that we produce to help us in figuring out alien AI.
If they could, because I bet you. Now, figuring out the Enigma code, that was one thing. Figuring out the US code, nobody ever did, because we were basing it on languages, Navajo, that were not connected to any other human languages that are extant. And at some point, that gets almost impossible to figure out if you don't have the key. And we just so happen to have the key. But I don't think that code was ever broken, right?
Yeah, so code breaking is an art that in the future might be dominated by quantum computers that operate very differently than traditional computers. And of course the question is, what do the aliens use and how complex is their language? And that's a very rich subject. And when we have an encounter with a functional device, that will open up new avenues of research. My hope is it will also inspire us if we realize that they traveled all the way to our home planet, and and we have all kinds of potential existential risks on Earth, then we should send a space platform with humans on it for a long journey as well to other places. And that's not a simple task, but I see it as a much more inspiring task than going to Mars. Why? Because Mars is just another rock that happens to be close to Earth, doesn't have an atmosphere, has dust storms, the temperature on the surface changes by hundreds of degrees, you're not protected from cosmic rays, you might not be able to survive unless you go underground into a cave. What I'm saying is, going from Earth to Mars, as much as it sounds very ambitious and visionary, is just like, being born in the jungle on a given tree and saying, oh, look at the distance, there is another tree where there might be more, we might go there. We don't know if something bad happens to our tree, maybe we should occupy that other tree as well. So going from Earth to another rock is very similar to that. But the point is that it doesn't really solve the long-term problem. And, we went out of the jungle into today, after a few million years, we are occupying high rises in cities all around the world. And the transition from trees in the jungle to high rises in cities is a major transformation, very different habitat, because in the city you get everything you need. And, going from the high rise of a modern city to space sounds to me like less of a leap compared to the transition from a tree to a high rise. And I do think that in the long-term future, we should contemplate a detailed plan for building habitats in space, a space platform, not just like the space station, but actually a place where people can live long-term, that can travel distances. That, to me, sounds far more appealing than imagining a rocket, a giant rocket that will bring humans to Mars, because once they get there, I would argue it's a much more challenging environment, less hospitable to life. What's the point of bringing people on a one-way trip where they would die soon afterwards from all kinds of risks? We really want to be smarter than that and establish something like Noah's spaceship. Noah built an ark to save animals from the great flood. And in my book, I refer to Noah's spaceship, and I wrote the book Interstellar where I talk about it. That will be the equivalent of Noah's Ark, except it will save representatives of humanity in space and perhaps interstellar space. Now, I'm talking about doing that in the future, but the sun formed in the last 1/3 of cosmic history 4.5 billion years ago. And that's exactly 1/3 of the age of the universe. So we are late to the party. Most of the stars formed billions of years before the sun. We can see them in the Milky Way galaxy. We can date them. We know that most stars like the sun formed billions of years before the sun. And that means that, the party was going on before we arrived. As a result, other civilizations might have lived billions of years ago. Where is everybody? Well, if you ask this question about humans on Earth, there were 100 billion humans on Earth, over the past few million years. Most of them are dead. Right now, we have only 8 billion that are alive. The rest are dead. The same may be true of other civilizations. Not only they existed billions of years before us, but they managed to die by now. However, some of them might still be alive, those that sent representatives to interstellar space. If we want to leave something behind, that will maintain the guidelines of the human civilization, that would represent us, we better aspire to build space platforms that would carry humans, and not just to the immediate vicinity of Earth, not just to another rock like Mars, but actually go interstellar with many generations of people on the ship.
Well, the idea, and this is actually the Jeff Bezos vision, but it goes back before that. His professor was Gerard K. O'Neill, and O'Neill cylinders and things like that, where people could live on giant O'Neill cylinders, and you could send those interstellar. I mean, it's possible to make a generational ship.
Yeah. So here is my question: could it be that 3I Atlas is one of them?
No, well, maybe.
In Rendezvous with Rama, the size of Rama,
yeah,
in Arthur C. Clarke's novel, science fiction novel,
very good novel.
The size was, it was a cylinder, and the diameter was 20 kilometers. The length was about 50 kilometers. That's not very far from the inferred size of.
Well, depending on inferred size with 3I Atlas, that's a big question. But the question is, did you read the novel and did you like it? Rendezvous with Rama.
I didn't read the novel. I actually learned about it after I wrote my paper on Oumuamua, and people noted that I should check it out. Now, I don't like science fiction because very often the storyline deviates from the known laws of physics. I enjoy doing science where, I follow the laws of physics as we know them, and I guide my imagination based on that. But I have a problem when someone talks about things that I know are, we have no evidence for. So,
well, also no ability, because then that becomes fantasy. But good hard science fiction, like Arthur C. Clarke, was pretty good at that.
Yeah.
Where it's like, there's some plausibility there. Maybe not entirely.
He was definitely very visionary and wise, and I would much rather learn from a first-class science fiction writer than from a second-class scientist.
Now, my last question for you, Dr. Loeb, is this. The Galileo project, you have a new observatory coming online. Tell us about that.
Yes, so over the past 4 years, we designed a framework of an observatory that monitors the entire sky at all times in the infrared, visible light, radio, and audio. And that's very different from astronomical observatories that are usually focused on a small portion of the sky at any given time. And the reason is that we want to check any objects within the Earth's atmosphere that are flying very fast across the sky. We want to find out if all of them are familiar, all of them are human-made, such as drones, balloons, airplanes, helicopters, satellites, or natural, like birds. Check whether there are any outliers. For that purpose, we need to identify the distance of each object that our cameras are recording. That capability will be available to us within a month because we will put multiple units within each observatory that look at the same object in the sky from different directions. It's just like the method of parallax or triangulation, and the reason that we have two eyes, by the way, is to protect ourselves from predators that might be very close to us. We can triangulate and figure out their distance and the level of threat. And so the Galileo project will use multiple units like that, hopefully within a month, and we will start getting distances. As of now, without distances, we can see a few million objects every year. Out of those, without distances, we can identify 97% of them as being human-made or natural, using artificial intelligence software, machine learning software that is trained on familiar objects. And of course, as we get more data, this software will become more efficient. But the distances are really essential for figuring out the velocity or the acceleration of objects so that we can check if it's within the performance envelopes of familiar objects, human-made or natural. And so that capability will change everything, because then we can get to an object-by-object analysis, look for outliers that are really beyond what we can imagine based on what we are familiar with. And I really look forward to seeing if there are any such objects, because the Director of Intelligence delivered 3 reports to the US Congress about unidentified anomalous phenomena. And I was invited on May 1st, 2025, to give a briefing about the Galileo project to Congress. And I was informing them about what we are doing with the Galileo project. And I really hope that in the coming months, we'll be able to say something statistically about whether there are any anomalous objects. And we are finishing the construction of 3 observatories. One already exists in Massachusetts at Harvard University, another one in Pennsylvania, and a third one in Nevada. We will operate all of those and see what comes along. The Galileo project also has a branch that attempts to retrieve materials from interstellar meteors. These are objects that happen to collide with Earth at a speed that indicates that they came from outside the solar system. And there was one such object reported in 2014 by the US government satellites, and the data appeared in a catalog of NASA, and we arranged an expedition to the Pacific Ocean to look for the materials. We analyzed the materials that we retrieved and found some unusual chemical composition for about 10% of those molten droplets that we retrieved. And there will be a Netflix documentary that will show how this expedition went and the research within the Galileo project related to that, coming out in early 2026. That would allow the public, again, to be excited, interested in science that is evidence-based. And finally, one of the most recent research avenues that we are pursuing is getting access to data that will come from the Rubin Observatory, searching for interstellar objects that may be of technological origin. And so altogether, we want to find if there is any evidence for extraterrestrial artifacts near Earth that could inform us about a cosmic neighbor, just like finding a tennis ball from another neighbor in our backyard.
It's all fun and games until the tennis ball hits you. Now, Dr. Loeb, thank you for joining us today. And everybody should check out Dr. Loeb's books, which are available everywhere. Interstellar and Extraterrestrial, and interesting ideas and something to keep in mind for sure. Dr. Loeb, do you realize you were the very first guest on this show many years ago now? I believe 8, something like that.
Well, that's a testimony to your open-mindedness, and you've done a terrific job communicating science. And I really, I was asked on a podcast a few months ago, how do I want to be remembered? And I said, based on my future work, because the best is yet to come.
My thinking is that I don't want to be remembered. What I want to be remembered are the interviews I'm doing. So I always lamented that there weren't enough interviews done with Einstein. There are very few. And I mean, you can find them on YouTube.
By the way,
so what I'm trying to do is document the people that actually are smart in this world, above and beyond.
And you know, that's important for another reason, because once you have a lot of interviews, you can, in principle, train an AI system on that data set so that even after the person dies, it could sort of provide us with an avatar, something similar that would answer questions that arise in the future based on the way that this person behaved, thought, and reasoned.
That is the future. That's the reality of the future.
So let's hope that this interview will be fed into an AI system long after I die, and that you know, there will be something representing me online that you can speak with even after I'm not around.
Let's just hope it's accurate and it doesn't have motives of its own to twist the information. Thank you, Dr. Loeb.
Thanks for having me.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.